field is, let's go back, my field is mainly, my research field is concentrated on internal reinforcement using FRP reinforcement. So from now I will focus about that, so about the long-term behavior of FRP as internal reinforcement. So as you know, here in Canada we have really a huge problem with the deterioration and degradation of the infrastructure made with the reinforced concrete. And the main reason for that is really the corrosion of steel reinforcement. Everything really is concerned by this. Any reinforced concrete structures in Canada is, of course, having this kind of problems. As you can see here, bridges, barrier walls, columns, piers, whatever, and also in parking garages for building. Unfortunately, sometimes it can lead to collapse of the whole parking garage. This is unfortunately, it happened in 2008 and killed, I think, 3-4 people killed at that time, unfortunately. And this is really due to the corrosion of steel reinforcement. So it's really a huge problem here in Canada. So this is why we started here in Canada a couple of years ago, developing design code and developing specification for FRP reinforcement. Here I'm showing first the specification. This is started in 2010 that we did the first edition. This is how to qualify and how to certify the FRP rebar. And now we have a new edition in 2019. So it was published last year. And I can tell you this it's include it's included new materials, and it's, from my point of view, the most comprehensive in the world. We introduced it, of course, it's maybe interest people from China. We introduced basalt reinforcing bars also as FRP reinforcement with all the requirement to be certified and so on. We have, of course, external reinforcement S808. We have also design code dealing with buildings, and we have also design code dealing with bridges. And we have the new edition also published in 2019. This is also, it's include design procedure and design clauses for all bridge components, in particular about the bridge deck slabs, about columns and so on. We introduced also something about the design barrier walls, and also how to repair bridges using FRP reinforcement. This is all, this material clauses, new clauses are really introduced in the new Canadian Highway Bridge Design Code. And if you need really more information on all this standards, please let me know and I can try to help you to get copy. This is showing the S807, the new edition, as I told you, one of the most comprehensive specs on FRP rebar in the world, and it's being used by different Canadian, North American and European, and also from China manufacturers using that. And this is the Canadian Highway Bridge Design Code. During the last few years, really we expanded the use of FRP reinforcement. Through my research group, we developed field application as world first, including multi-span bridge decks, including parking garages, highways, water treatment plants, piles, and so on. Some other applications include marine application. As you can see here, this is in the north of Africa, in Morocco. This was a huge project that I did with a French company. As you can see here, all the concrete, precast concrete jetties. It's having about 20-25 diameter. And here we have the one first cable bridge in Canada, also with GFRP. Also here some application in Miami, etc., using FRP reinforcement. One of the most recent applications that we achieved is dealing also with the marine applications. As you can see here, some piles. This is, most of the piles are pre-stressed using a steel cable and using steel rebar. It's being by what's called by the pile driving system. And we developed a new kind of GFRP reinforced concrete precast piles, including GFRP without any pre-stressing reinforcements. So it's only with the non-prestressed. It has 70 meter, 70 feet, and it's about 20 meters. The section is 600 by 600, and including GFRP. And we implemented them in one coastal bridge in Florida. And it was 2 years ago, and it's still really behaving very, very well. The pile survived and tested under the reinforcers and so on. So it shows you really the recent most development using FRP reinforcement. So now the next slide will be concentrating on the topic of today about the long-term durability and FRP and durability of FRP reinforcement. These are here the topic that I will be talking a little bit, which including the factors affecting the durability, accelerating aging tests. This is, of course, we don't have choice to evaluate in short time. We have to perform testing with accelerated testing, field durability studies, and some concluding remark and research avenues. Of course, as you know, the FRP material is very complex material because it's a heterogeneous combination, including fiber and resin, separated by what's called by the fiber matrix interface, and all of them really they interact together, the matrix with the fibers and the interface. Here this is photo showing the fiber distribution. And of course, even as I say before, FRP reinforcement is being used since the beginning of the 1990s. 90 here, at least in Canada, United States, and also some other countries in Europe. It's still that FRP bar durability is of concern for a few reasons. Of course, FRP bar is still new materials because, as I say, the most older application using FRP as internal reinforcement, it has only 24 years. So what we have as experience from the field is only 24 years compared to the traditional material like as steel. So it's nothing really. They are still, the industry is still innovating and developing reinforcement with improved properties. So there is some kind of FRP bar innovation is ongoing, and this is, we have it really in Europe, North America, and also in China, Australia, and many other countries. And also now most of the design codes, building, bridges, and so on, now they are not specifying only 50 years as service life, but most of them now they are specifying minimum 75, and there are a few of them even specifying 150 years. So really we have to show to demonstrate the durability of FRP reinforcement for this service life, of course, currently specified in the code. And unlike steels, FRP, of course, are resistant to electrochemical corrosion because it's non-metallic material, but however, FRP reinforcement could potentially deteriorate by different factors, including physical, chemicals, loads, moisture, temperature, and so on. And of course, the deterioration of the rate of damage of the reinforcement will depend on the multitude factors. So this is really, it's a multi-complex problem sometimes to resolve, you know. Is it coming from the matrix? Is it from the interface? The process of the manufacturing, and so on. So it's not really a straightforward problem or something like that. It's very complex. So for this kind of research, we developed really, I think, one of the largest durability lab at University of Sherbrooke, as you can see on this slide, including almost 500 square meters of lab testing, and we have for clip frame, we have beams, as you can see here, and so on, testing ongoing during the last few years. And we have, of course, all the microstructural analysis and so on. Degradation process in FRP bar are typically, we can say it, fiber dominated, matrix dominated, or interface dominated. And this is, of course, which one will be the dominated will depend, as I say before, on the type of the load and on the and in particular also about the environment and so on. So it's if you have an example fatigue problem, it's mainly, I can say, by the fiber dominated for the fatigue. If sometimes you have the alkaline solution, it could be really for the 3. It could affect the matrix, it could affect the fiber, and also it could affect the interface. And when you have an example, the interface is being affected, and you will lose the stress transfer, so you will not have really the composite, the reinforcement as composite material. You will have it like as dry fibers, and of course the strength will go down, and everything will go down due to this problem. So really it's very, very important to understand the durability performance and to perform testing, of course, and in particular looking to the microstructures. The interface, and sometimes even we can call it interface because it's really very, very small. We are talking about micrometer. This is as a key issue. The manufacturing process now, it's being, I think most of the manufacturers, they are making bars with high technology and taking care about the manufacturing process. Here I can show you some slides, SCM analysis, and this is, I recommend to all researchers doing durability on FRP as external, internal, whatever. You should really perform some preliminary testing and looking to the material as received by performing some microstructural analysis. As you can see here on this one, we look to this, when looking to this photo, we can see very good fiber matrix interface. There is no debonding, nothing in the material. But here, as an example, another example showing really poor bonding at the interface between the matrix and the fibers. And this is from the material as reference. It was like that. So it was done for a lot of many reasons. It could be non-compatibility between the resin and the sizing. It could be during the manufacturing process and so on. They are different, but you should really look at it before, because if you will not do this kind of analysis on this material and you will perform your durability testing, you will get not really good performance, and you will affect it to not really to the main reason, but the problem was from the beginning with this material. As here also you can see here on this slide, you know, this is, we did some durability testing, and we did interlinear shear strength, as we call by the apparent shear test by short beam. And as you can see here, this is after conditioning in alkaline solution. And as you can see here, SCM analysis on the fractured surface. Here, as you can see, the fibers and the resin, it's still with the fibers, you know, bonded to the fibers. But here you can see very smooth fibers. So on the right, because the interface was degraded by this conditioning, and not the one on the left. So this is to give you really more information. This is what we saw. All the researchers that they worked on basalt bars, the most problem with this material was the interface, and mainly not due to the resin and not due to the basalt fibers, but really due to the sizing. But now it seems that the industry, they found one good sizing, optimized sizing, that it works well with this kind of fibers, with basalt fibers. So it makes it maybe good, because we know, like for glass fibers, the sizing either with epoxy or vinyl ester is showing very good bond at the interface. Here also you can have in the material some porosity. This is also a kind of weakness in the material from the beginning, and this is also has to be well investigated before going to the testing. One of the factors which is affecting long-term durability is really about the glass transition temperature, and this is mainly linked to the curing, you know, and about the cross-linking in the resin. So if you have not material fully curved, you know, you will have it in this way. You will have some post-polymerization, as you can see here in this graph showing from the DSC. And when we do second cycle, because we are heating it at elevated temperature, we are completing the polymerization and we are getting this kind of behavior. This also, glass sponge temperature, is also very important factors. And there are many other factors, as I can showing here, that affecting the long-term durability. But there was a huge research on this topic during the last years. And now we know more about this material, and this is the reason why we come out now during the last few years about material specification and so on. But as I say, it's still some concern and some testing. Accelerating aging test, this is one of the solutions that we have to use, you know, to perform some testing to qualify the material or to know more about its long-term behavior is doing by accelerating aging tests. Most of the accelerating aging tests is based on Arrhenius model. As you can see here, you have the assumption, and we have to go with different temperature as so on. As you can see here, this is the moisture uptake with 4 different temperatures. As you're increasing temperature, the rate of moisture uptake is increasing. So you are accelerating the diffusion. So this is why we have, but you should not change any degradation. So the degradation should be only connected to the accelerating aging and the temperature. He's showing some bath that we are using in the lab. We did a lot of testing, including alkaline, saline, environmental, and so on rebar, on bond, and so on, and we show that the material has really very good behavior. Also about bars under stress, looking to the stress, but we found when FRP bars or any reinforcement, when we are applying stress as specifying in the design code, like about service load, there is at all no effect. From our studies, we saw that the stress level is affecting and inducing micro cracks in the FRP reinforcement, FRP reinforcement, when the load is higher than 60-65% of the ultimate tensile stress. Here also during the last few years, we developed a new testing setup for creep rupture. You know, creep rupture is one of the issue and the problem that we have with this kind of fragile material, elastic material, and we have criteria for the design. So we developed a new kind of fixtures, and we are using them extensively, of course. Coming back to accelerating aging test, as I say, everyone I think know that we need 3 temperature and 4 period of immersion. This kind of typical result that we can go to with the tensile strength as function of the time and temperature. As you can see here, as the temperature is increasing, you have more degradation because you have more diffusion and so on. This equation are being used. Also, it's very, very well known. So we can derive this kind of graphs, you know, the one on the plot of property retention as function of the time on the left. And we have the Arrhenius plot for service life as function of temperature and percent retention on the right. And then we can derive this kind of curve and we can predict. But as I can tell you, this is only giving the potential of this material. It doesn't mean that in the field you will have similar behavior. In general, in the field, the degradation is less severe than what we did in the lab. But at least it gives a very good idea. And this is, we prove it from the field durability testing that we did here in Canada during the last 20 years using samples from bridges reinforced with FRP. So, but it gives very good idea about the potential of the material. Coming back to the creep rupture, as you say, most of the codes are specifying low value for creep rupture. So like SCI is specifying only 20% of the design strength, which is really very low. And we can have in some application that this will be the criteria driving the design. So we did extensive testing on creep rupture, including rebar from different countries, including Germany, China, Australia, Canada, Switzerland, United States, different sizes, more than 350 tests. And this is the mode of failure. after chiropractor. And as you can see here, the data that we collected from the study, and we recommended to the ACI and also to ASHTO. Now they increased the chiropractor strength from 20 to 30%. So we increased it by 50%, and due to this testing, and we still have some margin, as you know, even by, I'm sure, by going to 40% of the guaranteed of the design strength, we still on the safe side, as we recommended here, and it was implemented in the code. And this is the paper that it was recently published in ACE, Journal of Composite for Construction. Another study also that we completed recently is also regarding the design and what's called by the environmental reduction factor. This is taking into account for the long-term behavior, and we have to include it. This is mainly it's being included in the strength, for the calculation of the strength, because we have to affect it to the guaranteed tensile strength. This is also, we did extensive testing, and also we collected data from the literature, so about more than 350 testing. As you can see here, the C sub E in ACI, it's only 0.7 when it's in contact with Earth, you know, which is also, it's very, very low value, and it's affecting also the design. So we developed a new model. This is really its new model that we developed, which include not only the mean annual temperature, but they include the variation of the temperature over the years, and also relative humidity, as explained on this slide, with the C sub E and the TSF, the time shift factor. And we did the testing, and we used the available data, and we come out now with, we recommended to the new ACI from 0.7 to 0.85, which is also, it's still conservative even with this value at 95% of confidence. This is the paper that we recently also published, and strongly I recommend you to have a look to that. So I will conclude for the next 2-3 slides. So what to do for ensuring durable FRP reinforcement? This here are the list of key points. Use high performance resin systems, and this is being really done by most of the FRP manufacturers using suitable resin. Use of fully curved system. If you are using product without having at least 90, 95, 96, 97% of curve ratio, and having TG higher than 100, 110 Celsius, I think the problem could happen in the field. Minimize the formation of porosity. This is also the manufacturer knows how to do that. Low moisture absorption. Sizing, this is mainly for the basalt, and don't recommend any reinforcement if it was not qualified, certified by any specification standard in any country. You have them in China, there is in Europe, they are in Canada, they are in the United States, and so on, in Australia, and it should be used. Concluding remark, corrosion resistance, of course, is without doubt the main motive and attraction of using FRP, because I am convinced that we can resolve the problem of degradation of reinforced concrete structures. Mode of degradation of FRP rebar are very, very, very well understood, and we have a lot of data available. Test method and requirement for assessing FRP bar with high quality have been proposed, and I recommend to the researcher and engineers to use them. And application of FRP bar in different civil infrastructure has been proved to be very successful. As I say, we have some application dated, they have almost 25 years without any sign of degradation in the field. And of course use FRP making durable structures. Some research avenues is really looking to the synergistic combined effects, as I say before, it could be very interesting. Looking to development of new accelerated testing protocol. Field monitoring, this will be very good. Inspection and evaluation guidelines for the long-term performance without coring. So it will be like without taking a course or something like that. And developing, looking, and collecting samples from in-field. This is mainly to correlate, calibrate them with the lab testing. I have a couple, as you may know, during the last 20 years, I organized many international conferences on durability of FRP reinforcement. I have really proceeding available for free, 2017 to 2019, 72 and 98. If someone would like to have a copy, please contact me and let me know. And finally, I would like to invite you, I will be organizing this year the third international workshop on GFRP bars for concrete structures. It will be online, and I am organizing that with my colleagues Tony Nani from University of Miami and Steve Nolan from Florida Duty as co-chair with me. It will be on next August, 3 to 4 August. And it will be just before the 8th International Conference on Advanced Composite Material in Bridges and Structures. This is also will be online, and it will be from 5 to 7. And this is, I am organizing that in collaboration with the Canadian Society for Civil Engineering. Thank you so much for your attention, and really I enjoyed to give you this presentation. Thank you so much.
Excellent. Thank you very much, Brahim, for the excellent presentation. We have time for a couple of questions in the audience.
May I ask a question?
Yeah, of course. Yeah.
This is Chris Leung from HKUST. Thank you very much, Professor Bemokrin. It's an excellent presentation. I learned a lot from it. You mentioned a good news to us, indicating that actually in the field, the GFRP rebars are performing better than in the lab. Is there any physical reason for that? Can you elaborate a little bit?
The reason for that is, of course, the environment is not really the same because most of the tests in the lab are really in direct contact with the alkaline solution, you know, which is not the case in the and also, of course, with high elevated temperature. But in the field, it's there in the concrete. The relative humidity in concrete, depending, it varies between, 65, 70 to sometimes when it's wet, of course, it can go to 100%. But the testing is not the same, and the condition in the field is not the same. So, of course, if we will perform tests in the lab and considering the field conditions, I think we will not see any degradation, and we will not see any loss in strength or something like that. So it's really the main reason. It's not really the same conditioning, of course. Yeah, not the same environment. Yeah. But as I say, in the lab, we don't have choice. We have to go with the accelerating aging test. At least we know about the potential of this material and how it's being degraded and so on. And of course, then by implementing it in the field and doing comparison, so it gives really very, very good idea about how this material is will last, of course, in the field. Yeah.
Thank you very much.
Thank you,
Professor. I have a question.
Yes, go ahead. Yeah.
Professor, I have a question regarding the laboratory aging results. When you plot the laboratory aging results on the logarithmic scale with on y-axis, you plot the tensile strength retention for different temperatures. For example, for 20, 40, for 30, the slope of the line according to the time shift factor, that will be same.
Yeah, it should be. Yeah, it should be parallel. Yeah, it should be really parallel. If it's not parallel, it means that there was not only one degradation mechanism. Maybe there was a second degradation mechanism happening during the conditioning. So, but if you have, in general, from my experience, if really you have only one degradation mechanism, which is related only to the elevated temperature, as started, of course, in Arrhenius, you will results, they will be parallel. And from this, you can generate long-term data. But if they are not parallel, of course, from my point of view, you cannot use them.
Another professor, another question that in your recent publication regarding the environmental reduction factor, you haven't used the sustained loading, and then you are recommended the environmental reduction factor of 0.85. So what can be the reason for that?
Yeah, this is also, it's very, very good point. Because the reason for that is, as you know, in terms of design, and this is in any code, you know, I'm talking, of course, internationally, Chinese code, US code, Canada, European, you know, the stress in the GFRP rebar under service load, you know, it's really very, very low, because most of the design of concrete members reinforced with FRP reinforcement, in particular GFRP bars, is really controlled by the crack width, okay? And the crack width, because we have to limit it to 0.5 or 2.7 millimeter, depending on the application. So this is bringing really the stress on the reinforcement very, very low. We are talking about 2,000, 2,500 microstrain. And believe me that the stress level will not affect at all when you are loading. Even you can see some of my papers that I published in ACI Structural Journal, I think 20 or 15 years ago. Even I did bars under 4,000 and even up to 6,000 with this, which is really 3 times the allowable stress level under service load when designing, and you will see there were not any effect. Of course, if you load the material as higher load, as I say before, above 60-65% of the ultimate tensile strength, this is, of course, you will see some degradation, and of course the environmental factor will be affected. You are right, yeah. But,
Professor,
but the design is really very low. Yeah, the stress applied is really very, very low. Yeah.
Professor, thank you for this. Thank you for whole discussion. I think I'm taking the time. Only one thing. I'm following your papers from the very beginning when you were working with the robot, and then in 2000.
I think it's because of time. We need to control the time.
Okay, thank you.
Okay.
Bring him afterwards.
I'm doctoral student in Shanghai, Jaitong. I will be contacting you via email.
Yeah, it's with pleasure, of course. Yeah, with pleasure.
Now,
thank you so much. Thank you so much.
All those in the panels, show your camera, show your face, so we can take a group photo.
Okay.
Seconds. Everybody can show your camera.
Make sure we are handsome. Huh?
Yeah, you are handsome.
Can you do it? I was having my glasses. I don't like my. Can I?
Okay, that's good. So, Bodong, have you got it? Hello, Bodong. Is that good enough?
It's done. It's fine. It's okay.
Good.
Yeah. Yes, it should be good. Thank you.
Okay. Okay. Thank you very much. Let's move on. Thank you very much, Ibrahim, again.
Thank you.
Excellent talk. Okay.
Thank you.
Thank you.
Okay, so our next speaker is Professor Jihua from Shenzhen University. He is my neighbor. Okay, so he is going to talk about this protection and structural strengthening, those things. And I'm not going to into detail to spend the time. So I'm going to leave it for Jihua to talk about his topic. Okay, Professor Zhu.
Okay, thank you. Good morning. Can you hear me?
Yeah.
Hello? Okay. Good morning. I would like to thank Professor Yutao to invite me to give this presentation, and also I would like to thank Professor Chen for his warm introduction. So the topic of my presentation is development of synthesized intervention method of reinforced concrete structure using carbon fiber reinforced composites, and I name it SCP-SS. Oops. Okay. So this presentation actually summarizes my main research work covering more than 10 years. And I will introduce some of my previous work on existing structures. And then I will introduce one of my major work on seawater and the seaside reinforced concrete. So the background is well known that the corrosion of steel rebar due to chloride is the most important problem for the durability of reinforced concrete structures. And there are many methods have been developed to improve the durability. And generally, the electrochemical methods, such as cathodic protection, can prevent steel corrosion. And the structural strengthening, which is more familiar for civil engineers, can improve the mechanical behavior of degraded structures. But however, structural strengthening cannot fundamentally prevent steel corrosion. So therefore, we may need repeated strengthening for the degraded structure through the service life, as shown in this curve. On the other hand, cathodic protection also has a drawback. It's not able to recover the mechanical properties caused by the steel corrosion in the early age. So therefore, it sounds like such a natural idea to combine cathodic protection and the structural strengthening to achieve the synthesized intervention of both steel corrosion and the mechanical behavior. So the research actually started from 2010, more than 10 years ago, based on my first normal project from Natural Science Foundation of China. The topic was on aluminum and concrete composite structures. So although the project was mainly on structural behavior, but I noticed that the aluminum alloy is more active than steel, and is commonly used as anode materials for sacrificial anode cathodic protection. And therefore, I designed this kind of aluminum extruded closed section, which is looks similar as the near surface mounted FRP. However, the results was not so exciting since the potential between the potential difference between aluminum and steel is insufficient to drive the system due to the high resistance of concrete. So then, how about the carbon fiber composite material, such as CFRP? The material has been well investigated and applied in structural strengthening. And since carbon fiber is conductive, then the idea came out that the carbon fiber composites may be also used as anode material at the same time. However, the potential of carbon is much higher than steel. It means galvanic corrosion occurs when the two are in direct contact, where steel is sacrificed, and this is totally opposite as the aluminum case. So I think another electrochemical solution, which is so-called improvised current cathodic protection, SSCP, may be used. This picture shows the structure and the working mechanism of SSCP. And then the direct power supply is used to drive the harmful anions transport to the external anode. And then the corrosion of the cathode, which is the steel rebar, can be prevented. And with the monitoring system, the information of the rebar can be obtained, and then the applied current density can be modified to realize the effective protection. The traditional anode material of SSCP include different forms of like titanium, MMO, mixed metal oxide, and so on. So generally speaking, SSCP has been well developed, and there are many international standards available. But the high cost of anode material prevents this technique from widely applications, especially in China. So then take a look of the structural strengthening and the SSAP, and then the layouts actually look similar. They both use an additional material normally arranged at the outer surface of reinforced concrete to achieve the additional designed functions. So therefore, the synthesized intervention of concrete SSCP-SS was proposed, where carbon fiber material works as both anode and strengthening material. So moreover, this technique reduces the cost of anode material and the full service life maintenance cost. And also it may provide a new composite structure for seawater reinforced concrete. But however, although this idea is clear, it should be noted that the anode material always suffer degradation. And this anodic degradation is much more serious than the corrosion in normal conditions. And therefore, firstly, we need to investigate the dual function behavior of carbon fiber reinforced composites. The research was the anodic polarization was firstly conducted on FRP. Then the tensor behavior was obtained. It shows stable feeding voltage. However, the tensor strength of FRP decreased with the increased applied charge density. And then you can see here are different kinds of electrolytes. They also influence the degradation of the material. The tensor failure mode shows degradation of epoxy resin and the debonding between carbon fiber and the matrix. The degradation actually starts from the interface with electrolyte and extending along the cyclic direction. And this is just the same as the corrosion of steel rebars. But it's very interesting, as you can see from the curve. The tensor strength of FRP after polarization increase with the chloride concentration. And when 3% chloride was used, the residual tensor strength is around 90%, which is, of course, very good. So therefore, this result indicates the chloride has positive effect of tensor behavior of FRP after polarization. So to further investigate this mechanism, here we investigated one single fiber. And from this curve, from the current time curve, we can observe the gradual increase of current densities due to the increase of electrochemical activity of carbon fibers. Then the current density decreased sharply, step by step, which means the degradation of carbon fiber occurs. But on the other hand, the whole charge loaded on the fiber in a solution with chloride is almost 6 times more than fibers without chloride. So from the video, we can observe that without chloride, the whole fiber was decomposed seriously, where with chloride, the fiber seems intact, except for partial decomposition due to the initial imperfection. So these results demonstrate that carbon fibers has a very stable anodic durability in the environment of chloride. With SEM, we can see the initial carbon is smooth, but after polarization, the carbon fibers in the solution without chloride was seriously damaged. However, in the solution with chloride, the carbon fiber remained intact. And from the ES, we can also see that the impedance of carbon fiber decreased slowly at first and then increased sharply with the process of polarization. This result is consistent with the above conclusion that carbon fibers are activated first before the degradation. And besides, the carbon fibers with chloride showed a lower impedance and the diffusion control performance at the lower frequency, which means the fiber has a higher activity. So this result also demonstrates that the chloride can prevent the anodic degradation of carbon fibers and at the same time enhance the activity of the surface. So based on these conclusions, there are 2 novel applications can be proposed. On the one hand, to combine with the acceptable residual mechanical properties, carbon fiber material can be used in SSC, and the long-term performance can be benefited from the high chloride concentration, such as seawater and sea sun. And on the other hand, by optimizing the current density and the electrolyte, the byproduct of anodic reactions can increase decomposition of resin of CFRP to achieve the efficient and non-destructive recycling of carbon fibers. And of course, the recycled carbon fiber can be further used in civil engineering to reduce the material cost and achieve the closed-loop application of carbon fiber material. So now I will introduce the development of SSC. So although the dual function of carbon fiber material has been proved, it's necessary to carefully design the careful SSC system. And there are some fundamental problems to be discussed. So let's consider a simple reinforced concrete cross-section. The external carbon fiber works as anode, and the internal steel rebars works as cathode. Clearly, the charge loaded anode and cathode through the service life are always equal. Therefore, based on the basic definitions, we can see that the anode current density can be calculated by this equation. So therefore, increase the anode area leads to smaller anode current density and relief anodic degradation. This is the most efficient and directed way to increase the service life of SSCP system. So in the design, we must try our best to achieve the largest anode area. And this is also the reason why the SSCP anode is normally arranged at the outer surface of reinforced concrete. And for a given cross-section, the cathode area is related to the reinforcement ratio, and the cathode current density is determined by the corrosion of steel. Then the maximum value is given by the SSCP standard. So based on this model and the test results of polarization of CFRP, it can be easily calculated that with a 2 millimeter thick CFRP, the annual service life is more than 40 years with the maximum cathode current density and the maximum reinforcement ratio. This calculation is totally following basic principles and can be used for any other cross-sections. And this calculation also indicates the annual service life always increase with CFRP thickness. This is consistent with the failure mode observed in the test. That's the degradation of CFRP starting from the interface with the electrolyte and extending along the cyclic direction, just the same as the corrosion of steel rebar. But of course, the thickness cannot increase without a limitation, since there is another familiar problem to us, which is the selection of bond matrix. So typically, there are two kinds of bond matrix, organic matrix such as epoxy resin, and then the inorganic matrix such as cementitious material. The bond matrix in SSCP is not only to transfer stress, but also provide a phase boundary of cathodic protection. So it must be conductive and very durable. Epoxy resin is not conductive, but some researchers try to use conductive powders into resin to achieve this kind of conductive resin. However, the mechanism of epoxy resin and the cementitious matrix in this case are totally different. The electro reaction is actually the process of charge transfer between the electron carrier and the ion carrier at the interface. But epoxy resin doesn't provide ion. Therefore, even with the conductive resin, the reaction occurs at the interface between epoxy resin and the concrete. So considering the durability of epoxy resin is not so good originally, but the anodic degradation makes the service life even shorter. This is why previous research use conductive epoxy resin, but they cannot achieve long-term performance. On the other hand, cementitious material provides iron. Therefore, in this case, carbon fiber is a rare primary anode, and then the matrix is in the secondary anode. This makes the anode area even large, and then the system is even more durable. Selection of carbon fiber composites is also a key problem. Our first try was a carbon fiber FRP plate and profile. It provides large anode area. However, the resistance is very high due to the high resin content. So please pay attention here. Here we are talking about the resistance along the thickness direction, not the longitudinal direction. So therefore, we must remove the surface resin to make it conductive. Clearly, this can be done in research in our lab, but not practical. Our second try was a carbon fiber sheet. The resin content is low, and the conductivity is also good. But the bond behavior with organic matrix is not acceptable. The third choice is carbon fiber bar. I understand that many researchers in this workshop are working on FRP bars. But here I have to say the bar is maybe also the choice in this application. Firstly, with the given amount of carbon fibers, which means material cost, the bar provides minimum anode area. And secondly, the resin content of bar is as high as FRP plate. And thirdly, the connection is a big problem. But one single bar doesn't provide anode network. So, but even if bars are connected like a cage, and please bear in mind, the anodic degradation is much serious than the corrosion in normal conditions. But the connection is also a part of anode, and also suffer this kind of degradation. So, and moreover, bars must be used inside the concrete. And once the connections are damaged, it's very difficult to replace. So finally, we use the dry fiber carbon fiber mesh as the primary anode and the cementitious material with chipped carbon fiber as secondary anode to build up this carbon fiber reinforced cementitious material, which is so-called CFRCM. And this design provides the largest anode area, original electrical conductivity, and low cost. But is this the perfect material? I don't think so. Since the impregnation of carbon fiber with cementitious matrix is not perfect. But perhaps with the development of new materials, we will have an even better design in the future. So based on the above considerations, the SSC SS system was developed. And as you can see, the steel corrosion was successfully prevented, as shown here. And then the same specimen without SSCP had a very serious degradation. This has been proved in many of our tests. And the bond behaviors were investigated with single shear, double shear, and the pull-off test. And then the specimens are with designed CFSM showed stable interface behaviors. And then intensive analysis was made on the degradation to investigate the degradation of CFSM. But for the time this, I will not go to the detail here. And then the results demonstrate the conductivity of a chipped carbon fiber in the matrix can slow down the degradation of the primary anode, which is the mesh. And after the material research, the mechanical properties of CFSM was also investigated because the hydration product of cement is too large. The dry fiber cannot completely penetrate by the matrix. And therefore, the fiber bundle is divided into an outer layer and an inner layer, as shown in this model. Now, our test results show the different failure mode and the different bond lengths. With the smaller bond lengths, the failure mode is fiber slippage, and with the longer bond lengths, the combined failure of rupture and slippage occurs. But this interface behavior is too difficult to be obtained by test. So therefore, an analytical solution was developed to obtain the bond behavior from the simple pull-out test curve. This work was conducted by Dr. Zhu Miaochang, who was the co-supervised PhD student of Professor Wei-Da Tamong and me. So later, Professor Wei-Da will introduce the details in the next presentation. And after that, a lot of work have been done on the member behavior of SSCP-SS, mainly in static and fatigue loading conditions. And another team member, Dr. Feng Wang from Harbin Institute of Technology, will present the work on continuous beam this afternoon. Okay, this is a brief introduction of SSCP-SS for the existing structure, and now I will quickly introduce my work on recycling of carbon fibers. As we all know, carbon fiber material is widely used in many industries, but in civil engineering, the consumption is actually less than 5% due to the high cost. Therefore, the development of carbon fiber recycling can not only solve the environmental problem, but also provide affordable carbon fiber resource for the application of civil engineering. So based on the previous research and the mechanism of analytic degradation of carbon fiber with chloride, we developed a green and non-destructive recycling solution, which can recover intact carbon fiber of full length, as shown in here. And the solution is totally under normal temperature and pressure, and can be used for both the organic and inorganic matrix. The quality of the recycled carbon fiber has been extensively studied. The tensile strength of recycled carbon fiber can reach more than 19% of the virgin fiber, and then the interfacial shear strength can be increased to 120%. Compared with the other carbon fiber recycling methods, our method has clearly advantages in terms of equipment investment, recovery effect, and economy values. Okay, so above my previous research, and now I'm going to introduce more of my current work for seawater seaside reinforced concrete structures. So the background is that actually I come from Shenzhen University. Shenzhen city belongs to Guangdong province and is closely nearby Hong Kong. As the most developed area of China, the demand of construction sand is around 1.6 billion tons per year. This is almost the 6 times of river sand available, and these data are given by the government. And considering the abundant ocean resources, the government is plan to use seawater seaside concrete in the coming future. So therefore, in 2019, I was granted the project entitled for key technologies of SSCP-SS composite structures for seawater seaside reinforced concrete. So based on the technique which was originally developed for existing reinforced structures, the main concept of this project is to further apply SSCP-SS for new constructions of seawater seaside concrete. And we are using ordinary steel reinforcement. Therefore, those well-developed technologies of reinforced concrete structures and composite structures, including design, fabrication, construction, can be keeping used. And this is very important to promote a new material. This project is from 2020 to 2025 with a total budget of 44.5 million RMB, where 5 million from government and the others from industry. And we are honored to have 6 partners from the top universities and leading companies. The project contains 5 work packages. And then the first one is the application for technology for seawater seaside concrete. And work package 2 and 3 are related to the behavior of SSCP interface and members. Package 4 is for the high performance of the SSCP-SS structure members. And then the last package is about the quality control and the practical demonstration. So I will briefly introduce mainly about the work we done in 2020, especially for work package 1 and 4. So although with SSCP-SS, some requirement can be released, such as chloride concentration, but it is still necessary to provide the index of the raw material of seawater and sea sand. And therefore, we built a database of seawater, sea sand of Guangdong province. And the raw material index will be proposed according to the practical data and the practical experience. And more data will be and this database will be eventually open to public.
Could you finish in a couple minutes?
Okay, I'll finish very soon. Okay, and we designed the concrete mix from say 20 to 18, and right now, next month, this year we will cast a large volume sea sand seawater concrete in factory. And here we did some work in numerical simulation, but adjusted the law. And Professor Dai Jianguo and Professor Zhao Weijian, they are working on high performance. Professor Dai proposed the high performance coating and high performance ECC for the permanent framework. And Professor Zhao is proposed the prefabrication scheme for composite beam and the steps. So here is my conclusion. This material, carbon fiber material, can be used, shows very stable dual function behavior, and it can be used for anode and strengthening. And based on this mechanism, SSC technique has been developed for the provide synthesizer intervention. And with the optimized conditions, the green recycling of carbon fibers can be used. And SSC is also considered as a new type of composite structures for seawater, sea sand, concrete. My presentation is quite a lot due to time reason, but there are many references available, including books, many papers, patents, and theses. Here shows the projects we obtained in the past years, and the financial support are appreciated. And there are many researchers joined the team. And I don't speak the name now. And my special thanks gave to Professor Xing Feng, Professor Han Ningxu, and Professor Tan Luping. This work cannot be done without their supervision and support. And here are my lovely students. Thank you.
Okay, thank you very much, Professor Tu. Because of time, I allow one question from audience, from panel. Is there any burning question? Okay, if there are no burning question at the moment, I think I'll leave you to talk offline, okay? So you can talk, contact Professor offline. He's at Shenzhen University. So I would like to move on to next speaker. That's Professor Tamon Ueda. Tamon is now also at Shenzhen University. So he moved to Shenzhen University 18 months ago, I think. Okay, so I think most of us know Professor Ueda very well. He has been one of the pioneers in working in research in this FRP strengthening and other structures. He has been active in many associations, and he is currently an advisory committee member of the IFC, and he's the president of the Asian Concrete Federation, and so on. I would like to leave the time for Professor Ueda to talk about his progress. Okay, come on. We cannot hear you, come on.
Just Can you hear me?
Yeah.
Okay. And also you can see my screen?
Yeah.
Okay. Oops, just a moment. All right, so my slide is appearing in appropriate way, I suppose. Okay, as the Professor Zhu introduced, my presentation is part of this big project, ICCPSS. And I'm involved in this project about 3 years ago as the joint supervisor at Hokkaido University. And since then, yes, I have started this collaboration with the Shenzhen University, Professor Xingfeng and Professor Zhu. Then, since my background is the structural intervention with the external bonded FRP and cementitious material overlay, so my responsibility in this project, ICCPSS, is, as this title, my presentation title indicate, mechanical behavior of the strengthening material for the ICCPSS. Just a moment. Then this is my content of this morning talk. Yeah, in fact, now my content is the FRCM as the multifunctional material for the synthesize the structural intervention, which is ICCPSS. Then I talk briefly about the multifunctional material. Then as a strengthening material, we have to discuss on the tension behavior and the bond behavior. But at the same time, Professor Zhu introduced earlier, we have some mechanical degradation due to the IC, the impressed electrical current. So, and also through the various studies on the this FRCM and other ICCPSS material, we can see some future direction on the optimizing FRCM. This is a similar slide as the Professor Zhu earlier showed. Once again, I try to explain. Multifunctional material, I believe this is a new concept, and or in other words, multifunctional interventions. Yeah, intervention is usually meant for the particular function, like corrosion protection or structural strengthening. But this multifunctional or synthesized intervention is we can provide more than one function. In this ICCPSS case, we use the same material, which is the, in this case, CFRCM, as a structural strengthening material, at the same time, cathodic protection material. Then to have this ICCPSS system work properly, we have other issues, such as the not only the good strengthening material, but also we have to provide a good bonding property so that the multifunctional material, which is the CFRCM, work together with perfectly with the substrate concrete. Then, yeah, this is today I talk about this material. Yes, carbon FRCM, fiber reinforced cementitious composite. Then in this case, we use the cement-based mortar with containing short carbon fiber, which we believe enhancing the electrical conductivity. And we use the dry fiber mesh or carbon fabric mesh. The reason was already explained by Professor Zhu earlier. Then we put this CFRCM on the tension phase of the existing concrete member, as you can see here. Then we are expecting some structural strengthening capability with this CFRCM. Then we start to have the investigating the tension behavior of this carbon FRCM. Then, of course, as a typical way, we prepare the coupon specimen for the actual tension test. Then several parameters can be seen here in this slide. We provide the different amounts of the carbon fiber mesh, starting from 1 layer, 2 layers, 4 layers. This is one of the main parameters. Then this is typical experimental result. As we can expect intention behavior, we can this CFRCM material, coupon shows the multiple crack, but one of the crack is becoming dominating and showing the bigger crack width, which is mainly due to the fabric slippage. And in fact, this fabric slippage is the key mechanical behavior as a tension material of this fabric. So as similar to the typical other FRCM, we have this tension stress, tension strain behavior. Before cracking, we have the very high stiffness, but after the cracking, it shows the strain hardening behavior. Then to have this CFRCM as the tension material, we propose some convenient method or concept, which is apparent strain of the carbon fiber mesh in CFRCM, which utilize this nonlinear stress-strain relationship. Then to have this apparent strain of the carbon fiber mesh, you can know the more precisely what is the tension contribution of the CFRCM. Then this is a comparison between 1 layer of the carbon fiber mesh and 2 layer and 4 layer. Among them, yeah, we cannot see much difference, but seems to me within our experimental result, 2 layer case shows this somehow better performance. Then we also conducted the fatigue test. This is a result of the fatigue test, and naturally during the cyclic loading, the accumulated deformation is increasing, so showing reduction of the effective stiffness of the carbon fiber FRCM. Then this is this is the experimental result, and from the starting, the continuously stiffness, effective stiffness is decreasing, approaching to the stiffness of the dry fiber mesh. Then this is a comparison of the other material, steel rebar. Our carbon CFRCM SN diagram shows the better fatigue strength. Of course, it's original, the carbon fiber strength is higher than steel, so it could be natural. Then this is showing our experimental result of the CFRCM. But from this comparison, our CFRCM, the fatigue strength is weaker than the CFRP fatigue strength. Then as a next step, we also investigated the tension behavior of CFRCM in beam as a strengthening layer. And this shows the specimen we tested. And again, our experimental parameter is number of the carbon fiber mesh. The carbon tension behavior, which was observed in the tension coupon test, was clearly applicable to estimate the tension contribution of the CFRC in beam. So that appearance strain of the carbon fiber mesh can be applied to estimate the tension contribution of CFRCM in the beam. Then using apparent strain concept together with the ordinary bending theory, you can calculate estimate the load and midspan deflection. So with using the appearance strain concept, we can have the good prediction of the member behavior. And also we conducted the fatigue test of the strengthened beam. Then this is the experimental parameters, number of the CF layers, and also we changed the maximum load level. Then this is a result of the fatigue behavior of the beam with the CFRCM. And experimental result shows clearly the increase of the fatigue life under the different level of the maximum load. And because of the strengthen, yes, the fatigue number of fatigue life increases, but nevertheless, the fatigue failure mode is all the same. Tension fracture, fatigue fracture of the steel bar in the substrate concrete beam. And this is an experimental result of our steel reinforcing bar fatigue life. Then we move to the effect of the impulse current on the tension behavior and the bond behavior of the CFRCM coupon. Then this is the experimental setup to have the impulse current. So we have the different level of the current density. Then this is the result of the tension behavior of the CFRCM tension coupon. Then naturally, we can see some degradation effect. Especially ultimate tensile strength becomes smaller and smaller as the current density is increasing. But somehow, if you look at the stress-strain relationship or appearance strain, showing some more ductile nature after influence of the impulse current, which means you might have the more progressive slippage. That is another difference in the as an effect of the impulse current. And to have the better prediction of the appearance strain under the effect of the impulse current, we propose another empirical formulation of the appearance strain. Then we have the tension fatigue behavior under the effect of the impulse current. And this is experimental result. And as the fatigue test shows, at the more cycles, then the stiffness getting smaller and smaller gradually, And this is a comparison under the different impulse current. As we predicted, the higher charge density, we have less stiffness during the fatigue loading. So to consider this effect, so this is an empirical formula to represent the effect of the current density on the appearance strain. This is the tension fatigue behavior of CFR-CM coupon and the impulse current. Then at the tension strength, fatigue strength is decreasing as impulse current increases, as you can see here. But even the maximum impulse current case, we still have similar fatigue strength as the steel rebar. And this is also showing another effect of the impulse current on the endurance limit stress range. So the endurance limit stress limit range becomes much smaller under the strong electrical current. Then we also have tension behavior in the beam. So we have this similar exposure test under the anodic polarization. Then we take a tension coupon, then a tension plate, and this is external bonded to the substrate concrete beam. Then this is a result of the low midspan deflection. We don't see much effect, but our appearance strain model can predict nicely on the load midspan deflection behavior. But somehow, if you look at carefully, this blue line, this is under the effect of the impulse current. It shows quite a good deformability, even could be slightly better deformability. Again, this is more greater fiber slippage induced by the impulse current. Then this is tension fatigue behavior of CFR-CM in beam and impulse current. Then, of course, once we have the strengthening by CFR-CM, we have the increase of fatigue life. But eventually, all the beam shows the same failure mode, which is induced by the steel bar fracture. So this is a experimentally obtained SN curve of the steel rebar SN curve. So due to the higher fatigue strength of the CFR-CM in tension compared with the steel bar, the failure mode becomes the failure mode is still steel reinforcement fatigue fracture. Then I come to the bond behavior of the CFR-CM, and we started investigate the bond behavior of the yarn, carbon yarn of the carbon fiber mesh. Then this is experimental specimens, and we took the single carbon yarn and embedded it in this matrix. Then this is a testing parameters, and we have the pool of tension test. Then as the experimental result, we came up with model, the bond model of the slippage to represent slippage between yarn and the surrounding cementitious matrix. And this is our model concept. And our basis is this trilinear bond stress slip model. Then having this trilinear bond stress slip model, we can make a comparison of the different specimens with different material compositions. And this is a result of the each bond stress slip relationship, so that we can see effect of the material composition on bond property. Then having this bond model, we can calculate the ultimate pull-out strength. Then ultimate pull-out strength cannot be greater than the tension capacity of yarn. To achieve tension capacity of yarn, we can know the necessary anchorage length. So this is a calculation result by model. And also we have the bond behavior experimentation of CF mesh itself. Then this is a testing specimens. This is a carbon fabric, and this is a CFRCM specimen. And this is a testing parameter. We change the embedded length. Then this is another test result of the carbon fabric bond behavior, as a carbon fabric bond behavior. Then, as Professor Zhu mentioned earlier, we observed the this kind of the partial tension fracture of the dry fiber mesh. So to explain partial fracture, we have the idea of the outer part and the inner part of the yarn, each yarn. Then to have the bond behavior, we have to assume outer interface and inner interface. Then this is a similar model concept as a bond behavior of the yarn. We assume for outer interface, we assume the trilinear bond stress and slip relationship. And the inner interface, of course, we cannot have the direct experimental evidence, but we simply assume, this simple something like a slippage, linear slippage model. Then, with comparison experimental result, we can come up with the we can identify each model parameters for these trilinear models and single linear models. Then having the, after conforming each parameters, we can have the parametric study for the key parameters. And this is the effect of the beta M. Beta M is the size of the outer core. And beta T is the reduced strength of the outer core. Reduced strength of tension carbon fiber is due to the partial impregnation of the matrix. So we cannot have the full tension capacity. So considering reduction of fiber tension strength and also considering the partial impregnation, we can have this two inner core and outer core model to predict the bond behavior. Then bond behavior CF mesh in the under impressed current is here. So we change the current density, as you can see here, and also we change the anodic polarization duration, as you can see here. And this is a CF mesh bond behavior test. Then this is the result of the bond behavior and the different electrical current density. So as we predict greater electric current density, of course, bond behavior is deteriorated, meaning peak bond stress becomes smaller, but you can say ductility cannot be reduced much. Even better, could be better. Then having the extended bond model to represent the effect of the electric impulse current, we come up with this model for the outer part and the inner part. We have the different effect on the charge density. Otherwise, to explain the experimental result. Then this is showing the how bond model showing the degradation induced by the electrical current. This is the outer interface bond model, and this is the inner interface bond model. Having assumption of those the degradation, we can have the good prediction of the experimental result under the impulse current. Then, as a summary of our study on the mechanical behavior, tension behavior, and the bond behavior, what we learn is listed here. FRCM with a short carbon fiber and a carbon fiber mesh can show good bonding property, in fact, without the debonding. And the degradation of the CFRCM and IC reduce the tension strength, as I showed you earlier, but slippage of fiber mesh provide a ductile behavior in tension. And the degradation of the CFRCM and the IC enhances the ductile behavior in tension. Then this FRCM ductility, which we observe in FRCM, even which is enhanced under the IC, member deformability under flexural and axial tension. Yeah, supposing if we don't have any tension fracture of the CFRCM. And also, member ultimate axial load and deformability under compression if we use the CFRCM as a confining material. But to have the better optimization, we have to consider those points. Efficiency of utilizing fiber strength. We still have the better solution, we believe, to have the better matrix impregnation and to have the bias way by having some better material combination. We can have a better bond at the matrix fiber interface. And also we can utilize purposely slippage of the fiber. So bond at the matrix and fiber interface can be optimized. And the moderate effect of the impulse current on tensile strength. We can still have the quite a big degradation, so we believe we can have some way to improve the mitigate the IC effect. And lastly, we haven't observed the debonding phenomena, but we have to clarify what is a bond property of at the matrix fiber interface and the substrate matrix interface. Otherwise, we cannot have the ultimate rational design model. I think this is end of my presentation. Thank you very much.
Thank you very much, Timon, for the very interesting presentation. Is there any burning question from the panel or the audience?
Professor Ueda.
Yes.
Yeah, thank you for a very nice presentation. I just have a simple question.
Yes.
So in your bond test, you have a single fiber yarn embedded in the matrix. And however, in the real structure, your mesh will have multiple fiber yarn, which may not be loaded uniformly in a real structure. So how do you consider this in determining the anchorage length for the concepts? Could you
okay. Probably I have to explain more. This bond behavior of the yarn it's not, our purpose is not to understand the bond behavior of the CFRCM in the beam. Instead, we try to identify what is the best material composition of the cementitious matrix so that we can have the better bond behavior. That is our intention. So our next study this one, the bond behavior of the dry carbon fiber mesh. I believe this test result is showing the real tension behavior of the CFRCM in the member. Am I answer to your question?
Yeah, okay, thank you. Thank you very much.
Okay, because of time, I think we are going to move on. Thank you again, Timon, for the very interesting presentation. There is a question from audience for you to answer. You can do this afterwards, okay?
Okay, thank you.
And so we will move on to the next presentation. It will be given by Professor Dai, Jianguo Dai from Hong Kong Polytechnic University. Professor Dai has been very, very active in researching FRP and many other things like cementitious materials. So I'm going to leave it for Professor Dai to talk about he's going to talk about high-strength seawater, sea sand, engineered cementitious composites, ECC. Okay, so Professor Dai, over to you.
Thank you very much, Jianfei, for your introduction. So I don't know why I cannot see the shared screen. Can you see my presentation?
I can see your presentation, but it's not.
Now it's okay, right? Okay, thank you. Yeah, thank you. Good morning, everybody. Thanks for this opportunity to introduce our recent work on seawater, sea sand, engineering cementitious material. In fact, today's work was conducted by Dr. Huang Botao, who is a postdoctoral fellow at PolyU, and Dr. Yu Jing originally was a postdoctoral fellow at Hong Kong UST, and now become associate professor at Sim Yat-sen University in mainland China. So this work is under co-supervision of myself and Professor Christoph Liang, and also in collaboration with Professor Victor Li. As you know, both Professor Liang and Professor Li are pioneer scholars in the field of ECC material. So today my presentation will include, first I will give you a very brief introduction, and then talk about our recent development of seawater, sea sand, ECC, and I will briefly describe, the major, mechanical performance of SSC, seawater, sea sand, ECC we have achieved in our experiment, and finally, we will describe, how to using this statistical method to describe this, correct distribution performance so that we can facilitate the actual, serviceability design. So I think needless to say, marine structure, infrastructure become more and more important for our human being. As you know, almost 60% of the being, are focused, live nearby the, coastal area. I think usually it's 100 kilometers, far away from the coastal area. So the durability and how to build a better, living environment, near the coast area become more and more important for our human being. Of course, as you know, those marine infrastructure, they are exposed to very severe service environment like chloride attack. And also they have various types of mechanical loading like fatigue, impact, and so on. So this is actually, at this moment, of course, mostly widely used structure type steel reinforced concrete structure. But as you see here, reinforced concrete structure, when they exposed to marine environment, they may subject to significant deterioration. I think many of you are familiar with this progressive, evolution of the structure performance of a typical reinforced concrete structure exposed to marine environment. Originally, you don't have anything happen, but once the chloride penetrating into a reinforced concrete structure, then, once your chloride contents concentration at the steel reinforcement surface reaches threshold value, then you may have, this concrete cracking, and then eventually you have spoiling of a concrete cover, causing, loss of your serviceability, of course, as well as your safety. This is how the structure performance, propagate with time. Of course, to tackle this issue, of course, maintenance is a very important issue, so-called life cycle maintenance issue. And we have different approaches to tackle this deterioration of reinforced concrete structure at the different stages. For example, at the earliest stage, we can using surface treatment method, okay? And the later stage, we may using this, sectional enlargement as well as FRP strengthening. In fact, I spent, many years in this area as well. And we also can using cathodic protection, as Professor Zhu Jihua and Professor Ueda just mentioned. We can using sacrificed anode system. Also, we can using imprint current system. Of course, we still can using realkalization and desalination system. So, of course, to facilitate implementation of this technology, new material development is very important. So we really need experts, know both well, know both material and structure well, so that we can choose most appropriate material and understand their underlying structure mechanics and then perform actual, design. So this is in fact my research group. I think in the past decades, we have spent our efforts, in developing those new material. And of course, the first area is we further develop, our strengths in the area of FRP and also FRP reinforced cementitious matrix. It's kind of tension stiffening material, different from linear brittle FRP material. And also we develop surface coating material, try to, perform the preventive maintenance. And we're using, develop geopolymer composites, both acid activate or alkali activate, to facilitate, for example, for drainage pipeline. Okay, we can using this geopolymer material to achieve a better, life cycle performance. Of course, another issue, is high performance fiber reinforced cementitious material, which is today's talk. So if we look at, this fiber reinforced cementitious material, I think basically in the past 2 decades, we have 2 major development. I think the first is, engineering cementitious composites. Of course, the theory to support this material development was back to, 1992, which is a technical paper published in Journal of Engineering Mechanics by Professor Li and Professor Liang. So basically, if you look at this cementitious composites, so we have plain cement, mortar concrete, and we have fiber reinforced cementitious composite. So during my master study, in fact, I studied my work on fiber reinforced cementitious composites. But at that moment, both test equipment and theory was in fact quite a little bit left behind. At that moment, even difficult for us to obtain the whole range, tensile stress strain curve. Okay, so at that moment, basically, our fiber reinforced cementitious material is a softening material. It's a tension softening material. Means after cracking, the tensile stress drops significantly. Okay, I think later on then we have this high performance, ductile fiber reinforced cementitious material. And under this catalog, if we cite, JCI, Japan Concrete Institute's definition in 2002, so they divide this high performance FRCC to 2 categories. One is deflection hardening material. If you carry out a bending test for your material, then you can get this hardening property. But pay attention, this deflection hardening property is not equivalent to tension, hardening property. Of course, the other category is so-called ECC, okay, engineering cementitious materials. Some other people also call it the high performance, okay, FRCC. So if we carry out a direct tensile test, we can achieve this tension hardening behavior. Of course, if you have tension hardening behavior, obviously if you can achieve deflection hardening behavior, but vice versa is not correct, okay? So the second category is UHPC, ultra high performance concrete. I think yesterday Professor Si Caijun, who is also a pioneer scholar in this field, this material was first used in 1994. In fact, it's based on this particle packing approach, how to compact your particle packing, make your concrete very dense through the composition of different size particle. Okay, and according to Federal Highway Administration, they define UHPC with material property as follows. You have a low cement water to cement material ratio. Usually it's below 0.25, and you should have some minimum discontinuous, usually it's steel reinforcement, okay, to achieve, some ductility. And usually compression strength should be higher than 150. Of course, some other people say 120 megapascal. Of course, this is in fact far beyond our normal range of the current code of practice. Taking Hong Kong code of practice as example, we just reach up to 70 megapascal. So we do need a new design method to facilitate the use of this material. And usually post-correcting tensile strength should be greater than 5 megapascal. Okay, so this is a typical mixed proportion of UHPC. You can see usually we're using cement, Portland cement, and we need using silica film and usually fine quartz powder. And superplasticity is very important. We have some additional steel fibers. So we realized in the recent 5 years, I think starting from the Renata in 2013, so research community try to push the envelope of material performance envelope of this ECC, okay? Means to try to combine the higher strength of UHPC and with higher ductility of ECC. Okay, so this is in fact we just submitted a paper to a journal. You can see this is our review. This is normal ECC. Usually, strength is below 80 something megapascal. But nowadays we gradually can push this performance envelope to 200 above 200 megapascal. Recently we just realized highest strength above 220 megapascal in the laboratory. While in the meantime, we still can achieve the tension strength hardening behavior. Okay, one example is one work we published in 2018. You can see the compressive strength we achieved is 120 megapascal. And in terms of tensile stress strain curve, the peak stress can reach up to 16 megapascal. And tensile strain can be beyond 8%. And we can get very uniformly distributed and saturated crack, okay, under even ultimate state. You can see this is a DIC imaging filter at the strain level of 7.2%. You still can get a very localized crack. And also, of course, it relies on very good bond between your fiber and the matrix. And also we need using very high strength fibers. Usually we're using so-called PE fibers. So of course, to realize this design, we need to pay attention quite a few issues. First, micromechanics, fiber pull-out behavior in the matrix, and also the fracture properties of matrix. Usually we perform such kind of test, use the notched beam under 3-point bending, and we also need to consider this statistical theory, how, you know, this distribution of your material property. I mean, you need to pay attention to the flaws of materials. So this is basically, I mean, underlying fundamental mechanics for this particular material. So another advantage to develop this ultra high strength, or I termed as ultra high performance ECC, UHP ECC, is it can be used in combination with fiber reinforced polymer material. As I mentioned, FRP is a linear material, while this material is very ductile material. If we combine both, we can achieve so-called tension stiffening material. And you can see once we're using FRP in combination with ECC material, we can avoid localized stress concentration in FRP. In fact, it affects both the mechanical efficiency as well as durability of FRP material. In fact, we have done many experiment tests and also seriatic analysis in this. This is beyond, you know, the scope of today's talk. So I think this is a basic background introduction. And then I just briefly introduce what we have done on seawater sea and concrete. Because once we try to using seawater sea sand to produce ECC, there is something different. So basically, we obtain, you know, this seawater sea sand. You know, we just using local material available in Hong Kong. You can see this is typical, you know, particle size distribution of size available in Hong Kong. And this is, I think many speakers, they talk about, you know, this gradient material, you know, composition of seawater already, and including a color, quite a lot of, you know, metal ion and also, you know, chloride, sulfate, and so on. Okay, this is fresh water. We also did some compressing tests between, you know, seawater and the fresh water. We get this natural seawater, and also we produce this artificial seawater by ourselves. So this is, we did two series of tests. One was for normal strength ECC. The other is for high strength ECC. And in both series, we compared the seawater and the fresh water. Okay, this is typical mixed proportion. We're using cement. You need using flash. Sometimes, you know, you also can using slag cement. Okay, and this is the seawater. This is sea sand, and we're using the fiber. We're using two types of fiber. PVA for normal strength ECC. Usually we're using PVA, but if you want to produce this high strength ECC, then you need using PE fiber. Okay. So this is basically a test result. First thing is in terms of workability. Of course, you know, setting time is a measure, is a very important parameter. So you can see basically this is the left side here is normal strength, you know, ECC. Right side is high strength ECC. As many speakers talked about already, I know. I mean, the setting time basically is reduced. I mean, is shortened. Okay, once you're using this seawater sea sand, because, you know, you have accelerated effect, you know, by these ions on the hydration of C3S. Okay, in Portland cement. And this is the tensile stress strength curve, you know, we obtained, you know, for normal strength ECC and high strength ECC. You can see tensile strength or normal strength ECC around 4.5. Of course, for this, you can reach up to, you know, 7 to 8 megapascals. Okay, so if you compare this two, I mean, the performance of fresh water and the seawater, I show you next slide. Okay. So this is show, you know, we compare the red one is seawater sea sand. This blue one is fresh water ECC. This is seawater sea sand ECC. You can see for normal strength ECC, we can get a slight increase, okay, due to the use of seawater sea sand. This is in terms of compressive strength. So second paragraph is show tensile strength. Okay, so no significant change, but in terms of tensile strength capacity for normal strength ECC, we get, you know, slightly declined tensile strength. So as I mentioned later on, it's mainly due to, you know, the particle distribution and also composition in seawater, sea sand. Sometimes we have some weak shears, okay, besides the sand. This is how the correct distribution looks like under the ultimate state. So left two figures is normal strength ECC, right figures is high strength ECC. You can see this is two figures in fact represent the same average tensile strength level. But if you look at locally, then your correct width and the correct spacing has some difference. Basically, we found in seawater, sea sand, concrete, correct spacing is slightly larger, means your correct width may become slightly larger. Okay. Of course, later on we were using mechanical model to statistical model to describe this distribution and to facilitate actual design. So this is basically after we understand the fundamental difference between seawater, sea sand, and freshwater ECC, and then we did some further investigation, parametric study. Okay, we changed just based on seawater, sea sand, ECC. Okay, and we forgot about we just ignored the normal freshwater ECC. So the major parameter we observed, one is the sand size. You can see there we have three typical different sand size, seawater, sea sand size. Okay, and also we choose different fiber volume. As you can see here is 1.0% and 1.5% in comparison with the 2.2%. And also we're using different fiber lengths. You can see we have 12, 6, and 18. Okay, as you can see here, this is how the different lengths of fiber look like in the left figures. And then we perform this direct tensile test. This is in fact the result. Okay, first figure is still compressive strength. You can see the fiber dosage. How the fiber dosage, different fiber contents influence the compressive strength. Okay, basically just once you increase the sand size, you get slightly a decrease of the compressive strength. So in case of tensile strength capacity, you can see similar trend. Of course, you have quite large scattering. It's because with increase of sand size, you can see slightly decline of the tensile mechanical performance. Of course, for other parameter, parametric effect like fiber dosage effect and the fiber length effect, this trend is exactly same. As what we observe for normal freshwater ECC, with increase of fiber dosage, you get the increase of strength capacity, and also with increase of fiber length, you get the increase of the tensile strength. But in terms of this is tensile strength in case of fiber dosage effect. Fiber length has relatively marginal effect on the tensile strength. So of course, to explain those kind of observations, we can perform micromechanics simulation. Basically, what you need to do is the first is a fiber pull-out test. As I mentioned in previous slide, you need to conduct this fiber pull-out test to evaluate the fiber bond performance, and also you need many other input regarding the fiber itself and the interface property, as you see here. And also you need to carry out fracture mechanics, fracture performance test for your matrix. And once you input all this material parameters and the mechanical performance parameters, then based on micromechanics model, you can predict this fiber bridging stress and the correct opening relationship under different parameters. Like if you have different fiber volumes, if you have different fiber lengths, basically you can predict this fiber bridging stress and together with correct opening property. And also you can predict the failure mode through some statistical analysis. As you see from the below figures, you can see lateral horizontal axis represents the average strength level, means your tensile strength during your test, and the vertical represents the percentage of the total fiber. You can see we have different failure mode. For example, you have debonding failure. You may have debonding together with pull out, and also you may have fracture of your FRP, your fibers. Bear in mind, so in your matrix, you know, some fiber fail in pull out, some fiber fail in rupture due to this statistical distribution characteristics. So in fact, we can using those models to predict this different failure mode under different strain level. This is, of course, we also can compare our prediction with, you know, microscopic, you know, observation. You can see actually, you know, in your SEM analysis, you can see, you know, fiber rupture, fiber pull out, and you can do, you know, statistical analysis and to find out, you know, what's the percentage of fiber with rupture, what's the percentage of fiber with pull out, or with a combination of both of them. Okay, so this one we did this micromechanics analysis, and also to assess this performance, you also can using so-called Seddon strain hardening index, representing, you know, the ratio. We have two. One is strength criteria, the other is energy criteria. Okay, so this we can using this PSH index to assess the performance of our seawater, C-sand, ECC, high strength seawater, C-sand, ECC, and also here shows the parametric effect, how the, you know, fiber volume and how the fiber length and how the sand size influence this Seddon strain hardening, you know, index in terms of strength and in terms of energy. Similarly, you can see the sand size has the minimum effect. Is osmomorphic, of course, as expected. You know, fiber volume ratio and fiber length has significant effect on this, you know, PSH index. And the final part, in fact, as I mentioned, once we have this experiment observation already, we also using micromechanics model to simulate our experiment finding, and eventually a very important issue, how to perform design. Since we usually say ECC has very good correct control, okay, usually is below 100 micrometer, then, you know, how to perform this kind of design, because actually at the different state you can see this correct width has a random distribution. So that's why we picked up this correct width, different spacements, okay, to carry out the distribution of tensile strength. Okay, this scattered line point means our experiment observation. Then we try to using this variable function to simulate this, you know, tensile strain distribution of our high strength ECC material. And we get this fitting, and also we get the relationship. As you can see here, we need some parameter, for example, K and lambda, okay, in this variable distribution. And we get the relationship between this variable distribution parameter and fiber material, our fiber parameter, like, you know, fiber volume and also fiber, you know, length. And then eventually we can get the, you know, so-called finalized equation. Based on regression of the experiment result, we can get the actual, you know, variable distribution function for correct width. Here just comparison between this, you know, formula and the experiment result. You can see with change of fiber dosage, how the mean value and the scattering, you know, property change with fiber dosage and with fiber length and with fiber size, sand size. You can see the scattering nature in case of, you know, sand size effect is not that significant. But for other two, not only you have change of mean value, your scattering, okay, your this property also change significantly. So finally, of course, we try to using this model to perform design. So we just select one typical curve. Well, usually we carry out several identical tests for each combination of parameters. So in such a case, we just choose, you know, one typical sample among three, you know, identical specimens. You can see the red one. And this is, we choose 5 strength level under this uniaxial tensile stress-strain relationship. We choose 5 typical strength level. For example, A is 0.2 represent, serviceability, and then, our E represent the ultimate state. Okay, we divide each curves to 5 stages. And this is just show under this correct width, different correct width. This is correct width distribution. This is vertical axis is cumulated distribution. This is the correct width. We can get this correct width distribution, this curve. Okay, and also we compared this our Weber distribution, and also usually use the log normal distribution. And this figure just summarizes the comparison result. So the red one represents, our Weber distribution function performance better than log normal distribution. This blue point means the log normal distribution performs better than Weber distribution. So eventually, we just believe, the Weber distribution curve we obtained, through the regression, they reflected this kind of statistical nature of this high strength seawater's ECC material. And we also, through this Weber distribution function, we can know the mean value, how the mean value change with different, parameter like sand size, like volume, this fiber volume and fiber length. And also we can show the standard variation of this Weber distribution, how this changes with our material parameters. And this is just to show, our finalized equation, theoretical one. You can see this is correct width. This is a probability density function. This is accumulated curve. And you can see how the mean value and how the standard variation changes with different material parameter. In the interest of time, I just pass those detailed information. And this is just show how this different material property influence the key performance, compressive strength, tensile strength, and the tensile capacity. And we propose using a 5 dimension, this chart to assess our mechanical performance of high strength seawater season and concrete. So first it is compressive strength and tensile strength, and also tensile strength capacity, means how ductile your material is. And we also using this mean value, mean crack width. We want to get the minimum mean crack width, so we're using this 1 over mean crack width, means the larger value the better performance. And the standard deviation, of course, if deviation is very small, then of course we think the performance is more stable. So we're using this 5 dimension to assess all the mixed proportion, and eventually we can obtain what's the best mixed proportion in terms of the optimal mechanical performance, which is shown here. For example, we're using a 12 millimeter length fiber with the volume ratio 2.0, and using sand 1 or sand 2. And once we, after we finish this assessment, once we have this Weber distribution parameter, of course we can compare. So this, our theoretical prediction and actual, experimental result in terms of mean value, in terms of scattering, And with this, and we do this, you can see our model, and this is the best fitting. In fact, our theoretical model based on regression can capture the experiment result very well. And based on this, you can see this is just show at different strength level according to our model, how the correct width distribute and how the scatter looks like at the different strength level.
Could you finish in a minute?
Yeah, sure. Yeah. This is just finally how we can using our Weber function for design. Basically, you can see our string can be relevant to the Weber function parameters. For example, if you look at the figures, left bottom figure, you can see the vertical axis is critical tensile strength, means how much strength we should achieve in our test. And this is the correct width. Correct width. For example, if you wanted, if you designed correct width is 100 μm with the confidence level of 99%, then you can see for this mixed proportion, for example, for S4, this blue one, at least in your material test, you should achieve above 1.5% ultimate strength, so that you can guarantee a minimum correct width of 100 μm with the confidence level of 99. As you can see from second figure, you can see for this green one, if we set this criteria, 100% with confidence of 99, in fact, you can see this green mixed proportion can never achieve our design target. Means it's not workable for this mixed proportion. But for other proportion, you can see this red one, you need achieve, around 3% ultimate tensile strength. Then you can guarantee you have a correct width, 100 μm with confidence of 99%. So you use this Weibull function, so we can design our wanted, material ultimate strength to satisfy the serviceability requirement. So I think this is all my talk to. I just leave this conclusion, for you to reading. So in fact, we publish a few papers in this area. So if you are interested, so you can read our paper for further details. So with that, thank you for your attention. Thank you, Jianfei.
Okay, thank you very much, Jianguo. Is there any burning question from the panel?
Yeah.
Otherwise, I would like to finish this session. We have.
I noticed that there was a question raised asked what is the stage of the compressive stress in the research?
What is failure in, sorry?
What is the age of the compressive stress?
What is age? 28 days.
Okay. This is not written to me, by others. I just...
okay, thank you, yeah.
Photo for you. And there was another question raised by another...
okay, Guangming, I think because of time, I would like you to talk to Professor Dai afterwards.
No. This is not raised by me, by others.
No, that's fine. I'm going to leave this for Professor Dai to talk about, to answer the questions after this, okay?
Okay, feel free to contact me.
Online.
Okay. Yeah, I see a few other questions in the chat window. So feel free to contact me by email.
No, Jianguo, there are questions for you in the question and answer button.
Yes.
Okay, so you can answer
besides the age, in fact, I have another question. I just wondering if you have conducted any fiber distribution and orientation analysis.
Jianguo, could you answer just right there? Okay, because we are 17 minutes delayed.
Sorry,
okay, so
I overrunning the time.
You overrun a few minutes. Okay,
I okay, sorry.
We started a couple minutes later. Okay, so I'd like to finish this session. I'd like to thank you all the 4 speakers for the excellent presentations. Okay, so and we don't need to clap here. So, close and so. Thank you very much. Okay, and I would like to finish this session and hand over this back to Yuta.
Okay, thank you very much, Professor Chen, for chairing the session, and thank you for all the 4 speakers for the very excellent presentations. So I think in the interest of time, we'll move directly to the next session, the second session of the morning. So may I invite Professor Zhang Sisun from Huazhong University of Science and Technology to chair this session. Professor Zhang, please.
Okay, can you hear me? Okay, yes. Dear professors, colleagues, and friends, welcome to the second session of the second day's workshop. As introduced by Tao, I'm Sisun Zhang, from Huazhong University of Science and Technology, Wuhan, China. So in this session, we will have 3 invited presentations to be given by Professor Jian Feicheng, Professor Gui Junxian, and Professor Yingwu Zhou, respectively. To save time, the first presentation will be given by Professor Jian Feicheng. Before his talk, please allow me to introduce him briefly. So I think most of you know Professor Chen very well. He is a very famous professor in the field of FRP competence in civil engineering, and he's also the previous president of IFC. And I have some materials with me, but I will just pick up important information for you. Professor Chen is currently a chair professor at the Department of Ocean Science and Engineering, Southern University of Science and Technology. I think he joined this university around 1.5 years ago, right, Professor Chen?
Yeah,
and,
that's right.
His research interests are very broad, including advanced construction materials and broad areas in structural engineering, and also research and application of advanced discrete element and finite element method, mechanics of unconsolidated material and particulate, solids, fluid, and stresses in silo and material handling. To date, Professor Chen has authored or co-authored over 300 publications. His work has been widely cited according to an elsewhere research conducted for academic ranking of world universities. He was one of the 150 most cited researchers worldwide in civil engineering in 2016. Today, his talk will be on behavior of CFRP wrap and CFRP tube confined C-sand seawater concrete columns. So, okay, Professor Chen, you can start. We are ready.
Okay, thank you very much, Sisuen. So I'm going to talk about this CFRP confined SSC columns, basically. So I'll go through a very brief background and then look at the source of the seawater and sea sand where we collected, and a little bit about the experimental design, and then look at some of the test results. So first of all, little background. I'm not going to read this, okay, because that's everybody knows. So basically, we are talking about that's Jingguang 10 proposed in TO11 that we could use sea sand and sea water to replace fresh river sand and fresh water. Okay, so that's basically we followed his idea and we applied for a little NSFC grant. So this what I present is part of that project. So what I'm going to talk about the key things that we are going to focus on today is the prolonged aging. Okay,
Excuse me, Professor Chen. I think your view model is not correct because we can see double slides on the screen.
Oh,
can you change?
No, I'm not sure how I change this. Let me see.
I think it's okay. The small window is just show what is the next slide.
Is this better now?
The same, doesn't matter. Doesn't matter. It's okay. It's not a big problem. Okay, now it's better.
No, yes.
It's okay now. Okay.
Okay, sorry. I think that's one of these different screen. One is for presenter, one is for the audience. Okay, so we'll look at the size effect of the little columns, and then look at the difference between wet layup and tube, CFRP tubes. For strengthening work, usually we have a column in place, and you wrap the column using FRP and to do the strengthening work. But if you construct a new structure, you have the FRP tube and fill the tube with concrete. So the two still have some differences, and that's what we tried to look at. Okay, so the sea water and sea sand were collected. We use natural sea sand and sea water, and that's collected from near Shenzhen, okay, in what's called the Damesa beach. So that's the map, the left top map, that's showing the bigger map. So it's along the coast. And then the left, the bottom map, that's showing the more closely this beach, and of course this top right map shows where it is actually is in a large map. So that's two pictures showing the how the sand and the water were collected from the beach. And that's the sand and the stones used. So we used the coarse aggregates, that's just the broken stones. And then we have the two types of sand, the river sand and the sea sand. Now the difference between the two, one is coarser and the sea sand is finer. Okay, so you can see the sizing curves are slightly different between the two sands. Okay, so for the experiment, I want to show you first that's something I talked about a couple of years ago. That we presented the four things. Okay, so we produce this natural, we produce normal concrete with the river sand and fresh water, and then we have sea sand concrete and seawater concrete, and then sea sand and seawater concrete. So the four different things for comparison. So just a very quick review of those results, and you can see the effect of the sea sand and seawater on the stress strength of confined concrete. The effect is quite small, and you can see the curves, they are almost the same. Okay, apart from very small differences in the early stages, the strength of seawater and sea sand concretes are slightly higher, and that's what we expect, and everybody knows. Okay, so there are some more curves here. So that's sea water and sea sand, and that's confined. Okay, so the previous picture, that's the unconfined concrete, and this screen shows the confined concrete. So again, you can see it's typical bilinear behavior of the stress strain curve, and you can see the early stage there are no differences, but in the second stage there are small differences again between the sea sand and seawater and the natural the fresh water and river sand. Okay, so but the effect is quite small. And here again, that's showing the axial deformation and the lateral deformation. So basically here, if you see the curvature, the slope, if the slope is larger, or you see these curves are going down steeper, then there's more dilation. Okay, so basically, if you have the confinement, if you have more confinement, then it reduces the volumetric strain or the expansion, so it enhances the strength of the concrete. So here, basically, there are no differences, very little differences between the types of concrete. The difference here mainly shows it's the different amount of confinement. The effect is different. If you have more confinement, then the volumetric ratio, strain is reduced. Okay. Now this shows the effect of the cooling age on the different things. On the first diagram here shows the effect on the strength. So basically, the strength, of course, increases with the aging. That's what we expect. But the thing is here, if you use seawater and sea sand, the effect is higher. And for the otherwise, the difference is quite small. Okay, so what I'm going to show is a new set of tests, and that we look at these different factors. Okay, first of all, I mentioned that we use different confinement method. The one is using RAP. So basically, we have the cylindrical specimens cast and cured first, and then wrapped with the FRP. And another one is we have the FRP tubes prefabricated and then cast concrete inside. Okay, and we have the specimen tested at 28 days, 9 months, and 2 years. And in this set of tests, we only look at the difference between sea sand and normal sand. Okay, so basically because of the fresh water, we use the fresh water, and in many occasions, you don't really need to use seawater. Okay, because if you cast, say, inland, that's you will not be short of the fresh water. And we look at the different sizes of the specimens. We keep the HOD, the height and diameter ratio at 2, and we have this diameter increase from 150 to 200 to 300 millimeters. Now that's this experimental work were all done at 80 was the time at the Guangdong University of Science and Technology, I think, and when Guangming Chen was still there, he supervised a few MSc students did the work. And he has now moved to Southern University of China. Okay, so it may be a bit confusing. My university called Southern University of Science and Technology. Guangming Chen's university called South University of China. Okay.
So let me make some correction. My university is called South University of Technology.
Okay, South University of Technology, whatever. Different from my university anyway. His university is very well established. My university
no, it's South new. China University of Technology, Guangming.
Yeah, okay, thank you, that's correct. Okay, so the student did some clever work to build this wooden mold for prefabricating the CFRP tubes, okay? And so you can take the wooden mold out easily once the CFRP wrap tube is produced. So that's here how they did the work. So they had this wooden mold and then put this on this framework and then have the CFRP wrapped around this wooden mold. And once it's dried, you can take the core of the wooden mold out first and then the rest. Okay, so here the picture on the right shows the prefabricated CFRP tubes. Okay, and then the other method is, of course, we use the wet re-up system, and that's everybody in this conference knows. Okay, so that's pictures showing how they were tested. So let's have a look at some of the results. First of the failure modes, and this sets just showing the S first S in the designation of the specimens. The S stands for small, and M stands for medium, and the large F stands for large. Okay, so large, that's 300 millimeters. Medium, that's 200 millimeters. Okay, so we can classify these failure modes according to STMC 3910. Okay, so well, you will not see really much difference in this failure modes unless we do a lot more tests to have some statistical meaning. The number here, it's not large enough to have the statistical confidence to see any differences, I think. Apart from that, you can see in the largest specimens, there are type D failure. That's the shear failure of the specimens. And that does not appear in the small specimens and the medium-sized specimens. Okay. So that's the only difference, I think. So these pictures show the FRP wrapped specimens. Now here you have this SW, S for small, W for wrapping. Okay, so that's the FRP, CFP sheet were wrapped around the cylinder. And here again, all this, you can see the failures whereby FRP rupturing, whether they are small, medium, or large, there are little differences. Okay, and here you can see, sorry, I'm going back. Okay, here see the locations of the rupture. Now this, of course, when you wrap the FRP around the cylinder, even the tubes will produce. That's because produced using the wrapping of the FRP around the molds. So we still have the overwrapping zone in this in the FRP. Okay, so there are two ends basically. If we look at the first diagram here, so at this area we have stress concentrations, and this area we have stress concentrations because of the geometrical discontinuity. I have a couple of papers on these things, okay, and if you are interested, you can read on this. So basically, this records all the location of the FRP rupture where they started. Okay, so like this, the first one at the left top corner, that's the failure was at what we call the inner end of the FRP, and the second one that's the same, and this the third one that's filled out of the wrapping zone, and the fourth one here it's at the inner end, and the fifth one again that's near the inner end, and the sixth one that's again near the inner end. Okay, so but if you look at this, I suppose you can see my cursor, am I right? The mouse cursor.
Yes.
Okay,
yes,
so you can see some of this field at the outer end of the FRP. Okay, so that's if you do the analysis, FE analysis, you can actually find the stress concentration is much severe at the outer end of the FRP. Okay, so you do see a lot of failure at this area. So overall, you can see there are about 60% of the failure, they occur at either the outer end or near the inner end of the FRP. Okay, so, and that's probably because of the stress concentration at these two locations. Of course, there are many other factors like the aggregates, the distribution of the aggregates can affect the stress distribution in FRP, and that you can lead to stress concentrations in other places. And that's probably why we see their failures in other places. Okay, now let's look at the stress-strain response of the cylinders. The first picture here, that's showing the small size specimens, and they were tested at different ages. Okay, at the 7 day, that's the what's called the Oxford blue. That's tested at 7 days, and then the pink one that was tested at 28 days. So basically, 7 day. That's unreinforced. Okay, not strength, not wrapped. So you can see the 7 day strength is just a bit lower than 28 days. But if you have that cured to 9 months and 24 months, the strength increased quite significantly. But the difference between 9 months and 24 months, that's very small. Okay, so but that's slightly different in the medium-sized concrete specimens, and here the phenomenon is still there, but the increase between 28 days and 9 months or 24 months, that's not significant. Not as significant as a small size specimen. Now that's something I cannot explain. Okay, so I think that's some not really because of the size, but some random factors here. Okay. Anyway, the large size specimen shows a very similar phenomenon. One thing is interesting is that as the strength develops, the descending branch becomes much steeper. Okay, so that means the concrete becomes much more brittle as the strength develops. Now that's something we understand, and all concrete, high strength concrete is much more brittle than the lower strength concrete. Okay, now these are the confined concrete. Now here you can see the in the middle, in the specimen destination, you can see C1 and C2, okay? So C1 basically, that's wrapped with one layer, and C2 wrapped with 2 layers or more. Okay, something like this. So here you can see these are typical bilinear behavior of this confined concrete. And here, if we look at one of these diagrams in more detail, so let's say take this 150, this diagram A here, that's a 150 millimeter cylinder. Okay, and that's with just one layer of the FRP. And these 2 curves here at the bottom, that's the T curve 1 with that's dashed line that's tested at 28 days, but it is tube. Okay, so the tube 1, and then this Oxford blue, I think it's called, and that's slightly higher. That's everything else is the same, but it is with FRP wrapping. So if you look at the next set, that the circle one here, that's the black circle one, that's cast with tube, concrete cast in tube, okay, and that's cured to 9 months. And then this green one, that's the same, everything else is the same, but it's wrapped, okay. And then we have the square ones, again, we have the red one, that's cured to 24 months, and it is tube, and the purple square, it is cured to 24 months with FRP wraps. So basically here, what you can see is the wrapped specimens always slightly higher than the, or stiffer, slightly stiffer in the second branch than the cast in tubes. Okay, now I think that's probably because of the shrinkage of the concrete. Because if you cast in the tube, the concrete as it cured, it shrinks a little bit, okay? But for those wrapped specimens, because the concrete specimens were cast and cured first, and they were wrapped near the time when they were tested, so there is no shrinkage problem. So probably in the tubes there is very small gap between the concrete and the tube. But in the wrapped specimens, there's not such a problem. Now that's a very similar phenomenon for the rest, for the other pictures. Right, now this pictures here showing the dilational behavior of the specimens. So here we then not anything really systematic, apart from showing that the behavior is quite similar between all the different specimens, okay? And they are scatters, but the differences are not systematic, so we cannot really draw any firm conclusion from this. And this picture showing the effect of the age on the strength. Now, basically, that's something we expected. For the unconfined concrete, the strength of the concrete increases with the age. Okay, so that's not really something strange. And in diagram B, we still have the similar phenomenon. That's for the tube. Okay, it's concrete in tube. It's the increase is quite. The trend is quite clear, but for in the diagram C, that's not so clear cut, and you can see the 9-month specimens. I think here the 9-month specimens showing higher strength than 24 months for some of the specimens. I think that's something not really systematic behavior. That's probably something due to the specimen scatter, I think. Okay, so, but I think overall, there's still the trend that the strength increases very slightly as the concrete ages. Okay, so here is the effect on the strain at the peak stress, the ultimate strength. Okay, so the strain here now, how do you say it? That's for the unconfined concrete. I think we should not read much in this diagram because for unconfined concrete, the strain measurement is not really reliable at the when the specimen is filling. Okay, because you have cracks. So there are lots of scatters here, and that's something we expect. But for the FRP confined concrete, that's more clear, and you can see for those confined with the tubes, here again, we have I think overall we can say more or less that the strain reduces as the time increases. But somehow this 9 months specimens, they still show some bit strange behavior. But for the specimens wrapped with FRP, that's much more clear. That's the strain at the ultimate strength reduces as the age increases. And now that's also because what we have looked at because the strength increases. Okay? The strength increases, so the strain will reduce a bit here. Right. Okay, so here we have the hope strain. Again, now that's not something really that clear. Okay, so, but the diagram on the left, you can see there, basically we can see there is some very small trend that's going down as the time increases. But on the right, the diagram shows a bit more clear trend here. That's the hope strain also reduces with the age. Now this diagram shows the Young's modulus, okay, the effect of the age on Young's modulus. Now here you can see the Young's modulus increases a bit. That's increases from here, it's something like 26.5 to when it's 24 months, that's something around 29.5, something like this, okay? So that's not very significant, but there is a trend of increasing a little bit. Now this picture showing the size effect of the specimens. Again, the 90 days, I think, shows something interesting behavior that's not really that clear. Okay, so, but basically that there is, I think from the top diagram, you can see there is an overall trend that's the strength reduces a little bit when the specimen increases in size. Okay, now that's not that clear and not that significant, but the trend is there. And then the lower left diagram, that's showing the axial strain at the ultimate limit state. Okay, so that's the trend is clear for most of specimens, apart from this green solid line. Otherwise, that's there is a trend that it reduces a little bit for the increase of the specimen size. Okay, and for this again, for this the hope strain in the FRP, that's again, that's it looks like for majority there is a trend there. Okay, the increase of the size, the strain reduces a bit, but they are large scatter here again. Okay, so I think I have spent enough time. So basically, of course, FRP confinement is effective for sea sand or seawater and sea sand, seawater concrete. Okay, now the effectiveness compared with normal sand, I think the results are not there. It was this conclusion was drawn from the previous results that the effectiveness reduced slightly compared with the river sand. And there are small differences in terms of strength and strain in the CFP rock, whether it's wrapped or it's tube confined. Okay, so this two method will have slight difference. So that that indicates that for new construction and for strengthening, there will be small differences. And then we have the size effect. That's there is a bit there, but it's small. Okay, I cannot draw strong conclusions here, but apart from there is a bit there. Okay, and as the cooling age increases, the modulus will increase a little bit, and the strength will increase, and that's we expect, and the strain capacity will reduce as the strength increases. Okay, now that's probably something important as the strain capacity reduces. In design, there are some implications. Okay, thank you very much. That's all from me.
Okay, thanks, Professor Chen, for the interesting presentation. In view of time, we can allow one or two quick questions. Any question from the panel or the other audiences?
Yes, can I have one question?
Yes, please.
Thank you for interesting presentation, Then, my question is related to one of your conclusion. Third dot, some difference FRP hoop, wrap case and the tube case.
Yeah.
Relating to this conclusion, in case of wrap, you have the overlap regions. Yes. What's your opinion? How do you consider overlapping portion in terms of stiffness?
Okay, Taman, for the tubes used in this set of tests, they were also overlapping zone. So that's so that's not different between the two sets of.
Okay, I misunderstood. But how do you consider overlapping portion in terms of the confinement stiffness? Yes.
Now, the overlap portion. So if it's small size specimens, the overlap portion could be very significant because you have a large part of the circumference that's one more layer. Okay, but for large specimens, that's our overlapping zone could be much smaller. But in any case, the overlapping produce two positions. That two positions have the geometrical discontinuities, and that's something we cannot avoid. And based on what I have done before, that can reduces the strength by 60%, something in that order. Okay, not 60%, reduced to 60%. So reduced by 40%, all because of the strain concentration at the geometrical discontinuity.
Yeah, but that is strength in terms of strength, ultimate point. But to achieve before the ultimate point, the stiffness of the tube or wrap is important to see the confined concrete behavior. During that stage, overlapping part stiffness may have some effect. Then if it is, how do you consider? That is my question.
Yeah, okay, now this, I don't think, in terms of the actual stiffness, okay, I don't think that the overlapping zone has any significant effect because in this case, the fibers are all circumferential. So we don't have axial direction fibers. And the axial in this case, the axial direction, the stiffness of the FRP in the axial direction is very...
No, I don't mean the axial direction stiffness. Hoop tension, we have the stiffness is important, I believe. So that's why overlap part increase overall the stiffness of the confinement. Then there should be some effect. This is my question.
Oh, okay. Now you're talking about the confinement effect.
Yes, confinement effect.
Okay, okay. Now the confinement stiffness, I think that it is obvious that we just mentioned a minute ago that the confinement, the overlapping zone, if it's large, then you increase the confinement stiffness within that zone. Okay, but out of that zone, there is no increase. So in that case, whether you have a large overzone or small, the effect on the strength and the stiffness is questionable. I don't think there should be any significant effect because it is the weakest link that controls. Okay, so in this case, we have, if the concrete is uniform, homogeneous, then we will have the two ends of the FRP wrap that controls. And if you want to calculate the wrapping stiffness, the confinement stiffness, it is outside of the wrapping zone that controls. I think that the extra layer within the wrapping zone, you can measure strain that's reduced, but in terms of the confinement, I don't think it should affect the effectiveness.
Okay, thank you very much.
Okay, thank you, Professor Ueda and Professor Chen for the in-depth discussion. So in view of time, because we have already been around 50 minutes behind the original program, so we need to stop here and move on to the next one. And hopefully, Professor Guijin and Professor Yingwu Zhou, it would be great if you can finish your presentation within 25 minutes because we are already late, and to allow enough time for lunch and moon break. So please keep on time. Okay, so the next presentation will be given by Professor Guijin Xian. And before his talk, please allow me to introduce Professor Xian briefly. Professor Xian is working in the School of Civil Engineering at the Harbin Institute of Technology Science, 2009. From 2005 to 2009, he worked in the Technology University of Kaiserslautern, Germany, and the University of California at San Diego. His research is focused on high-performance FRPs and their applications in civil engineering. Professor Xian has published more than 150 papers and contributed to 8 standards or codes related to FRP in civil engineering. And today his talk, as you can see from the screen, it's a new fiber reinforced polymer composites for construction. Okay, Professor Xian, you can start.
Thank you very much, Susan. Could you see my
yes.
PPT? Okay, thank you very much. And thank you very much for everyone, and especially for the committee of the conference to provide this opportunity. Today, my presentation will focus on new fiber reinforced polymer composites. And Susan, I will make sure I will finish as you required, 25 minutes or 20 minutes.
Thanks.
Finish as soon as possible. And firstly, I will give the background. As everybody knows, we have the problems. We do not have impacted success in new structures with the FRP materials. And so in recent years, I focus on this direction and see what can I do on this, especially for the bridge, the cables and bars. And as I thought, because not massive applications of FRP in new structures, so we have limited advancements of new high-performance FRP in construction. For example, FRP bars. By now, 85% of the bars belong to GFRP, and the left belong to the CFRP of basalt FRP. 2015 global values only 0.59 billion. It's not too much. Of course, it's have a very high ratio, increased ratio. As expected, 2024, the global value will reach 1.25 billion. It's high, and we look through this. For my part, I believe applications of FRP in some new structures will accelerate the application of the new FRP materials, also new technologies of the FRP in construction. This, I think everybody knows this. Just finished the last year by Professor Yue Qingrui in Sanyang with carbon fiber tendons. It's excellent. And with this application, we have a lot of ideas for the new materials and new technologies, especially for the not only for the anchorage, also for the installation and so on. And from this point, we our group also involved in the projects in the last year on the bridge. We work on the cables and pre-stressed tendons. When we really involved in the project, real projects, we will find there's a very high performance required for the FRP materials. For example, fatigue, durability, impact resistance, fire resistance, creep, and so on. There's a lot.
And from those experiments, from my point, it's very important to study the properties of FRP comprehensively, and not only and some tensile understanding the property tensile properties. And it's also very necessary to develop new materials. And for current commonly used FRP materials, we can see from this slide. For the resin, we mainly use epoxy, 1 etre. The most is epoxy. For the 1 etre, we use for the bars. Fiber reinforcements, carbon, glass fibers, and of course we have another choice. There's a lot of choice, not only basalt fiber, aramid fiber, and others. All the products also we have bars, rows, profiles, cables, plate, pipe, and so on. We use the most commonly processing technology, the protrusion. Besides this, widening hand layout. So when we think about the new FRP materials, we must based on those commonly used materials and technologies. So our study is to, in this presentation, is to develop new FRP materials and goals and or criteria to develop new FRPs. Due to our experience for the bridge application, the first is toughness, and the second is durability, and the third is cost effective. And we have a lot of choice to do this. For example, for the toughness, we can choose the resin matrix and or thermoplastics, and also some fiber hybrid. It's a very effective way we can use. For durability, we must think about not only focus on the epoxy or 1 etre. We still think about there's a lot of choice for the stable chemical structure materials, hydrophobic resin systems, and thermoplastic. Of course, for the durability, fiber hybrid is also another way. Cost effective, especially at the moment, big two carbon fibers will reduce the price. It's very effectively. And also we think about the quick manufacturing techniques and also fiber hybrid. We replace some expensive carbon fiber will be a good way. And some examples for the fiber hybrid. There's a lot of work on those, and I think this is very intriguing for done by University of Alberta, Canada, 2015. They developed new kinds of hybrid bars. This is the protrusion. This is the core side is the carbon, and the outside is braided aramid fibers. So we have this pseudo ductility. It's very intriguing, but unfortunately, this is only done in the laboratory. And also this done by our group. We use the polyurethane. I think there is some. Okay. Yeah, these are very intuitive materials, very intuitive. This exhibit very high ductility of the resin matrix and very high, excellent durability properties. Of course, it's just like the hybrid bar we just mentioned. It's just done in the laboratory. There's a lot of work need to do for the real application of this kind of new materials. And thermoplastic matrix is very intriguing, and not only in construction, also in aerospace and other industrial field, because thermoplastic, the molecules is not pure liquid. It's kind of a linear or some branches. The advantage is tough. It's very tough. Generally, we use, for example, polypropylene is hydrophobic. And if we use of produce the materials, this bendable. Of course, we must face the difficulty. The most important difficulty is the manufacture. Manufacture is very difficult for thermoplastics due to high melt viscosity. And also there are some laboratory products. This done in 2000. I'm not sure why this done published in 2013. This kind of bendable bars. The property, the test in the laboratory is perfect. Unfortunately, it's not. It's just a laboratory. So our research aims, this done by in the last year or 7 months. We want to develop new FRP with the fiber hybrid thermoplastics and for high performance required by engineering structure applications. Frankly, we have not too much, but we will show you what we have advanced. We go. The first one, carbon glass fiber hybrid composites. First, we produce kind of hybrid rod. The diameter is 22 millimeters. The fiber volume fraction is 17%. We fix the fiber hybrid ratio of fiber, glass, and carbon. Carbon to glass is 2 to 3, and we have two kinds of mode. The first one, the glass and the carbon, is relatively uniformly distributed rod. The other one is the shell and core structures. And we do the test for the static test, the shear test, and the tensile test. And we also do the fatigue test. And for the shear properties of the hybrid rod, and we will see, we have a lot of try, but we only show this 2 and 4. This is the typical hybrid composites. We will see if there's core shell structures. We will see the debonding between the core and the shell. This is the most important failure mechanisms, not only for the static properties. And this the structure 2, we will see the crack in the middle and the debonding on the shell and the core. And we do the tensile properties. This is the structure 2, uniformly distributed. This is the shell and the core. We will see the hybrid does not affect the tensile properties. The modulus, the strength are almost the same. And the field mode, we will see from the digital image correlation photos, we will see the mechanisms is not correct, not the same. From this, the first one, we will see the breakage. This is just before fracture of the sample. We will see this some breakage of carbon fibers. And for this, we can conclude the debonding between the shell and the core. The most intriguing results is fatigue performance. These two kind of rows, we will see the fatigue life is much, much different. At the same stretch levels for 43% and 41.7%. For the uniformly distributed hybrid rod, has much, much longer fatigue life. It's almost 5.6 times longer than the core shell structures. And why this happens, we can analyze, we can see for this distributed, uniformly distributed rod, the stress and the strain almost the same. The stress is distributed to the glass and the carbon will take the most force. And as we know, carbon fiber has a much, much high fatigue properties. So this we can use the properties of carbon fibers. But for those the layers, the debonding will happen after some cycles of fatigue. So this means the glass fibers will take the much higher force compared to this one, the first one. So this means the pictures for the mode. So the fatigue field, it comes from the debonding, the shell and the core for this one. And for those, because of the carbon fiber and the glass almost the field at the same time. So we use all the fiber properties. So we have a much higher fatigue performance. We also can get the modular degradation. We'll see the damage inside. We will see for the second one, there's a very noticeable damage during the fatigue life. Please keep in mind, the cycles is much less than this one. And we also do the hybrid plates with a wide immersion. Because we use wide immersion, we can have a more hybrid mode. I will not give more details about this. And we do the tensile. We did not do the fatigue for those plates. We get the tensile properties, and we will see for the modulus, it's follow the raw meter very well, but for the tensile strength, does not, especially with the high fiber content, carbon fiber content. It's it's much far from this line. And we can understand that there is some damage of the fibers. And glass fiber is long elongation, high elongation, but carbon fiber, lower elongation will fail earlier. So there is an optimum balance between them. So for those, I will not give more details, and with summary, glass and carbon fiber hybrid can bring a new type of FRP with high cost effectiveness and some desired properties. For example, we have a longer elongation. And the design in fiber content hybrid mode and manufacture routing is required for the positive hybrid effect. We did not talk about the positive hybrid effect just in this section because we use so high carbon fiber content. We did not reach this. Okay. The next is a fiber reinforced thermoplastic composition. That started in this machine. We did not do the bars. We do the prepregs because we have a problem with the mode, and we believe we use the prepreg is more effective to understand the properties. We started the glass fiber reinforced polypropylene composite prepreg tips. And why we choose this, we want to have the GFPP, glass fiber reinforced polypropylene tension bars. We also want to have reach the bendable straps. We choose PP because it's very cheap. It's comparable to, it's very simple, and you will see it's any other, besides of carbon and hydrogen, there's no any other atoms. This means this material is very hydrophobic and also very durable materials. There's no hydrolysis or no the properties we made with the epoxy materials. It's the epoxy monomer. Generally, PP will not absorb any waters. And we got the prepregs. The tensile strength is around 524 because we have a lower fiber content. It's just the beginning. We will increase. And we also do the tensile tighting perpendicular to fiber directions. We want to understand the bonding between fiber and the resin systems. And we do the durability. While we use this, we have two properties: one, toughness and durability. We use the water and the saline and the alkaline. This for the marine applications. We use the temperature 25 and 60 degrees C. And we see the water uptake. It's frankly is out of my expectation. And for those one, it's a high temperature 60 degrees C. Saline alkaline solution is take a lot of water. This means there's something wrong, there's something damaged. And for others, it's okay. It's comparable to the epoxy. It's around 1% or less than 1% at lower temperatures. And for that, we did not do a lot of data. We will see the tensile properties. This is the original. This is the 35-day, 31. I'm not really sure why this is 2 days. It's around. It's 1 month, 2 months, and 3 months. For the low temperature water, it's not much degradation, but if we use high alkaline, we have big problems, degradation for those materials. Used by 94.8 for this 60 degrees C, and this undesired. And for the bonding, it's better than those. It's better than the tensile strength. And the worst one is only reduced, not only, it's reduced by 80%. Why this happens? Frankly, we understand that this is the good things and the bad things. Polypropylene is there's no function or active atoms. This means there's bonding between the polypropylene and the glass fiber is very, very poor. So this is why we have the problems. All those things, the solvent will go along the fibers inside the tape. So that the glass fiber cannot resist this alkaline. So we see the very noticeable cracks happens on the glass fibers. So this is why this happens. We have the much reduced this because of the glass is damaged. It's damaged completely. And so for those study, we will see glass and PP polypropylene products. So impact low saline alkaline resistance. It's due to the poor fiber adhesion. So if we use those, we must think about the appropriate glass fiber sizing, suitable fit with the thermoplastic. All polypropylene must be modified to have the good bonding between the glass fibers. So it's not easy as we thought. So I give a very simple conclusions. The first one for fiber hybrid is a very feasible way to get a new FRP with the desired properties, and also very cost-effective. Hybrid design is needed. It should be carefully studied and to reach optimum positive hybrid effects. This is a balance, properties, cost-effective. And thermoplastics, FRP brings a high potential for advanced engineering structure applications. However, there is still a big gap from the practical applications. And we also found a lot of study from Canada and the United States. And they just do some work in the lab, but did not really use. Okay, thank you very much. I think I save some time.
Yes, thank you, Professor Shen, for the interesting and clear presentation. And you used 23 minutes. Thank you. So we still have time for a couple of questions. So any question?
Okay, may I have questions, Sushan? Yeah.
Yes, please.
Guijing, thank you for a very nice presentation. I think I have one comment and another question. So first comment, I think a hybrid is a very good idea because usually for high strength FRP, we cannot utilize fully its high capacity, usually due to, you know, the stiffness requirement and so on. And also it's linear materials, and we need a very safe, you know, large, you know, partial safety factor, means cost effectiveness is not good. So I think once you have this hybrid, it will influence our eventually design concept. If we can, I think this is a way. This is my comments. Yeah. Second is you talk about the thermoplastic, since this become very hot issues. So do you know what's the progress in the automobile industry for utilizing this, you know, thermoplastic FRP material? Because we think this recyclability become much better.
Yeah, for recycle is for thermoplastic, it's very easy for recycle. They can directly use them to make some reuse. And the problem for us, we want to have a durable properties, and we also want to have the cost effective. And for other industry, especially aerospace, they do not use the polypropylene, they will use the PEEK. And frankly, that's, they do not face this problem we meet, and because they use completely different materials.
So it means thermoplastic material used in other industry cannot be, I mean, we cannot take them as possible in the application.
The first very popular use in aerospace, they use PEEK. Exactly PEEK, and we cannot use them. The PEEK is much more expensive compared to carbon fiber, but the property is perfect. They also in the automobile industry they use polypropylene, but the properties they required is much lower compared to us.
Okay.
Yes, they do not care about the durability. So the properties, the materials we can use, but for example, the durability like this, they don't care. They do not work on those. They only use the mechanical properties. More focused on those.
Okay, now I understood, because I read the news a few days ago. Mitsubishi Chemistry, they say they develop a thermoplastic FRP, you know. So, okay, I understand difference. Thank you. Yeah.
Thank you.
Okay. Thank you, Professor Dai and Professor Xian. I have one question. So for the hybrid FRP bar, so you have two main types. The first one is the glass fiber and carbon fiber are smeared between each other. And the other one is just glass fiber in the center and surrounded by the, carbon fiber in the center and glass fiber surrounded by the glass fiber.
Yes.
So if you, in the interest of the durability, would it be better to put the glass fiber in the center and carbon fiber?
Yeah, yes, yeah, this is the design. This design problems. If you do the hybrid, what's the properties you really want to have? For this application design, for this glass oxide, frankly, it's good for the impact, good for the scratch and so on. It's not good for, just like you said, it's not good for the durability. Yes.
Okay, thank you.
Depend on our aim.
Okay, thanks. So this last question from the audience, it says, would you give some comments if we consider plant-based fiber as new type of FRPs, the natural fiber, I think?
Yeah, thank you very much, Jack. I like these questions because I have a big direction is on the flex and the natural fiber composites. Why did not I talk about this? Because in recent years, I do more work on the bridge application, and flex composites is very useful for other applications, but not for bridge. so I did not talk about this. I do believe flex or natural fibers biocomposites will be bright future in construction, and for example, for the buildings and some not high loading bearing requirement structures.
Okay. Okay. Thank you, Professor Xiang, again for your interesting presentation. Also, thanks to Professor Dai and Jack for your questions. Okay. Now, let's see what is the last invited speaker. Professor Yingwu Zhou. Before his talk, please allow me to introduce him briefly. So, Professor Yingwu Zhou is currently a distinguished professor in the College of Civil and Transport Engineering at Shenzhen University in China, and the Deputy Director of Guangdong Provincial K-Lab of Durability for Marine Civil Engineering in China. He is also the winner of National Natural Science Foundation of China for Excellent Young Scientists. He received his PhD, his bachelor's degree in 2003 and the PhD in 2009 from Dalian University of Technology, China. His teaching and research involve green concrete, high-performance concrete, durability of concrete structures, FRP composite structures, and structural rehabilitation using FRP materials. He is now undertaking or has accomplished 7 national foundations, including 1 National Excellent Young Science Fund project and 2 key national projects. Professor Zhou has published more than 130 journal papers, including 83 SAI indexed journal papers, and has got 16 Chinese invention patents. He also won a first prize of Science and Technology Advance Award of Guangdong government, China. And today his talk will be on an innovative hybrid CFRP bars reinforced concrete structure system with intelligent anti-corrosion. Yingwu, are you with us?
Yes.
Okay. You can start when you are ready.
Thank you very much for Chairman's introductions. I am Zhou Yingwu from Shenzhen University. It's my great honor to give a presentation in this international workshop. My topic is an innovative hybrid CFRP bar reinforced concrete structure systems with intelligent anti-corrosions. That's to use CFRP bar as a structural reformer and angles. Here we go. This presentation consists of 5 parts. Let's start with the research background. As we know, the corrosion of steel is an electrochemical process. Iron is oxidized and corrosion products are produced, leading to the reduction of steel bar corrosion section area and bonding strength. Because of the large volumes of these products, concrete crack appears, leading to the degrees of bearing capacity and durability. Corrosion has serious threatens the surface safety of infrastructure and cause huge loss to the national economy. According to the studies of academical Houbaolin, the economic loss caused by corrosion account for 3.3% of GDP in China. Therefore, 2 basic issues appear: the corrosion inhibition and structural strengthening. Many progress has been made in these 2 aspects. Generally speaking, the methods of corrosion inhibition can be divided into 3 types: anti-corrosion reinforcement to replace steel bars, reinforcement coating technique, and casualty technique. In the first time, stainless steel bar and FRP bar show excellent corrosion resistance, and they have been widely used in civil engineering. However, in addition to the high cost, they also suffer to insufficient ductility. In the second time, coated steel is also widely used in practical engineering. However, the coating may reduce the bond strength.
Passive protection is another technique to inhibit corrosions. The principle of the passive protection is to transfer enough electron to the surface of steel bar to force the rebar to become the cathode. Thus, the further corrosions of steel bar can be inhibited effectively. According to the applied current, cathode protection can be divided into sacrificial anode and impressed currents. The impressed current cathode protection is hereafter termed as ICCP. ICCP is the only technique which has been proved to be able to completely prevent the corrosion of steel bar in salt contaminated concrete. ICCP technique has been widely used in civil engineering, such as Hong Kong to Macau Bridge. For existing structure, the strengthening methods include enlarged section, pre-stressed bond steel, and FRP. In this presentation, we only focus on FRP. FRP is lightweight, high strength, and corrosion resistance. FRP products has been widely applied in concrete structure, and corresponding researches have been conducted in areas of material interface and structures. So, can we achieve the goals of corrosion inhibition and structural strengthening at the same time? Thanks to the excellent conductivity of carbon fiber, carbon materials such as acrylic, sheet, and bar can be used as anode for ICCP systems. Thus, the corrosion inhibition and structural strengthening can be achieved at the same time. It is in fact in the past decades, some progress has been made with respect to FRP anode in ICCP system. Professor Lee Orange from Mexico's first conduct an experiment study of FRP as anode in ICCP system. This is the FRP anode, and this is the steel bar. In the experiment, the FRP sheet was placed on the surface of concrete, developed conductive epoxy resins. The resistivity of epoxy resins was tested after compiling carbon fibers. In the figures of the potentials, we can see that in the ICCP state, the potential value of the protected steel bar is more negative than the values of non-protected rebar. This indicates that ICCP properly work to inhibit steel corrosions. Professor Gray from India studied the active and passive protection of FRP sheets. It is known that the passive protection relies on the various behaviors of FRP, and the active protection relies on ICCP with FRP as anodes. And conductive resins was developed by mixing the conductive particle into resins. For the desired concrete beams, we can see that the potentials of the active protection simple are lower than minor 720 MV, as you can see in these figures. According to the European draft standard, it can be inferred that ICCP is effectively and the steel is protected. Besides, based on the load deflection figure as shown in this figure, the simple with this slide, the simple with ICCP show the largest threshold capacity. So active protection provided by ICCP with FRP sheets as anode is effective. Another scholar, Professor Li from Wuhan University, also studied the active and passive protection of CFRP. In the experiment, CFRP red was placed on the surface of concrete column with a modified conductive epoxy. The modified conductive epoxy was produced by mixing graphite in epoxy resins. Here is their results. In the potentials figure, we can see that the instantaneous of potentials of the protest symbols range from minus 720 MV to minus 1,100 MV. According to the European draft standards, ICCP is effective. There is an interesting phenomenon, as we can see in these three figures, that during the linear polarization test, with the increase of the critical mass loss, the effectiveness of ICCP system with CFRP as NO is more obvious. Professor Yun from UK also studied the performance of CFRP brick and CFRP rock as ICCP anodes. The potentials with saw so that the steel is protected with CFRP brick fabric and rock as anodes. The circle resistance results show that the dissolution rate of FRP fabric was higher than that of CFRP rock in the ICCP systems. That's to say, the CFRP rock, as you can see, this is a CFRP rock, is more stable than CFRP fabric in ICCP systems. Shenzhen University has also conducted some research in the aspects of CFRP anodes. Professor Zhu and Professor Weida and Professor Xing proposed the ICCP XS system. In this system, CFRP grid was placed on the surface of concrete structure with an organic cementitious brightness. The effectiveness of ICCP XS system has been verified in aspects of material, interface, and structures. The CFRP anodes in this system played dual functions of structure strengthening and casualty protection. Professor Zhu and Professor White have introduced this ICP system this morning. At the same time, Professor Xin and I have proposed another system, a hybrid CFRP bar reinforced concrete structure system. In this system, CFRP bar is used as a structure reinforcement to replace steel bar, possibly an anode to integrate steel corrosions. The dual function of CFRP are fully displaced. This system is suitable for new structure and also existing structure. This system may have some several advantages. First, CFRP bar and steel bar are arranged in the lower layer and upper layer of the tension section, as we can see in this figure. The configuration can improve the ductility and stiffness of a CFRP bar RC structure. Besides, the durability of hybrid RC structure is also improved because thickening concrete covers for steel bar. Furthermore, since the bond performance of CFRP bar concrete mainly composed of the mechanical action, friction force, and chemical bonding force, without any adhesive, the bond strength depends on the bond length, accuracy, length, and roughness. Thus, the bond performance of CFRP bar anode to concrete may be more reliable. Besides, in this system, we can start the ICCP intelligently according to the corrosion status of steel bar by monitoring the condition of steel bar. Instead of the whole surface life, the ICCP system is only start when the corrosion of steel bar is detected. We also evaluated the total life cycle cost of these systems. And the results show that compared with the steel bar RC structure and CFRP bar RC structure, the hybrid RC structure with ICP show a minimum life cycle cost as shown in the red light. This line is the structure we form with pure CFRP bar, and this is a steel reinforced concrete bricks. So, aimed at this dual functions CFRP per annual ICCP system, we have carried out a series of studies from the aspects of material interface and structural performance respectively. The effectiveness of these systems has been verified. Okay, firstly, we need to know the degradations of CFRP per annum in the proposed system. The anode may degrade in ICCP process, so the accelerated anodic polarization test of CFRP bar is performed first, and then the mechanical property is identified. This is the experimental setup. CFRP bar is connected to the positive terminal of the power supply, and stationary steel is connected to the negative terminals. The maximum stand current density is amplified by 10 to 100 times to accelerate the corrosions. After polarization for 28 days, the surface color of the FRP bar deepens greatly with the increase of the current densities. That's to say that the great degradations of CFRP bar is proportional to the current densities. After polarization test, the tensile test of CFRP bar is performed. Here is the test results. As we can see from this figure, compare with the initial strength, the strength of CFRP bar with 100 times of standard current densities only decrease 40%. The deteriorations may be acceptable. To observe the microstructure for CFRP bar after polarizations, the XEM test was performed. This figure shows that the surface degradations of CFRP increase at current densities. The causes gradients react with the racing matrix, leading to the decompositions of racings. Therefore, we can infer that the improvement of carbon fiber matrix racings may improve the performance of CFRP anode in the ICCP systems. Based on the balance of charge quantity between the anode and the cathode, the surface line of CFRP bar as the anodes in ICCP can be calculated. As shown in the right figures, combined with the experimental data, it can be inferred that the residual strength is about 88% of the initial one after surf for 22 years with a current density of 20 MA per square meters. So in this part, the main conclusion is that considering the electrochemical and mechanical properties, CFRP bar can be used as an anode for the ICCP system. The second issue is to discuss the degradations of CFRP or steel bar to concrete interface during the ICCP process. For this new system, two interfaces are accessed. One is the steel bar to concrete interface. Another is the CFRP bar to concrete interface. Here are the corresponding experiment design, including ICCP tests and pull-out tests. In this study of steel bar concrete interface, the influence of the corrosion rate and current densities are considered. In the studies of CFRP bar concrete interface, we only consider the effects of the current densities. For the steel bar concrete interface, the accelerated corrosion test is conducted first. This is the test setup. During the test, lots of corrosion products are produced as shown in these figures. And the steel corrosion is also quantified after the whole experiment. It can be found that compared with the steel bar without ICCP, the corrosion rates of steel bar with ICCP decrease obviously, indicating ICCP is effective and the further steel corrosion has been inhibited. These are the setup of electrochemical tests, including ICCP tests and linear polarization test. During the process, the potentials of the steel bar are matched regularly. This is the result. From the potential results, we can see that the ICCP is effective. The steel bar is protected. The result of the linear polarization also verify the effects of ICCP. It can be observed that the steel bar is protected. Here are the pull-out test results. As shown in these two figures, the bond strength decreases with the increase of the pre-corrosions and the current densities. And these are the corresponding column figures and box figures for bond strength of steel to concrete interface. It is so that in the condition of 5% pre-corrosion range, as so here, the optimal current density may be 10 MA per square meters. Similarly, we also study the CFRP to concrete interface after ICCP. Here is the test setup. Potential is measured during ICCP process. Based on the potential result, we can see that the effects of ICCP is obvious, and the steel bar with ICCP is protected, as you can see these four figures. Most of the steel bar is protected. And the linear polarization results show that steel is protected with ICCP. After the electrochemical test, the pull-out test of CFRP bar is also performed. Here are the results. We can see that the bond strength show a slightly decrease after ICCP may be served for 30 years. We think this is still reliable. And these are the corresponding figures of the bond strengths. The bond performance decreased 30% after ICCP served for 30 years, but it is reliable, and the effects of such time on the bond strength is not previous. In this part, the main conclusion is that the bond performance of the both system is reliable. The last part, we want to note the structural performance of the proposed system. We consider the hybrid RC being with three different reinforcement configurations. Section type 1 with steel bar arranged in the bottom, and section type 2 with FRP bar arranged in the bottom. This is FRP bar. And type 3 with mixed arrangement. Combined with the accelerated corrosion test, driving cycle corrosion test, ICCP test, and bending test, the first performance of the hybrid RC beam can be identified. In the whole process, we consider the effects of corrosion rings, section layout, wet-dry cycle corrosion, and current densities and time. This is the detailed information of the experimental design. To review the effects of ICCP treatment in the short time, the accelerated corrosion test is performed first. These are the test setup for wet-dry cycle and ICCP. According to the potential result, it can be found that depolarization potentials of steel bar with ICCP treatment develop in a positive direction in intake, indicate that the steel is protecting with ICCP. While steel bar without ICCP develop in a negative, as shown in this theory of curve, indicates the corrosions are not is not inhibited. The bending test is conducted after the ICCP. Here are the results. In this figure, so the comparison of the low deflection curve corresponding to different section type and different conditions. It can be seen that for all the conditions, section type, as you can see this curve, with the FRP bar arranged in the bottom, so the largest bearing capacity, while section type 1 with steel bar arranged in bottom, so the smallest bearing capacity. Besides, compare with specimen without ICCP treatment, the bearing capacity has been improved with the ICCP protection. And the effect of the duration of 180 days is more obvious, as you can see in this figure. Then, the results are classified according to the section type to show the effectiveness of ICCP. Similarly, as we can see in these three figures, type 2 with FRP bar arranged in bottom and steel bar arranged in top is most effective to improve the artillery capacity of hybrid RC beams. Here we can take for the type 2, for example. As we can see that it is the red curve is the beam without corrosion, and the black curve is the beams with pre-corrosion and then wet-dry cycle. You can see after pre-corrosion and wet-dry cycles, the performance of the beam was reduced significantly. However, we also if the blue curve is beam with pre-corrosion, but without only with precursion without further wet dry cycle. And the per curve is the bin with precursion and with followed by wet cycle, wet dry cycle, and then with ICCP system. As we can see that the blue and the purple curve is almost overlapped, which indicate that the ICCP has inhibited the further corrosions of the steel bar. So we think this system is very effective to increase to inhibit the corrosion and to increase the performance of the V4 concrete. After bending test, the RC bins are broken and the steel bar as well as the CFRP bar are taken out to further quantify the steel corrosion and the effect of ICCP. These are the figures of steel bar with each condition. And the arterial corrosion rate of steel bar can be quantified after cleaning and rating. We can see that with ICCP treatment, the corrosion rate of steel bar is reduced, as we can show in this column. We can
Hello?
Screen is frozen.
Yep. I think you has a very weak internet.
Yeah, computer maybe getting tired.
Okay. So we need to wait for him. Oh. So I'm gonna call him.
What's the problem? I cannot say anything now.
Yeah, I think they're trying to contact Professor Zhou now, and I guess after that we may try to conclude the morning session. Let's see what happens. It seems that Professor Zhang has.
Yes, I just contacted Professor Zhou, and he's dealing with the problem, and we come back to us very soon.
So Shenzhen University is very rich. They have 2 big projects on ICCP.
Yeah. Sure.
Okay, Professor.
Yep.
Can you hear me?
Yes, I can hear you now.
Okay. Sorry. I'm sorry.
That's okay. So maybe we missed the last slide of your presentation. The conclusion, maybe have you finished? So I think should be okay. So we can go into the discussion session. So in view of time, maybe we can allow 1 or 2 questions. So any question?
I will ask a question on the result. Can you show your PPT again? No. Go. Please share your PPT again. I will ask a question about you, one of your results. Maybe the last 3, last third.
Right?
Can you share your PPT again? I will ask a question on your results.
Yes, I can try to share the.
Yeah. On the on maybe on the page on page 51.
Which one?
51.
51.
Yeah.
51.
51. 51.
Okay.
51页.
Yes.
I think the right, yeah, the figure on the right. I think it's very hard to understand. For examples, the right, the figures on the right. After you after the beam was corrosion, both the strength, the load capacity, and the stiffness should be already degrade, right? So then you do a cycle, dry wet cycle.
Wet dry cycle, yes.
Yeah.
The first was pre-corrosions, and then the beam was put in wet dry cycle.
My point is here. After the beam was pre-corrosioned, and it was both the load capacity and the stiffness was damaged, was degraded. That is understandable. And if you do some further dry wet cycle to this beam, then we can observe or see the 2 curves on the bottom. We can say that both the load capacity was reduced further, but the stiffness of the beam was there was near no change. This is also understandable. But my question is this: after the beam was pre-corrosioned, and if you use your system, use your technology SSC, and you do a dry wet cycle, how can you restore that load capacity to the level of the beam without corrosion? That is very hard to understand. I think maybe you make some mistakes in label the figure. I think the curves.
I'm sorry, I'm not very clear about your questions.
我中文说一次吧，就是我觉得那个下面2条线是很好理解的，因为你这个已经腐蚀了，然后你它这个刚度和它的承载力都降低了，然后你再对它进行一些3次循环之后，它这个刚度它不降低，但是强度继续降低，这个是可以理解的下面2条线。但是我不能理解的是你上面2条线，也就是说你用了你这个技术，那同时又进行了损伤，它为什么能够使损伤之后？用了你这个技术就能把它恢复到那个就是腐蚀之后，用了你的技术之后就把它能够恢复到那个承载力，能恢复到那个没有腐蚀的程度吗？强度那个 level 上面吗？我觉得这个很难理解哦。
不，我知道你的意思了，是这样的，这个黑色这个线呢，就是先 pre-corrosions and then wet dry cycle, and blue curve is only the blue curve is only with pre-corrosions, and the purple curve is with pre-corrosion and then wet dry cycle, and then during the wet dry cycle, ICCP is applied to the beam when the beam was further put in the wet dry cycle corrosions. So this purple curve and the blue curves is overlapped, so indicated that the ICCP system has inhibits the further corrosion due to the red dye cycle.
No, but if you conclude that this you propose the technology can stop the corrosion, can delay the effect of the corrosion, that's okay. But you cannot say that the system can restore the node capacity of your beam to a higher level, to the level of the beam without corrosion. That is hard to understand. You cannot, maybe I guess maybe you just label these two curves wrongly. For example, the pre-corrosion dry wetland cycle, SSC, maybe this is wrong. You just give a wrong label. And then pre-corrosion dry wet cycle, SSCP, 118 days. That's also wrong. Think about that, okay?
Okay.
Okay, thanks, Guangming, for the question. Thanks again, Professor Zhou, for this systematic study. It's an interesting presentation. Okay, so we had 3 interesting invited presentations, and here is the end of this session. So if you have further questions, you can contact the invited speakers in person. Okay, so it's the end of this session. Maybe Tao, you want to say something? I will pass this on to you.
Thanks, Sun, and I think we have finished all the morning presentations. And thank you to the 2 session chairs and all the speakers for their excellent presentation. We'll have a lunch break now, and we'll come back for the afternoon session at 1:30 p.m. So you probably need to have a quick lunch. Okay, 1:30 p.m. We'll come back again. Okay, thank you very much. I'll see you in the afternoon.
Thank you. See you.
Bye-bye, Tao.
Thank you. Bye-bye.
Bye-bye.
我上来了。
Yes, welcome, Professor Chen. Yes.
Should we start now?
We'll start in a few minutes.
Hi, how are you today?
Hello, Professor Madaway.
Yes.
Yeah, nice to see you.
Yes, welcome. Professor, we're going to introduce a little bit and then you can start to share your screen. We have stopped the share.
Guangming, you have a lot of books.
I think when Professor Madawi was sharing his PPT, I will give him introduction.
No, we'll start in a few minutes. We'll start exactly 1:30.
Okay. You give me a reminder.
You see the screen at the moment?
Yes.
Yes, clear.
That's good, yeah.
How? Can you hear me?
Yeah.
Okay.
So shall we start?
Wait a moment.
Okay, I have a meeting after half an hour exactly, so I have to leave after half an hour.
Okay, I think it's 1:30 now, so we'll make a start. Good afternoon, everyone. Welcome back to this workshop. So I hope you have enjoyed your lunch. In this afternoon, we have 2 sessions. So now we invite the chair of our first session, Professor Guangming Chen from South China University of Technology. Guangming, it's yours.
Okay, can you hear me now?
Yeah.
Now, I will chair this section, and thanks for the organizing committee giving me this chance. Now I'll give a brief introduction to Professor Tema Madaway. Professor Tema Madaway is a professor of structural engineering at United Arabic University. He's currently serving as a strategic initiative manager at the university's project managing office. He's also a coordinator of the PhD program in the College of Engineering. Before joining the university, Professor Madaway was working as a structural engineer at the Toronto, Canada. He earned his PhD degree from the University of Waterloo, Ontario, Canada. He is now an associate editor of the ASC Journal of Composite for Construction, and also an associate member of the ACI 440 committee. Professor Madaway has established a national reputation as an expert consultant in the field of conditional assessment, corrosion monitoring, surface life prediction, and rehabilitation of concrete structures. Professor Madaway, you can start now.
Thank you, Mr. Chairman, for introducing me. I'm very glad to be here today. And in the coming...
you have 30 minutes.
Yeah, don't know why it doesn't want to... Yeah. So in the coming 25 minutes or 20 minutes, I'm going to share with you research projects conducted recently at United Arab Emirates University on reinforcing concrete structures with FRP bars. So this is actually the agenda of my presentation today. I'm going to start by explaining corrosion problems, advantage of using FRP bars, And then I will show you some demonstration projects that have been conducted at UAE. And then I will also elaborate more on research projects conducted at the university, United Arab Emirates University, and then I will end up with some conclusions. So in the Gulf region, the marine environment, high temperature and saline groundwater results in major corrosion problems. As you can see, corrosion can attack the bottom soffit of a bridge deck or even the top surface of bridge deck suffer also from corrosion sometimes. Not only the superstructure, substructures in terms of columns also are very vulnerable to corrosion, damage, and cracking. Also, the use not only in the Gulf region, in cold countries, in North America, in Europe, the use of de-icing salts also results in major corrosion problems. And this is why FRP actually have a great potential to replace conventional steel reinforcing bars and eliminate corrosion problems. In addition to being non-corrosive material, FRP, as we know, they have high tensile strength, and the glass in particular, the glass bars have magnetic transparency, thermal electrical conductivity, and most of the FRP bars are very lightweight, and this facilitates construction and actually speed up the construction process. So composite rebars are typically used in special structures, such as structures in highly corrosive environment, including seawalls, waterfront structures, bridge decks, etc. And in some special cases for building with sensitive equipment like MR units, for example, in hospitals, steel bars are not actually a good choice. So in such cases, the use of glass bars with to avoid actually the disturbance of some sensitive equipment is a must. This is a project that has been actually conducted in Saudi Arabia using where the GFRB bars have been used to establish or to construct marine dock, and obviously this would actually eliminate corrosion problems and extend service life of the marine dock. This is another project in Dubai waterfront where FRP has been used to extend the surface life and avoid corrosion. This is a building that has been entirely constructed using GFRB bars. And the reason of doing that, the building function was to calibrate electrically sensitive equipment. And the use of steel bars actually wouldn't help in achieving the function of the building. As such, GFRB bars have been used and selected. Despite the advantage of using FRP bars in construction, the durability of these bars under harsh environmental conditions is questionable. And this is actually the main reason of, or the most obstacle that hinders their actually widespread use in the Gulf region in particular. This is why durability of FRP under harsh environment research on this subject has attracted many scholars in many countries, including actually my research group at UAE University. So I'm going to share with you now some of the research work that has been conducted at UAE University using FRP bars. As we all aware of, FRP could be used in strengthening or could be used in new structures. the focus of this presentation is only FRP bars, not FRP sheets. And FRP bars have been used at university in both, actually, as reinforcement in concrete element, and also as a strengthening technique to improve the flexion of the shear capacity of existing elements. And as I mentioned, also durability was a concern, and it's actually ongoing project at United Arab Emirates University to examine the long-term behavior of FRP bars under the harsh environment of the Gulf region. So every generation of commercially produced FRP in terms of glass or basalt or carbon, their durability must be examined before they can be routinely used in practical application. So what you can see here, this is actually a project where we examine the durability of 2 different types of GFRP bars and 1 type of basalt bar. And test parameters included the conditioning duration. GFRP bars were conditioned for up to 15 months, but basalt bars conditioned for up to 9 months, and there are 3 different temperatures in the range of 20 to 60. And the conditioning regime included the actual concrete environment. In some cases, the concrete was seawater contaminated, and in another case, we had the only alkaline solution just to examine the difference in the behavior under 2 different conditioning regimes, and to actually imitate what might be happening in practical application. We applied sustained load to a group of FRP bars while being conditioned using sustained loading frames. These frames have been fabricated at the university, and these frames have the capability to apply sustained load to 3 replicate specimens each frame, and they actually can magnify the load up to 50 times. So here you can see the concrete. Here you can see the concrete surrounding the FRP bar, and these are the loading frames. You can see here the 3 replicate specimens are loaded for each frame, and this is actually the conditioning tanks. And these are the bars that actually conditioned without sustained load. Following conditioning, the bars were retrieved and then tested to failure under uniaxial tension. And here you can see the mode of failure of a basalt bar, rupture of FRP, and here also glass bar rupture mode of failure was recorded. In terms of results, this actually shows the strength retention with time for 2 different bar types. The top figures for bar type number 1 and the bottom figures for bar type 2. The left figures for bars without load, and the right side figure for bars under sustained load. Obviously, increasing the conditioning time results in additional strength reduction, and increasing the temperature actually aggravates or more the reduction more significant. Obviously, also the presence of sustained load during conditioning was had like a significant effect on the strength retention. If you compare results of bar type 1 to results of bar type 2, you will find that the durability performance of bar type 2 was inferior compared to bar type 1. Although bar type 2 has initial tensile strength of 1300, which was higher than the initial strength of bar type 1. This gives the message that the initial strength is not indicative of the durability performance. So in our research, as an example, we found that it is not necessarily if the bar strength, the initial bar strength is higher, it doesn't mean that the durability of the bar will be better. I need also to emphasize that many bars were ruptured under sustained load, especially those at the higher temperatures of 40 and 60 degrees. And the results that's actually displayed in front of you excluded the ruptured bars, because if a bar ruptured, then the strength is 0. And the reason of rupture of the bars during conditioning was due to creep. And I need to highlight also here that we have applied a sustained load that corresponded to 25% of the tensile strength. And this is actually much higher than the code limit. The code limit is 20%. And if you consider the strength reduction factor, then the code limit would be around 15%. We were aiming to examining the bar under sustained load higher than the code limit, maybe to recommend an increase in the sustained load limit, but obviously it's not recommended to apply sustained load higher than that specified by. If we consider the bars that were ruptured during conditioning, then the strength degradation will be much more severe under sustained load. These are results of the basalt bars up to 9 months of conditioning, but group of bars, as I mentioned, were under alkaline solution, bare bars under alkaline solution, and other ones were in concrete environment to resemble what might be encountered in practical application. At the low degree of temperature of 20, no significant difference between the performance in alkaline solution or in concrete. However, at the higher temperature of 40 and obviously at 60, the degradation was much more severe when the bars were immersed in alkaline solution than in concrete. This actually again gives the message that long-term results in alkaline solution might overestimate the strength reduction. It's conservative, but it might not actually be practical, and it's recommended to use actual concrete in durability test rather than alkaline solution. In order to understand why GFRB type 2 was inferior compared with GFRB type 1, we had to measure the water absorption with time. And we found the reason why type 2 didn't perform well compared with type 1 is because of the water absorption. Type 2 experienced higher water absorption with time, especially at the higher temperature. And this results in the higher water absorption facilitates the hydrolysis reaction, and this actually would cause matrix softening and disintegration, and this will damage the bond at the fiber matrix interface. Also, when we measured the void content of two types of the GFRB bar, just to understand why type 2 had more water than type 1, we found that as per STM test method, that bar type 2, the void content was 0.25%, which was much higher than the void content of type 1, and that was the reason why more water absorption was existed in type 2, and which resulted in poor durability behavior of type 2. And this is mainly related to composition of the FRB bar during fabrication. To better understand the degradation mechanism, we also did microstructure analysis using SEM, and here for each part type you have, in each figure you have 4 sub-figures.
Figure number 1 is for the control unconditioned, and the other figure is B, C, D for conditioned bar, conditioned for 15 months under 20, 40, and 60 degree. Obviously, for the control samples, you can observe that we have matrix between the fiber, well intact and well bonded. And this is obvious in the longitudinal micrographs and also in the transverse micrographs as well, for both types. After 15 months of conditioning, especially at the high temperature, you can see clearly here that there is a deterioration of bonds between the fiber and the matrix. And this is clear in the longitudinal graphs, also in the transverse graphs. Here, this actually picture clearly shows the bonding at the fiber matrix interface. And that was the main reason of degradation. Away from durability, I'm going to share with you in a few minutes the application of FRP bars in structure application in terms of strengthening and in terms of using them as reinforcement in new structures. So this is actually a project to examine the effectiveness of using GFRP bars in strengthening, flexural strengthening using near surface mounted technique. So these are slab strips, and we cut groove on the surface, and then we insert epoxy, and then insert the bar, leave it to cure. We have done experimental testing on continuous slabs. Test parameters included sagging strengthening versus hogging strengthening, and we have done also numerical simulation to better understand the behavior. In brief, sagging strengthening was much more effective than hogging strengthening. So sagging strengthening resulted in up to 70% improvement in flexure capacity. Hogging strengthening resulted in up to 40%. So GFRP bars can also be used in near surface mounting strengthening technique with a great success. This is another project for shear strengthening of T-beams using GFRP bars. Of course, these bars could be actually applied on the surface as near surface mounted, but in this project, we examined the effectiveness of using a new technique called embedded through depth. So we drilled holes vertically, as you can see in the pictures, and then we insert epoxy and insert the bar inside, leave it to cure, and then we tested beams strengthened and beams unstrengthened with different amount of internal stirrups. And the graph on the left side actually gives you idea about the shear behavior. We found that the shear strength has improved significantly after the application of GFRP bars. And the strength gain was dependent on the amount of stirrups inside. The strength gain was in the range of 30 to 56%. The last project I'm gonna share with you is about reinforcing discontinuity regions in deep beams using GFRP bars. So as we are aware of, installation or creation of an opening in a concrete deep beam is frequently required to accommodate air conditioning ducts, water pipes, etc. However, creation of an opening reduces the shear capacity significantly because it interrupts actually the natural load path from the loading point to the support point. So in our research here, only 20% an opening with 20%, having a height 20% of the full height of the beam resulted in 50% reduction. The black curve in this figure represents the controlled solid specimen without any opening, and the blue one represents the behavior of a beam with opening. So you can observe the significant reduction in shear capacity due to the opening. So in this research, we examined the effectiveness of reinforcing D regions using GFRP bars. So we developed 3 different strengthening schemes based on certain time modeling. And scheme number 1 included GFRB bar below, diagonal below the opening in the bottom chord. The scheme number 2 was diagonal FRB bar in the top chord, and the scheme number 3 actually had 2 bars both in top and bottom chord. And obviously the use of GFRB was very effective in improving shear capacity up to 90%. I mean, these results actually for scheme 1 and 2 only. So we observed up to 90% enhancement in the capacity. So proper use of FRP could actually fully restore the original capacity. And we conducted also numerical simulation, and you can see here the crack pattern predicted numerically was in good agreement with the crack pattern recorded from the test. And the numerical simulation also was very important to understand the shear behavior and how the load will transfer in the presence of reinforcement and in the presence of opening as well. So to conclude, FRB bars have a great potential to replace conventional steel reinforcing bars and eliminate corrosion problems. And the application includes reinforcing of new structures and also strengthening or retrofitting of existing structures. Flexural strengthening of continuous slab strips with GFRB bar using near surface mounted techniques resulted in 70% strength gain if applied in the second region and 40% if applied in the hogging region. The new technique of embedment of GFRB bars through the entire depth of the section using GFRB was effective in improving the shear capacity. Up to 56% was recorded strength gain, and the shear strength gain actually decreased by increasing the amount of internal stirrups. So if you have more stirrups inside, the use of GFRB will result in a minimum strength gain. But if the beam is lacking the stirrups, then the use of GFRB obviously will significantly improve the behavior. Now, reinforcing of D regions and D beam with diagonal GFRB bars was also effective. The scheme having diagonal bar in the bottom chord was more effective than the scheme having a diagonal bar in the top chord. Degradation in tensile properties of GFRB is highly dependent on the void content and water absorption properties. And this is highly dependent on the manufacturing process and composition of the matrix and the fibers. The degradation of in tensile properties of FRB bars was more sensitive to the temperature rather than duration. The temperature has more significant effect. And obviously, the presence of sustained load actually aggravates the damage, especially at the higher temperature. And at the end, I would like to acknowledge the financial support provided by University, Sultan Qaboos University and American University of Sharjah in these research projects, and also in some of the structural applications. I would like also to acknowledge the donation of GFRB bars provided by Poltron Composites. Now I concluded my presentation. We have like maybe 5 minutes. If anyone has any questions, I would be glad to answer.
Thank you, Professor Madawi. You have a very good time control. Is there any question from the participant? You can raise the question on the QA window.
Hello? Hello, Professor Madawi.
Yes.
Thank you for a very nice presentation. And it's interesting to see that the 2 types of FRP you use actually have quite different durability properties. Okay, so my question is the void content the only difference between the 2 types of bars? Could you comment on other possible factors, including the location and distribution of the voids and the fiber to matrix bond and the use of different railing? Could you please comment on this? Thank you.
Yeah. Thank you very much for the question. You know, manufacturing of these bars I mean, these answers to these questions are secrets to the manufacturer. We don't know the exact composition, but the only property that could actually measure in the lab is the void content. And obviously the void content was higher for the bars that exhibited inferior durability performance. So I don't have an answer for the other properties because we did not measure in the lab, and it's not an easy task to measure these properties. Maybe the manufacturer would actually have a better idea about these properties, but for sure the void content was a factor that affected the performance in our research.
Okay, thank you.
No problem.
Okay, we can permit one more participant to raise a question. Is there any researcher want to ask a question for Professor Madaway's research and presentation? If there's no, I will close the presentation of Professor Madaway. Thank you very much, Professor Madaway. Very good research. And I will now go to the next speaker. I will give a brief.
Thank you very much.
Okay, I will introduce to the next speaker. Our next speaker will be Professor Zheng Yu. Can you hear me, Zheng Yu?
Yes, yes, Guangming, I can hear you, yes.
I think you can start sharing your PPT then during this process.
I share my screen, yes.
Yeah. Yep. Professor Zheng Yu received his PhD from Queen's University, Belfast at the year 2008. And he's now professor of structural engineering and head of the Department of Civil Engineering at the Dongguan University of Technology. And his research interest include emerging structure materials and systems, the structure use of FRP in construction, retrofitable structure, life cycle, structure engineering, and the numerical modeling. Now he published over 30 SI papers, which attracted around more than 200 citations. He also served as a reviewer for more than 20 international journals. Now, Professor Zheng, you can start.
Okay, thanks, Guangming. Thanks, Chair's nice introduction. Good afternoon, everyone. Today it's my great honor to make a presentation in this excellent workshop. Thanks for the invitation. The topic of my presentation is the structural behaviors of the self-compacting concrete bridge deck slabs reinforced with FRP bars. This is a collaborative research including the Dongguan University and Queen's University Belfast and one composite material manufacturer named as Haichuan in China. This is the outline of my presentation, include the introduction, why we need to do this research, and then the field test of a real bridge constructed with a bridge deck slabs by using the self-compacting concrete and FRP reinforcing materials. Then we developed the research on the bond behavior between these two materials, and then we study the serviceability and the ultimate behaviors of FRP reinforced self-compacting concrete bridge deck slabs, and then we get some conclusion. The first part of my presentation is why we need to do this as well reported. The sustainable problem caused by the infrastructure can be found from the two sources. One is the corrosion problem in the steel materials, including the steel reinforcement and the steel structures. Another one is the high carbon dioxide emission in the traditional concrete materials, especially for the cement-based concrete materials. Therefore, it can cause very high maintenance fee. This is we can find that the sustainable problems for the infrastructure. How to solve that problem? Usually, the solution for these two problems, one, we can use some corrosion-free materials such as FRP to replace the steel materials, such as FRP reinforcing bars to replace the steel bars inside the concretes. Another one, we can use some concretes with high proportion of the industrial waste, such as fly ash or GGBS. We can use that to we can use that to replace the traditional cement-based concrete, such as the geopolymer concrete or the self-compacting concrete with high volume of fly ash or GGBS. Therefore, another one is why we need to study the bridge deck slabs. In our previous research, we can find that the bridge deck slabs is the structure can be will be deteriorate faster than any other structural element in the bridges. This will be caused is due to the de-icing sources and the side effect of the small companies of this structural component and the transportation loadings applied directly on this structural component. That's caused some serious service problems. Therefore, we try to build some high sustainable bridge deck slabs. One is we will try to replace the steel reinforcing bars by the FRP bars. Another one we can try to use some one we try to we build a real bridge in Northern Ireland. In this bridge, the bridge deck slabs is constructed by using the self-compacting concrete and the basalt fibers. Another interesting point for our research is for the bridge deck slabs. As well known, this is a lateral restraint structures. For the lateral restraint, concrete slabs have inherent strength due to the implant forces set up as a result of the external implant forces as a result of external restraint. Those external restraint occurs due to the slab boundary condition, such as the supporting beams, the diaphragm, and the continuity of the slab outside the loading area. This structural phenomenon we call as arching action or the compression membrane action. Therefore, due to the low elastic modulus and the brittle behavior, the construction cost of the traditional FRP reinforced concrete could be high due to the high reinforcement percentage for satisfying the requirement of the service behavior to control the cracked wires, to control the diffraction. Interestingly, in the lateral restraint concrete slabs, such as bridge deck slabs, generally the lateral restraint stiffness and the concrete strength control the structural design. The structural behavior of the lateral restraint concrete slabs is independent to the percentage of the reinforcement percentage, or sometimes independent to the reinforcing materials. Based on this structural phenomenon, it can be summarized that the arching action inside the concrete slabs had a beneficial effect on the service and ultimate behavior of the FRP reinforced concrete bridge decks with low reinforcement percentage. Therefore, the aims of this project, we try to develop some low energy concrete materials by utilizing the combination of the waste industry waste materials and use the corrosion resistant fiber materials and try to investigate the behavior of the FRP reinforced low energy concrete structure. We try to use the benefits of the arching action in the concrete bridge deck slabs to realize the concrete bridge decks with low reinforcement percentage of FRP bars. Therefore, we can produce the economic lower energy and improve the whole life performance infrastructure. The first part of our study, we try to build a real bridge named Twingson Bridge. This bridge is built in Northern Ireland. This is the layout of test panel. We have four panels reinforced with BFRP bars, and the other two panels reinforced with steel bars for the compression. This is the configuration of some optical fiber sensor and then casting the self-compacting concrete for the construction. That's the test configuration. We apply the maximum applied load for this testing is 4 kilonewton, which is allowed 3 times of the maximum weight load defined in the Europe code. That is the one test result. The typical load deflection result for the vertical deflection given in this figure. For the panel, the reinforced FRP bars, we can find that the recoveries of this structural performance is in the state of 90%. That means the service ability is acceptable. In the comparison between the load and deflection between the FRP reinforced bridge decks and the steel reinforced bridge decks, you can find it's very interesting. Even though the reinforcement percentage is very close, even though they have different stiffness of those two reinforcing materials, the deflection, the lower deflection response will not be influenced by the lower stiffness of this of the FRP reinforcing materials using inside concrete. This could be due to the action contribution to the structural behavior for the FRP reinforced concrete bridge deck slabs. Another one, we can find that the ultimate strength or the maximum strength inside the FRP bar in this field test is at the low of the 400 kilonewtons, was around 11% of the maximum strength of the adopted composite materials. That means it's nearly, even though when we apply the low is 3 times of the maximum Europe code defined wheel load, the strength values, the stress level of the FRP reinforcing bar is still very low. All that suggested the applied load is within the service loading for the bridge deck slabs. It saw good recovery in the strength after the ultimate load removed. Currently, we developed the structural health monitoring for these bridge decks. You can find that even though the heavy truck passing past bridge decks, the strength value is still very low. That means all the structure is very healthy and the service is acceptable. Another one, we can find that the hairline crack was visible in the permanent GPC bridge decks. And we use the strength value measured by in the BF basalt fiber reinforcement. We can obtain the crack width. We can find that the maximum crack width is less than the 0.7 millimeter, which is the limitation defined in the ACI code for the bridge for the FRP reinforced deflection flexural components. Another one. In this study, the current design code named as ACI 440, it was adopted to predict the ultimate capacity. As shown in this table, the failure modes defined will be predicted as punching shear failure. But we can find that the ultimate load is smaller than the test load. For the test panels, the predicted failure load is far below the value of the prior load, which is within the service load range for each panel. Therefore, we use a design code named BD81, provided by Queen's University Belfast in the British standards to predict the ultimate capacity of the FRP reinforced concrete bridge deck slabs in this construction. You can find that is around 3 times of the for the predicted result of ACI code. Therefore, we can get some temporary primary summary for this field test. The bridge deck slabs reinforced FRP bars has strength of the designed ultimate loads and behavior similar manner to those reinforced with steel bars, have the similar reinforcement percentage. By using the benefits of action, the very low percentage of FRP reinforcement are possible. The self-competing concrete showed the similar behavior to the conventional vibrated concrete in terms of the action performance. Based on this summary or the findings in this field test or the demonstration construction, we need to develop some further study including the material of the high volume fly ash self-competing concrete and the interaction relationships such as the bond behavior or the tension stiffening behavior between the FRP bars and the self-competing concrete. Then another one, we try to study the serviceability and the ultimate behavior for the FRP reinforced self-competing concrete bridge decks. And finally, we try to establish the design methods for these composite bridge deck steps. But due to time limits, we will not introduce the first one and the final one. We try to introduce the second and the third and fourth point in my research. The first one, as well known, the bond behavior or the interaction relationship between the reinforcing material and the concrete metric material has a strong effect on the service behavior, such as the crack rise and the diffraction, especially for the FRP reinforced concrete structures. Therefore, we need to develop some study to investigate it, the interaction behavior between these two materials. We developed two phase test experimental study. One is the traditional pull-out test to study the bone behavior. Another one, we try to develop some two additional tensile tests to study the tension stiffening behavior. But in this presentation, we will introduce the first part. In the bone test, this is the experimental variables for the bone test, including the diameter of the reinforcing bars. We change the reinforcing materials. We change another one. We change the spiral height for the GFRP bars, and then we change we vary the surface treatment for the GFRP bars. That is the typical test samples. That's the test configuration, including the loading configuration, and then the measured methods using in our test. In this result, we can find that the recorded the average bone strength for the bone strength for the steel reinforced test sample is around 2 times of the bone strength for all the FRP reinforced self-competing test sample. This could be contributed to the high axial stiffness of the steel reinforcement compared to the FRP bars. And then another one is the steel rib surface treatment in these reinforcing materials. And in all the test results, the common failure modes observed in this test is the pull-out failure. The bone failure of the reinforcing of the FRP reinforced test sample depends on the friction. You can find depends on the friction and the adhesion and the chemical adhesion. While the bone failure for the steel reinforced test samples is controlled by the mechanical interlocking. In addition, when we study the GFRP bar, those have the standard coated surface treatment, resulting in this test sample. This surface treatment resulting in the elimination of the result-rich outer fiber coat and damage to the concrete attached to the bar surface. And the surface of the concrete GFRP reinforcing bars, the damage elimination of the result-rich outer in the pull-out test in the self-compacting test sample. But for the normal concrete test sample, you can find that the GFRP bar, the surface, you can find that the surface is intact. The damage is smaller than the self-compacting. This is due to the fact that the compactness of self-compacting concrete is better than the normal concrete due to the filling effect of the fly ash and the limestone powders using in the self-compacting mixture. The failure modes also can be defined by our using some novel monitoring method. Due to time limitation, we will not discuss here. Therefore, we try to predict the bone strength for the FRP reinforced self-compacting concrete. You can found that we're using the concrete in the literatures. Most of the bone strength have been having overestimated, and the effect of the concrete interface compactness have not been considered in those prediction methods. Therefore, we try to establish or propose a new prediction equation for the FRP reinforced self-compacting concrete. Because we can observe that the self-compacting can significantly improve the bone strength compared to the normal concrete materials due to the high symmetry and high density. With the consideration of the filling ability and the compactness, therefore, we consider the ratio between the diameter to the development length. We consider the phi aggregate to the all aggregate ratios. Use that to define our bone strength prediction method. And therefore, we can find that increasing the ratio of the final aggregate to the coarse aggregate results with improvement of filling ability of the set capacity and the interface. That means that can enhance the bone strength between the FRP bars and the self-compacting concrete. Compared to the test result, it shows a good agreement between the test result and the predicted result. But currently, the test result is still very limited. Based on the bone strength prediction, we developed the development length prediction method for the structure design for the FRP reinforced self-compacting concrete. Another one, we could compare the most popular three bone slip constituent model to predict the bone slip response. We modify some parameter based on the experimental data. We can find that the modified BPE model, the accurate expression is more accurate. The precise piecewise expression is more accurate in the predicting the bone slip behavior of the FRP reinforced self-compacting concrete. This model is capable for for these composite structures. And the fourth part in our study, we try to study the serviceability of the bridge deck slabs. In this test, we develop a one-way slab to represent the concrete bridge deck slabs. To start, apply the 4-point bending loading to study the service behavior. In this test, we changed several experimental variables, including the concrete materials, reinforcement percentage of the FRP bars, and then the reinforcing material. And another one, we try to use some PP fiber to try to use that to increase the crack control ability. That is the typical failure modes. It can be found that due to the low stiffness of the FRP bars, the failure will be controlled by the shear cracking and then the shear compression or the shear direct tensile failure in the FRP reinforced self-compacting concrete. And due to the higher axial stiffness of the steel reinforcement, the typical fracture failure can be observed. Another one, we can find that the relationship between the average cracking and the maximum crack is also linear. And then we can study the ratio between the maximum spacing, crack spacing to the average crack spacing is also in the range of defined by the Euro code for the steel reinforced concrete structure. But in the study for the crack bias, it can be found that two concrete materials have not significant effect on this structural behavior. But if we use some PP fiber in a higher portion in the concrete mixture, it can be increased the crack control ability. But as expected, when we change the reinforcing material, steel reinforcement can result by far smaller crack wise compared to the FRP reinforced concrete bridge deck slabs, and as expected too, the reinforcement percentage of the FRP reinforcement has also a strong effect on the crack wise control. And interestingly, we can find that when we compare the average crack wise to the maximum crack wise, the linear behavior can be found for the FRP bars. That means the stronger compatibility between the reinforcing material and the concrete materials. In the study of the low and diffraction response, all the test results can be expected. The concrete materials have no strong effect on this structural behavior, and the reinforcing material stiffness and the reinforcing percentage have a strong effect on the low and diffraction response. Therefore, we try to establish the design criteria for the serviceability. We select three design criteria. One is the stress on the material limitation and the crack wise limitation, the diffraction limitation. And finally, when we compare the surface load to the cracking load and the surface to the ultimate load, in the two comparison, we can find that the crack wise can be the control criteria, design criteria for the serviceability in the design of the FRP reinforced self-compacting concrete structure. We try to evaluate the accuracy of the current low and diffraction prediction method for FRP reinforced self-compacting concrete. We select those prediction methods have been published in the literature. But we can find that the prediction method in the ISS Canada code and the CS8 can predict reliable and accurate predictive results. And furthermore, we try to discuss the crack spacing prediction. We use the Europe code and the model code and the Europe code 2, 1902 and the JSCE. In those two, in the maximum prediction, we can find that the Europe code can provide accurate result compared to the JSC, compared to the model code 19. And then for the average cracking prediction, also the Europe code can provide the reliable prediction. But in those, as a result, it can be summarized that the bone behavior but in our study, the bone coefficient need to be adjusted, need to be modified based on bone test result, need to be increased due to the bone strength, bone behavior have been enhanced due to using the self-compacting concrete. The final study section in serviceability, we study the crack-wise prediction. Unfortunately, we can find that currently the current crack-wise prediction is not reliable and unstable, and accuracy cannot be acceptable. Therefore, based on our test result, in the test result revealed that the low bone behavior of FRP and self-compacting resulted in small tension stiffening and the low contribution of the FRP to the concrete crack-wide control. Therefore, linear behavior is a sham. We propose our crack-wise prediction. In the comparison between the test result, it found that a good agreement and validation can be obtained. In the final section in our study, we try to study the ultimate state. This is the test setup. We try to study the punching behavior of the bridge stack slabs constructed with FRP reinforced self-compacting concrete. In this section, we modify the reinforcing materials, including the BFRP, steel, and the GFRP, and change the reinforcement percentage of the BFRP reinforced material, and we change the concrete materials. And in one sample, we use some PP fiber inside in the concrete mixture. This is all our experimental variables. It can be seen in those figures, it can be seen all the crack pattern and the failure mode is very similar, despite the different reinforcement percentage and different reinforcing materials and the different concrete materials. It can be summarized that the cracking load cannot be affected by the load reinforcement. Also, the low FRP, load reinforced stiffness cannot be affected the crack-wise and crack pattern significantly, which due to the contribution to the abstraction in the lateral restraint bridge stack slabs. When we're using some PP fibers, the smaller cracks can be obtained. That means using those fibers can increasing the cracking, can control the capacity for the concrete materials. We studied the punching angle because the large punching angle resulted to more brittle punching failure. Though means the increased the contact area between the concrete portion. Because we can increase the larger punching failure in this assumption, that means the larger the punching strength. And this is the after the measure we can after the test we measure the punching angle. It means the punching angle is very similar, but when we found that we can try to discuss the ultimate load and the low and deflection comparison. We can find in this when we change the reinforcement percentage and the reinforcement percentage and reinforcing material and the concrete materials, those variables have not a significant effect on the ultimate loads. But when we change the stiffness of the reinforcing material, the low and deflection response can be enhanced compared to the FRP reinforcing materials. Therefore, we try to establish the ultimate capacity prediction method for the FRP reinforced concrete bridge stacks, especially for the punching failure, shear punching and the fracture punching. There is a modification for based on our previous study for the ultimate strength of the bridge stacks reinforced with the steel bars. In those theoretical model, two critical points. One is the effective wise to define the area of the action. Another one is how to quantify the restraint model for the bridge decks, which can be contributed by the implant stiffness of the supporting beam and the torsion stiffness of the supporting beam and the axial stiffness by the diaphragm and the continuity of the slab outside the loading area. That can be caused, all of them contribute to the restraint models. Another one for the FRP reinforced bridge decks, which is different, is one critical point is to accurately evaluate the stress level of the FRP reinforcement. How to evaluate the stress level due to the compression depths have been changed due to the action action contribution. We establish an iterative procedure to predict that. For the prediction, we have to modify the shear punching failure for the FRP reinforced concrete slabs to increase the reduction coefficient. Therefore, we can find that our prediction is compared to the other prediction method, our prediction is more accurate. Can show a good agreement between the predicted result and the test results. Finally, we can get some conclusions. The self-competing concrete can improve the bone strength and bone behavior and the tension stiffening behavior of the FRP reinforced concrete self-competing concrete. And a formula proposed by the authors to calculating the bone strength and the development length is accurate and more restricted for the service limit state of the FRP reinforced self-competing concrete is the characterized. And the self-competing experimental and theoretical investigation results indicated that the FRP reinforced self-competing deck slab have the similar behavior with those FRP reinforced normal concrete deck slab in terms of the self-competing action. Increasing the reinforcement ratio has little effect on the ultimate bearing capacity of the bridge deck slab with little restraint. The calculation of the specific calculation method of the punching bearing capacity of FRP reinforced concrete bridge deck is high conservative, especially for the current design standards. And the findings indicated that the combination of the action and the FRP and self-competing concrete can produce the low carbon footprint and durable and economic infrastructure. That is the economic one. And finally, we can introduce some perspective in our, we develop some materials for the high volume fly ash self-competing concrete. And finally, we also develop some structural health monitoring for the FRP reinforced concrete structure, especially for the larger cracking wise and the deflection. And tensile stiffening behavior is also being carried out. And another one, we develop a construction demonstration in China to apply the FRP bars in the payments of the concrete bridge access. Thank you very much.
Thank you, Professor Chen, for your excellent presentation. Since time is he used most of the time, we permit one participant to raise a question for the Professor Chen's presentation. If there,
hello, Professor Chen.
Hi.
Yeah, thank you for your presentation. Yeah, I just have a quick question for you to comment. So in your bond test, you have quite a number of different FRP bars with different surface treatment. Some with sand coating, some with different height of the ribs. So could you quickly comment on the effect of this surface treatment and your conclusion about using SSC would improve the bond? Is it valid only to a specific type of bars, or is valid to all the bars that you have tested? Thank you.
Thank you very much, Professor Yu. I think in our test, the SSC can improve the bone strength. I think especially for some sand coated surface treatment or some surface treatment without lip in the reinforcing materials. But if the reinforcing materials with some lip, I think the failure mode can be changed from the friction and chemical adhesion to the mechanical interlocking. We are developing this research currently. Yeah.
Okay, thank you.
Thank you.
Okay, thank you, Professor Zheng. And
thank you very much.
Now I will introduce our next speaker, Professor Pengcheng Jiao. Professor Pengcheng Jiao, would you please start to share your PPT, and during this process I will give an introduction to you. Professor Jiao is earned his MSc and PhD degree in civil engineering from the West Virginia University and Michigan University in the year 2012 and 2017 respectively. Prior to joining Zhejiang University, where he works now as a research professor in the year 2018. Professor Jiao was working as a postdoctoral fellow in the University of Pennsylvania. And Professor Jiao's research interests include marine mechanical materials, structure health monitoring in ocean engineering, marine software robotics, artificial intelligence in ocean engineering. He has published over 50 journal papers and delivered several invited and tailored presentations, and he was also a PI or co-PI of several projects in China. Now, Professor Jiao, you can start your presentation if you are ready.
Okay, thank you very much, and Dr. Chen. Thank you for the introduction. Again, my name is Pengcheng Jiao, and I'm from Zhejiang University. So today I'm going to talk about the high performance fiber reinforced concrete, and particularly focusing on using the FRC as a type of repairing material for normal concrete. So my talk is going to cover the following 5 parts. Let's get started with the significance and the background. So nowadays we know that smart cities is a very hot and well-known concept, which covers almost every aspect of our daily lives. And we see that many of them are directly related to structures. Therefore, to fully improve or expand the functionalities of, let's say, transportations or civil infrastructures, we have to improve the functionality of concrete. And here in these 2 figures, we see the in general, the tensile performance of concrete. And especially we see here for normal concrete. Of course, we know that it doesn't perform well under tension. Therefore, researchers have developed FRC, fiber reinforced concrete, and later high performance fiber reinforced concrete. The idea is to mix different types of fibers in those FRCs and to improve the tensile performance. Such as in these images, we see that those steel fibers are mixing in the concrete such that to hold the concrete from splitting. And in our study, we developed a type of fiber reinforced concrete using steel fibers. And here are the preparation of the casting materials. So we have different types of sands, and ICS, SF, and particularly we use those steel fibers. And after well mixing the materials in the mixer, we use the constant temperature tanks to cure our samples. And then we test and calibrate the compressive and flexure performance of the HPFRC. So in particular, we cast the samples into 2 configurations. The cylindrical configuration is for the samples under axial compression, and the beam black samples are under the 3-point bending for the flexure strength. And here are the failure modes or the failure figures for our samples. And the left part is the failure under compression. So we see that steel fibers here are holding the concrete from destroyed. And the red part is the HPFRC under 3-point bending. And again, along the crack, we see steel fibers, right? So here are the compressive and the bending results in terms of force and displacement relationship. So we see that under compression, after a very sharp dropping, we see the decreasing of the stiffness for the concrete. And here in this part, we see in general 2 types of the stiffnesses, following by the decreasing of the stiffness. And here is the stress-strain relationship based on the force displacement response. And we put the compressive and the tensile stress-strain curves together. Next, we propose to use the HPFRC as a type of repairing a material for normal concrete. So the idea is we cast and put HPFRC on top of normal concrete and apply the shear loading in mode 2 to see the debonding behavior between them. And so we first make the normal concrete and sand the surface of the concrete to increase the friction. And here is the bonding area between the NC and HPFRC. So next, we cast HPFRC on top of it. And there are 2 types of bonding strategies between the NC and HPFRC. One is directly cast HPFRC on top of it, and the other is using a type of bonding agent between the NC and HPFRC. So this is the HPFRC NC sample, and we designed this kind of a butterfly shape to make sure that the mode 2 shear loading can perfectly apply to the sample. And this is the setup of the loading machine. Okay, so here is our sample in the shear loading setup and in the debonding test. And after applying the shear loading, so we see the debonding. Those are the debonded samples. And the top 2 are the normal concrete, and the bottom 2 are the HPFRC samples. So from the debonding interface, we see that, so because the strength of the normal concrete is way less than HPFRC, so pretty much is the failure part is the normal concrete. And so here is the debonding response in terms of force and displacement relationship for the HPFRC and NC bonded using 2 types of strategies. And in case 1, we directly put HPFRC on top of NC. And case 2 is using a type of bonding agent between them. And we clearly see that by using the bonding, the glue, so the peak load, the peak force is reduced, but the debonding behavior is postponed. And here is the hardening and softening regions comparison between the HPFRC NC using different types of bonding strategies. Okay, so next, let's get into the numerical simulations to develop a numerical model using ABACUS and compare the numerical results and experimental results. So here is the numerical model that in general we have 3 parts, right? The HPFRC, the NC, and the bounding area between them. And here are the geometric and the material properties in the numerical simulation. And this is the HPFRC-NC debounding process from the initial configuration. So the collapsed boundary conditions are applied on top and bottom of the NC part. And we are applying a shear loading on top of the HPFRC part. So for the partial debounding step, we see that the HPFRC is moving in the longitudinal direction, and so the bounding region takes the force. And for the complete debounding step, we see that the HPFRC is significantly moved down, and these 2 parts are totally debounded. And here we compare the numerical and experimental results in terms of the force displacement relationship so first we compare the force displacement response for the HPFRC itself, and we see a good agreement between the numerical simulations and the experimental results. And in this part, we compared the shear debounding response between the HPFRC and NC. So again, we see good agreements between the numerical simulations and experiments. So next, let's do some parametric studies. The first, this part is the compressive stiffness that is studied in terms of the axial displacement and dilation angle. And this part is the bending stiffness study with respect to the autoplane displacement and the dilation angle. Okay, and here is a study on the maximum debounding force for the HPFRC-NC with respect to the bonding area and the initial debounding stiffness. Okay, so next, let's get into the artificial intelligence modeling part for the HPFRC-NC. And I think the very first question is why we need to develop such an AI model for the concrete. I think the reasons are the concrete are expensive. They are time-consuming to make, and there are many reasons to affect the experimental results of the concrete, especially in the kind of complicated shapes. So by using artificial intelligence techniques, we hope to be able to accurately predict the bonding or debonding performance of the HPFRC-NC, and also can help us do inverse design. And so to investigate our HPFRC-NC sample, we define a total of 9 input variables. 4 of them are based on the geometries, and 4 of them are about the material. And the 9th is about the bonding area. And the output variable is the shear strength. So the relationship could be something like this. So we have 4 geometries, 4 material, and 1 about the bonding area. So we particularly use genetic programming in artificial intelligence to develop the AI model, because genetic programming allows us to have a clear relationship between the input variables and the output objective variable, which is different from the, let's say, numerical machine learning, deep learning, those kind of black box algorithms. Here are the expression trees in the GP model, and eventually we end up with this expression between the 9 input variables and shares strength. Okay, so here is the validation of the model. So we compare the models, we compare the GP model with the experiments, and we see that the predicted share strength and the measured share strength, they match each other pretty well. Okay, and here is a quick sensitivity analysis regarding based on the GP model, and according to the results, we see that okay, the height of the bonding area is playing a significant role on the debonding performance of the HP FRC NC, and other than this, the material properties of the normal concrete are important to the debonding behavior, and also the surface, the bonding area. Okay, so in the very last part, I'd like to give some quick discussions on the high performance concrete. So other than using a fiber ring of steel fibers to improve the debonding or to improve the tensile performance of the concrete, we are also using some waste materials, which can be defined as a type of sustainable concrete, right? So we are particularly studying the engineering cementitious composites, and also the alumina refinery recycle-based concrete. And the studies are still ongoing, and we hope to publish the results soon. So for the conclusions of my talk, so I first presented the HPFRC enhanced by steel fibers, and in the experiments, I talked about the calibration of the compressive and the flexor strength for the HPFRC. And next, I talked about using HPFRC as a repairing material for normal concrete, and studied the mode 2 shear debonding. And I also developed a numerical model and artificial intelligence model to study and predict the debonding performance.
Would you please speed up a little bit because the time is up?
Okay. Okay. And so the very last, I quick talked about HPC using waste materials. So that's all. Thank you very much. Thank you for your attention.
And there was a question raised from the audience. I will raise it. I will I will transfer this question to you. You can answer it. Okay.
Okay.
I also have the similar question. Can you would you please share more details on the contactor properties of your simulation? Also, I have a similar question. What is the profile of your concrete when you do the strengthening? I think the profile of the concrete to be strengthened may have a considerable effect on the strengthening effect.
So you're talking about the geometric properties and material properties of the numerical model, right? The properties that we used for the HP, FRC, and NC in the numerical modeling. And right, and here is the debonding process.
So you the contact surface, in particular the concrete surface, the normal concrete surface to be stressed, is it smooth or have some rough surface or something else?
Okay, so in the experiments, so we did sand the surface to improve the bonding performance, but in the numerical simulations, it's smooth. And we only, if we go back, so we only model the concrete in 3 parts. And for the normal concrete, it has a smooth surface, which we used a tie constraint between the surface, this surface of concrete, and the bonding area, or the glue, the materials of glue.
Okay. So I think the participant who raised this question may discuss with Professor Zhao later, personally, because the time schedule. And now we thank you, Professor Zhao, for your presentation, and we will now go to the next speaker. Thank you.
Thank you.
Our next speaker is Dr. Chanri Guo. Is Dr. Guo there?
Yeah, I'm here.
I think you can now share your PPT, and during this process, I will give a brief introduction to you. Dr. Guo received his bachelor degree in engineering mechanics from the Central South University, China, and also he received his master's degree in the same university in the year 2014, and later he obtained his PhD degree from the Missouri University of Science and Technology, USA, in the year 2019, just the year before last year. Before joining, he now is a research assistant professor in PolyU. Before joining PolyU, he was a postdoctoral fellow in the Missouri University of Science and Technology. His research interests include laser-aided fiber grating, optical fiber sensor, two-dimensional nanomaterials synthesis and characterizations. And without further ado, Dr. Guo, you can start your presentation now.
Okay, thank you, Professor Chen, for your introduction. Good afternoon, everyone. My name is Guo Chanri. I'm a research assistant professor in Civil and Environmental Engineering Department in PolyU. Today, I'm going to talk about the graphene silver nanowire-coated LPFG sensor with the electroplated FEC layer for ultra-sensitive corrosion monitoring. And the similar techniques or the methodologies can be also used for future durability-related chemical parameter monitoring in the seawater, seas, and concrete. And I'm going to talk about the LPFG theory and fabrication, and LPFG for the strain, temperature, and refractive index sensing, and the LPFG-based corrosion sensor and pH sensor. So long period fiber grating belongs to the fiber grating category for sensing and signal processing. The fiber grating means we periodically modulate the refractive index of the fiber core. One type of the fiber grating sensor we use a lot is the FBG, the fiber break grating. So for the FBG, the grating period usually is less than 1 micrometer. And with this grating, if we have a instant light, we will have a reflected signal with a specific wavelength. We call it break wavelength, and it's related to the refractive index of the grating and the grating period. And if we want to use the FBG for strain and temperature sensing, that means when we have a strain or temperature-reduced fiber deformation, we will have the grating period changed. And in this case, the reflected signal or the break wavelength will shift according to the temperature or strain. That's how we use the FBG. For the long period fiber grating, the long period is related to the FBG. That means the grating period is longer than the FBG. It's usually in several hundred micrometers. And with this longer period grating, we will have a mode coupling effect. That means part of the incoming light, the energy will couple into the cladding and then dissipate into the surrounding medium. So if we focus on the outcoming light or the transmission spectrum of the LPFG, we can see several peaks like this, and we call it resonant wavelength. And this wavelength is determined by the refractive index of the surrounding medium and also the grating period. So similar to the FBG, since the grating period will change with strain and temperature effect, we can still use the LPFG to do the strain and temperature sensing. But another unique property of this LPFG is we can monitor the refractive index of the surrounding medium. This is the property that the FBG does not have. Commonly used method is the CO2 laser point-by-point fabrication. And here is the CO2 laser grating system. And we assemble this system in poly-U. And here we can see the grating process. We have the laser exposure on the fiber. And then we can see the real-time transmission spectrum on the OSA here. As you can see with more grating points, and we can see the transmission spectrum of this LPFG. And this entire system includes the CO2 laser, the beam delivery system, the controller, the linear stage, which we can control the grating period, and we have the LED source and the OSA to get the transmission spectrum of the LPFG sensor. For the application based on the grating period, we can use the LPFG to do the strain, temperature, and pressure sensing. And based on the refractive index of the surrounding medium, we can do the pH, liquid level, corrosion, and we can also use LPFG to monitor the chloride, sulfate combination of the seawater sea-sand concrete. Here are two simple examples of the refractive index sensing of the LPFG sensor. The red curve is the LPFG sensor in air, and the blue curve is the sensor in water. So from air to water, the refractive index changes from 1 to 1.33. So we can see the resonant wavelength has about an 8 nanometer shift from the air to water. And this illustrates how we use the LPFG to do the refractive index sensing. Another example is with different sodium chloride concentration, we can also have this wavelength shift. And from 0 to 4 nanometer, and the sodium chloride concentration changes from 0 to 14%. So this is another potential application of the LPFG sensor for chloride sensing. And another application is the strain sensing. This is similar to the FBG sensor. We put the sensor on the rebar with the epoxy, and by modulate the grating period, we can have two different modes of the LPFG sensor. And these two different modes have different sensitivities. As you can see here, the LP6, LP7, we have two different sensitivities for the strain measurement. And similarly, we can also do the temperature sensing with these two different modes, and it also has the different sensitivities. So with these two different sensitivities of the LP modes, if we put these two sensors parallel or in series, we can simultaneously measure the strain and temperature. Because we have the different sensitivities of the LP6, LP7 modes, we can decouple the temperature and the strain effect. So this is the temperature and strain measurement of the LPFG sensor. Another thing is the FEC-coated LPFG sensor for the corrosion-induced mass loss measurement. And here we first define the mass loss as a direct parameter for the corrosion monitoring. We define the corrosion-induced mass loss, the lowercase m, over the original total mass, capitalized M, as the mass loss ratio. And the advantage of this mass loss parameter is it can directly correlate it with the corrosion process. Because previously we used the corrosion-induced strain or stress to quantify the corrosion process. It's a indirect parameter. But with this mass loss parameter, it's a direct parameter, and we can provide definitive information to the engineers, and it will not be affected by other factors. And to monitor the mass loss, we use a FEC-coated corrosion sensor. The FEC is the iron carbon nanoparticle layer, and it has the same chemical component ratio as the steel rebar. And we use the electroplating method to coat the FEC layer on the optic fiber. To do this, we need to make the fiber surface conductive. That means we need a conductive layer for the electroplating purpose. And we also want this conductive layer to be transparent because we want the sensor has higher sensitivity. So we choose the graphene as the conductive and transparent material. The reason is graphene is a allotrope of the carbon element, and it has unique properties like the high stiffness, it's conductive, it's optical transparent. And for the graphene material, recently it received more attention due to its unique properties. It has many applications, such as the wearable device, the bionic skin sensor and actuator application, and other like the flexible electrode, other applications. And there are many methods to synthesize the graphene material, and we use the low pressure chemical vapor deposition method, the LPCVD method. And we will have two LPCVD systems in PolyU, probably in March this year. The fundamental theory of this LPCVD device is we have this high temperature furnace, and we put the copper foil as a catalyst into the furnace. Once we have this methane, the CH4, as the carbon source flow into the furnace, it will decompose into carbon and hydrogen, and the carbon atom will deposit on the copper surface, and we will have this graphene layer. Here shows the fabrication procedure of this corrosion sensor. So first, we have the graphene grown on the copper surface. We will use the PMMA, a polymer, to transfer the graphene layer onto the fiber surface, and then we do the electroplating to have this FEC layer on the LPFG. We use another group of silver layer-based sensor for comparison. For the graphene-based sensor, we also add some silver nanowire to enhance the graphene conductivity. And here we can see some pictures of the sensor fabrication. Here is the graphene on the copper, And here is the graphene PMMA layer, and you can see it's transparent. And we transfer the graphene layer on the fiber surface. We do the electroplating, and finally we can have this black color FEC coating on the sensor. These are some SEM images. We can see the silver nanowire on the graphene, and we can see the FEC layer surface. And we can also see the silver layer coated optic fiber before and after corrosion of the sensor surface. And here is the results about the 72 hours corrosion test. And we can see the graphene-based sensor has much higher sensitivity compared to the silver-based sensor. And finally, we have this wavelength shift versus the mass loss of the FEC layer. And again, we can see the graphene-based sensor has a much more higher sensitivity. So even though this part of work is more focused on the corrosion process of the FEC or the steel rebar, but we believe the similar technology can be used for the chloride or sulfate ion penetration and for the seawater sea-sand concrete for the long-term durability monitoring. And another sensor we developed based on the LPFG is the carbon nanotube wrapped or coated LPFG sensor for the pH sensing. And this part of work was done by our the postdoc, Dr. Ding Siqi in our group. So in this work, we put the PEI and PA polymer together with the carbon nanotube. We coated this layer by layer structure on the LPFG. And we changed the pH value from 2 to 13. And from this transmission intensity change, we can see it has a very good response between the transmission of the LPFG sensor and different pH values. So we can use this sensor for the pH value monitoring in the seawater sea-sand concrete. There are several other issues we investigated for the LPFG application. First one is we want to investigate what's the maximum number of LPFG sensors we can use in one loop. Because we know for the LPFG sensor, we need to have an input and output for a fiber loop. So here we put 6 LPFG sensors in series in one loop. And here we can see the total wavelength width is about 140 nanometers.
Paul, please speed up a little bit because the time is up.
Okay. So if we have a 16 channels of the interrogator, that means at the same time, we can have 48 LPFG sensors in the sensing network. Another one is we combine them together. That means in one fiber loop, we can sensor. This technology has the potential application in the bonding strength, bonding measurement in the seawater, sea-sand concrete. And last part is in this month, we will put the humidity sensor at the field exposure site near the Hong Kong-Zhuhai-Macau Bridge. And we will implement the humidity sensors, and we will use the 4G connection to remotely get the data in PolyU. So in the future, if you want to get the data or you want to install your sensor at the bridge, you can talk to us and we can collaborate. So for conclusion, we developed the CO2 laser grating system for LPFG fabrication, and we developed the corrosion sensor, pH sensor based on the long period fiber grating. And we also investigated the multiplex sensing and the integrated sensing with the BOTDA. And in the future, we will develop the LPFG-based sensor for chloride, sulfate, and carbonation monitoring in the seawater, sea-sand concrete. And we also will investigate the mechanism of this ion penetration process and more sensors will be implemented at the Hong Kong-Zhuhai-Macau Bridge exposure test set. So this is all the material I want to share, and I will take your questions. Thank you.
Thank you, Dr. Guo, for your excellent presentation. There was a question raised from the participant. I will read it to you. How to ensure the long-term stability of the FE-C coated LPFG? The question, he said that the coating is proto-pinion from the bare LPFG. What kind of special barrel you have taken to use? You have used in your fabrication?
Okay, so for the long-term stability, it depends on the coating method and the coating material used. For our electroplating method, the FEC layer is pretty much very stable during the entire test. But for the institute test, the institute application in concrete, we will use other steel tubes to protect the LPFG sensor. And actually, we have one journal paper submitted, and right now is still under review. And with this steel tube, we can protect the FEC-coated LPFG, and it can monitor an even longer time for the corrosion measurement.
Okay, thank you. I think you can contact with Dr. Guo for further discussion and communication. And for the time issue, I will close his presentation. Thank you again for Dr. Guo for your presentation. And then now I will introduce the next speaker, Dr. Feng Ran. Are you there? I think you can now start sharing your PPT. I will during this process I will give a brief introduction to you. Dr. Feng Ran is now an associate professor at the Harbin University of Technology, Shenzhen, China. He also gets some titles such as the Peacock Plane of Shenzhen. He is also a member of a number of technical committees, such as the subcommittee of the Construction Metal Society China, and also the member of Association for Steel Concrete Composite Structure and the China Steel Construction Society, and so on. And Dr. Feng Ran research interests are high performance steel structure, steel concrete composite structure, repairing and strengthening of reinforced concrete structure and steel structures. He now has published more than 60 SI papers and have applied and got 7 Chinese patents. Now, please start to present if you are ready, Dr. Feng. You can start now, Dr. Feng Ran. Dr. Feng, you can now start present. I think we cannot hear you. I will contact him personally.哎，冯老师，你这个我们听不到啊，你开始做报告了没有？ Hello, can you hear me? Yeah, I think you can start if you are ready. Okay, thank you. Share your screen first. Yeah, so sorry for the technical problems. And thanks for Professor Guangming Chen for one nice introduction. My topic today is the flexible behavior of the CFRCM strengthened corroded reinforced concrete continuous beams. And this topic mainly includes the following parts: introduction, experimental work, fundamental analysis, design rules, and following by the final conclusions of some future work. First, the introduction. And the corrosion of the steel bars has nowadays become a serious threat to the durability of reinforced concrete structures, especially in coastal environment, being susceptible to the chloride erosion. The deterioration of the reinforced concrete structures caused by the corrosion of the reinforcement not only result in tremendous economic loss, but also possess a potential danger to the engineering structures, which also seriously strengthen the life safety of the human beings. The impulse current cathodic protection technique is the electrochemical anti-corrosion technique for the cathodic polarization to reduce or prevent oxidation of the metals. So the reinforced bars can be used as the cathode material, and applied current is input to suppress the electrochemical corrosion of the reinforcing bars with applying ICP technique to the IC structure subject to the chloride salt erosion, so that the surface of the reinforcing bars produce a passive film and reduce the content of chloride. To some extent, protects the steel bars from the corrosion. However, there are some limitations for this technique due to its expensive anode material. It cannot repair or enhance load carrying capacity. So in order to restore or improve the bearing capacity of the structure, it is necessary to implement the structure strengthening on structure with durability problems. The fiber composite reinforcing method was widely employed by using the fiber reinforced polymer for structure strengthening in practical applications. Well, the epoxy resin engine is normally used for the bending fiber as a supplementary, which, however, have some limitations I presented here. And so, in order to overcome all these shortcomings for the epoxy resin impregnated fiber reinforced polymer in the rehabilitation of damaged IC structures, the fabric reinforced cementitious matrix composites were developed as a feasible alternative for structure strengthening. It was noting that the cementitious matrix is used in FRCM as the bending material instead of the epoxy resin in FRP for bending fiber, which not only overcomes the aforementioned drawbacks here, but also has such better compatibility with concrete substrate and long-term durability. However, the structure strengthening technique also has some limitations, which presented here. It cannot repair or improve the corrosion resistance. So an innovative dual-functional rehabilitation system was developed by combining the ICP and the SS techniques together. In these systems, the carbon fiber mesh will be used as the anode due to these advantages. On the other hand, the cementitious matrix also used as the binder owing to these advantages. So we get the CFRCM, which have the high alkaline resistance and the long-term durability. The dual function of CFRCM include the capability of repairing or improving the corrosion resistance and the compatibility of repairing or enhance the load carrying capacity. And based on this idea, a research group of Professor Jihua Zhu from Shenzhen University, who make a presentation this morning, first developed the ICCP-SS technique by conducting a series of tests to investigate the strength and durability of CFRP and the degradation and the acidification of the anode interface after polarization, and which was eventually validated to be technically feasible and efficient. So after that, our research group from the Harbin Institute of Technology in Shenzhen campus were also quite interested in this topic and joined this project by conducting a series of research on the behavior of the corroded reinforced concrete beams and columns rehabilitated by ICCP-SS technique. So this is the background of the research I presented here. So in this study, the flexible behavior of both uncorroded and corroded RC continuous beams strengthened by CFRCM
plate will be experimentally and numerically investigated. The effects of the CF mesh layer, the U-shaped wrapping layer, and the degree of corrosion of reinforcing bars on the bending capacity of RC beams are investigated. Now let's talk about the experimental work. And the CFRCM composite were prefabricated in this study to facilitate the efficient strengthening of the RC beams. This is the procedures in details for the prefabrication procedure. Next, the ICCP procedure. A stainless steel plate was designated as the cathode of the circuit. So the CF mesh was connected to the positive polar of the external power supply to guarantee that the CF mesh was fully electrified. Steel connection plates were employed to be closely tied to the extended regions of the CF mesh out of the cementitious matrix. The system continuously operated for 19 days. So the electrified solution continuously provided the chloride attack to the CF mesh and the cementitious matrix interface of the composite during the ICCP procedure. So the compressive test was conducted on concrete cubes to obtain material properties. And the tensile tests were also conducted on steel bar and a single bundle of the carbon fiber to obtain nanomaterial properties, and the compressive and the flexible strength of the cementitious matrix, as well as the CFRCM composite obtained from the material tests accordingly. And the material properties of a concrete steel bar and the carbon fabric meshes and the cementitious matrix and the CFRCM composites are summarized in this table. A total of the 10 RC2 equal span continuous beams with the same cross-section dimensions are tested. One half of the specimens were uncorroded RC beams, and the other half of the specimens were corroded RC beams. In both the uncorroded and corroded specimens, the one unstrengthened RC beams was designed as the control specimen. The other two were designed strengthened by different layers of the CFRCM plates and to evaluate the influence of different layers of carbon fabric meshes. The remaining two were further strengthened by U-shaped ramping to assess the influence of the end anchorage. The details of the beam specimens designed in the experimental investigation are presented here. The finished CFRCM plates were employed to strengthen the flexural capacity of RC continuous beams, which were positioned at the top and the bottom flanges of the RC continuous beams to cover the potential hogging and the second moment area, respectively. Furthermore, some specimens were further strengthened by the U-shaped ramping for CFRCM plate as the end anchorage. And it is worth noting that locations that were strengthening CFRCM plates and the U-shaped ramping were sandblasted to a certain degree prior to the strengthening to remove the smooth outer layer of the concrete. And then the location of the strengthening CFRCM plates and the U-shaped ramping were water saturated prior to strengthening to enhance the bond behavior of the cementitious matrix on the concrete substrate. And this is a test setup. As usual, we use the compression force was applied by using a spread beam on the spread beam to each middle span of the RC continuous beams, and we also use the load cell to report the applied load, and some inclinator used to obtain the implicate rotations during the test, and some LVDTs also used to capture the vertical deflections during the test of the middle span. And some strain gauges specific to the concrete as well as the steel bars were used to obtain the strain distributions and the in-plane bending. And the displacement control was used to drive the hydraulic actuator during the test. So let's talk about the failure modes. A total of the 4 typical failure modes were observed from the flexural test. And the first failure mode is the conventional flexural failure, which was initiated by the yielding of the tensile rebars, followed by the crushing of the concrete at both the middle support and each middle span of the RC2 equal span continuous beams. The second failure mode is the slippage. of the common fabric meshes within the cementitious matrix, which generally occurred at the middle support of all strengthened specimens and the middle span of all strengthened specimens with U-shaped ramping as the end anchorage. The third failure mode is the depending of the CFRCM for the concrete substrate, which generally occurred at both middle support and each middle span of all strengthened specimens. And the fourth failure mode is the fracture of the U-shaped ramping, which occurred at the span of RC continuous beam strengthened by 3 layers of CFRCM plates. It was noting that the failure mode of the control specimens of unstrengthened RC beams was conventional flexural failure only, while the failure mode of the strengthened RC beams were complex, which combined the different typical failure modes. Now, let's talk about the test results. The flexural capacity, including the cracking loads, the yielding loads at both middle support and each middle span, and the ultimate loads of all specimens are listed in this table. It is found that the enhancement of the ultimate load of uncorroded RC beams strengthened by 3 layers of the CFRCM plate was smaller than that of the counterparts strengthened by 2 layers of the CFRCM plate, which may attribute to the failure mode of the debonding of the CFRCM from the concrete substrate occurred at the middle support of the uncorroded RC beams. It is also found that the enhancement of the ultimate load of the corroded RC beam strengthened by the 3 layers of the CFRCM plate was also smaller than that of the counterparts strengthened by 2 layers of the CFRCM plate due to the same reason. And the redistribution of the bending moment usually occurred for RC continuous beams subject to the development of the plastic hinges, which exhibited the flexure and deformation capacities of the RC continuous beams. In this study, the redistribution of the bending moment was calculated at the middle support for the hogging moment and at each middle span for the sagging moment based on the redistribution ratio of the bending moment and the ultimate load. And it is shown from comparison that the redistribution ratios of the bending moment of control specimens of unstrengthened RC beams at both middle support and each middle span was larger than those of the strengthened counterparts. It indicates that the strengthened CFRCM plates weaken the deformation capacities and development of the plastic hinges of the RC continuous beams due to the brittle characteristics of the CF carbon fiber, which eventually deteriorated the redistribution of the bending moment of the strengthened RC beams. The applied load varies the vertical deflection curves at each middle span of the RC continuous beams are plotted here for both uncorroded and corroded specimens. It is shown that the load deflection curves of all specimens generally consisted of the pre-cracking and post-cracking of concrete as well as the pre-yielding and post-yielding of the steel bar. It is shown from the comparison that the ductility of the control specimens of unstrengthened RC beams was usually the best, and in which the ductility of uncorroded RC beams was much better than the corroded counterpart. It is also found that the strengthening CFRCM plates weakened the ductility of the strengthened RC beams, in particular for the specimens with more layers of the carbon fabric meshes, which may attribute to the brittle characteristics of carbon fibers. Now is talk about the phenomenon analysis.
Dr. Feng, you already used out your scheduled time, but since the next speaker will not present due to the technical problem, you can present 5 more minutes. Okay.
Okay. Thank you. And now the phenomenon program called DANA was used in this study to conduct 3D nonlinear phenomenon models, phenomenon analysis of specimens. It can accurately simulate the whole process of RC structures from the initial stage, the cracks development, to the final structural damage. In the simulation process, the actual geometry of the structure, the material properties of the steel bars, CFRP and the concrete, the intention and compression are considered. So a total of the 10 phenomenon models including the 1 uncorroded beams, 4 uncorroded beams with reinforcement, and 1 corroded beams, and 4 corroded beams with reinforcement are established and analyzed. And we can get the verification of the phenomenon models by comparing the ultimate loads. Its table shows the comparison. It's easy to know that the test results are close to the FEA results. What's more, the ultimate moment obtained from the test are in good agreement with the rows determined by the FEA. This is the verification of the moment redistribution. The comparison show that the numerical analysis also provides relatively accurate estimation of moment redistribution values. The failure mode of 10 beams obtained from tests are compared with rows in numerical analysis. We can see that the cracks simulated by the FEA are in good agreement with the test results. So, the validated failure models were used to carry out the parametric study. A total of 16 numerical models are supplemented. So this table include 10 validated failure models and 16 supplementary models. And the layers of the safe mesh are displayed by zoom in since the membrane element is taken to the U-shaped ramping. The different layers of U-shaped ramping are identified by the color of the mesh. This is the numerical results. I'm not going to go through its detail due to time limits. Next, the design rules. The common design rules include the ACI 440 code and the ACI 459 and the AC code and the FRP Bulletin 14 and the CECS Chinese code, in which these two failure modes these two design codes are applicable to the FRCM system, and while the other three design guidelines are specific to the FRP system. And it is assumed the bonding behavior between the CFRCM and the concrete substrate remains effective for CFRCM strengthened and RC members in these two design codes, where there's no relative link between the carbon fabric meshes and the concrete substrate for CFRP strengthened RC members in other three design guidelines. So the experimental ultimate bending moments are compared with the design flexural strengths calculated using design formula given in the current design codes for both experimental work as well as the failure analysis. And as you can see, that all the design codes, the current design guidelines are all conservative for the flexural strengths of RCM strengthened RC continuous beams, and it is easy to find. It is easy to find the bend capacities calculated by FRP Bulletin 14 is relatively conservative. So, in order to obtain more accurate bending capacity results, the formula of the FRP Bulletin 14 is revised by multiplying the correction coefficients. We propose new design equations preliminary and compare test results. We found that the proposed design formula is comparatively more accurate. Then let's come to the conclusions. I'm not going to go through every single conclusions in details which have been presented previously in my presentation. And some papers also have published based on this research. And I also would like to take this opportunity to thank the financial support from the key area research and development program in Guangdong province and some other research fundings, and the great efforts from the members of our research group, including one postdoc and the 3 PhD students, are gratefully acknowledged. And some other future work I wanted to talk is that some other research work will be conducted on the behavior of the corroded reinforced concrete beams and columns subject to the different loading cases rehabilitated by ICP SS technique. And furthermore, we also would like to conduct research on the key technology of the seawater sea sand concrete structures based on the ICCP SS CFRP composite materials, financially supported by the key area research and development program of Guangdong province. In this project, the lateral seawater and sea sand from the ocean in Guangdong province will be used to cast concrete, which will be employed together with the ICCP SS CFRP composite to develop the new structure members. That will be totally different from the research presented previously for existing corroded reinforced concrete structure members and rehabilitated by the ICCP SS technique. A theoretical model is expected to develop for better prediction of the structure behavior. The last but not least is that more accurate and efficient phenomenon models will be developed for beams and columns to seriously consider the interface behavior between the carbon fiber mesh and the cementation matrix, as well as the cementation matrix and the concrete substrate. With that, I can conclude my presentation. Thank you for your kind attention.
Okay, thank you, Dr. Feng, for your excellent presentation. Now, let me make an announcement first on behalf of the chair of the workshop, Professor Yu Tao. The last speaker of this session, Dr. Shaoqin Yuan, will not attend this, will not deliver his presentation because of the technical problem. So we will have a break next and start again at 4 p.m. as scheduled for the next session. But now we still have some time left since the next speaker gave up his presentation, although Dr. Ran has already used 10 more minutes. We still have 20 minutes. So please raise your question on Dr. Feng Yuan's presentation. Also, you can raise questions on other presenters in these sessions.
Okay, Dr. Feng.
Okay, Professor Yu.
Yeah, thank you for your presentation. It's a very comprehensive study. So I just have a small question on your finite element modeling. So in your models, you simulated corroded steel bars, right?
Yeah.
So I just want to know how you consider the effect of corrosion on the bond slip behavior between the steel and concrete. Could you elaborate a little bit on that?
Okay, you want to know the bonding behavior between the corroded steel bars with the concrete. And I'm sorry to say that this work is done conducted by me. It's conducted by my PhD student. As far as I know, it didn't seriously consider the bonding behavior in his finite models. That is why I mentioned in my last slide that the more efficient and accurate concrete models will be developed in the future to consider this seriously. So because that is the preliminary study nowadays.
Okay, thank you.
I would like to ask a question. If there are no other question from the participants at the moment, I will raise a question. I noticed that to apply this so-called ISS.
SSC, yeah.
Yeah. So you need a power to supply the electricity, right?
Yeah.
So I'm wondering, I'm not challenging you technology, okay? I think this is a very good and promising technology in the future, but I'm thinking about how to practice this technology, because you needed to provide electricity at the on site, on the construction site during the service life of the structures. So how can you do that? Did you ever think about this?
You mean the serviceability of these ICP-SS technique systems in ocean area?
No. I'm just where you always you provided the power consistent.
Yes, it's the power supply. Yeah, we need to install the power supplies to provide the electricity and to operate the ICP. So your question is how is the serviceability of this system, right?
Not the serviceability. I'm not questioning your serviceability. I'm just wondering how will you apply this? Because if you supply the power to a member, maybe is there any danger to use if there was some person who don't know
I see.
The structure, yeah. And also the energy consumption and the cost issue. Can you give some discussion on this?
Okay. Firstly, for the safety of the human being, I don't think this is a problem, because the current density is quite small. Nowadays, it's limited to 200 million. It's quite small. The current density, it will not hurt anybody touch these members. As well as for the energy consumption also quite small. It's not the industrial. It's not an industrial. How to say it? based on our knowledge up to now, I don't think the energy consumption will be the problems in the future use.
How will you protect the wires, the electronic wires connecting to the structures during the service life of the structures? Maybe if in the field, in a village area, maybe some villager will come to cut that wire away.
Okay, cut the wire away. Okay. That will, I must not admit, that will be a problem. We have to protect it by ourselves. If you cut, and definitely will be out of service.
Just propose a discussion. Never want to question.
I fully understand. All these issues have to be considered, I think, in our future plans to do it in the real, in the practical applications. How to handle these issues? I think we will seriously consider all these issues carefully.
Why I raise this question? Because we just have a new project looking at the structure, and we are doing a monitoring on the structures, and to provide power to the monitoring system is a problem, a challenge for us if you want to monitor that structure for a long time, and also that will be an issue for you maybe.
Okay. Maybe we need to use this, the techniques for the structural health monitoring to supervise our to monitor our members in time.
No, not the monitoring. How to provide the power in a long run, in a long term, will be an issue to be considered for you.
I think we need to replace it in the long run. We need to replace it because it also we also will be out of energy during some time. Then we need to replace it.
Okay. Is there any question from other researcher or participant?
Can I add some points? I mean, related to the discussion just we have. Even I'm not a real expert for the cathodic protection, but ICCP has been used quite widely in many practical applications. And in some cases, very severe corrosive environment, probably ICCP is only the way to prevent further corrosion. So I think ICCP itself, it's a well-developed technology already. This is my understanding. But the usual ICCP, they use the much more expensive material, which is titanium. Then compared with titanium, carbon is much cheaper. That is also another advantage of our ICCP SES. Yeah, this is something additional comment. Thank you.
Okay. Thank you, Professor Tamon.
Yeah.
Is there any other questions? If there is no, if any, I will repeat this again. Is there any other questions? If there is no further question, I will just end this session. And the next session will start at 4 p.m. as scheduled. Thank you for your attendance.
Okay.
Thank
you, Professor Yu. Okay. And
下一个 section 就4点钟准时开始啊，按计划中文重复一遍。谢谢大家参与，我就退出了。我这次参与，我就不当 chair 了。
Okay, thank you, Guangming. So as Guangming has announced, we will start again at 4 p.m. So we'll have a short break now. Thank you.
Oh, sorry. There seems like a bit of technical problem. Give us a second.
Good morning. I am Nele de Bailey from Ghent University in Belgium, and it is my pleasure to present on this fourth Seawater workshop. The presentation will deal with multi-ion degradation of concrete structures in seawater, including effects of cracking and self-healing. Well, as you all know, structures in marine environments are exposed to aggressive conditions, and much of our important infrastructure is made of concrete, such as bridges, locks, wharves, piers, tunnels. So there is a lot of concrete damage reported for these structures, and they need a lot of repair annually. Several years ago, Matthias Maas, one of my PhD students, has focused especially on the degradation of concrete in marine environment, and he has studied the influence of chlorides on sulfate attack and vice versa. Because when you want to know the real degradation in realistic conditions, you have to take the different types of ions in seawater into account: chlorides, sulfates, magnesium, and so on. Furthermore, concrete is a material with a pretty low tensile strength, and often cracks are present, which will accelerate degradation. So a solution for this could be the newly developed material of self-healing concrete. So in this research, we will be looking into combined attack mechanisms, sulfate combined with chlorides, for different concrete or mortar mixtures, with as main binders Portland cement and blast furnace slag cement. So this mix design will have an effect on the service life, as will the presence of cracks have, and if the samples would autogenously or autonomously heal. We will also look at the immersion conditions, being cyclic or continuous. So the mortar mixes used in this research consisted either of Portland cement as a binder, being an ordinary Portland cement or a high sulfate resistant material, and then a third mix contained a blast furnace slag, with the slag over binder ratio being 50%. For sake of completeness, the chemical composition of the different binders is shown here. And of course, you will notice that for the high sulfate resistant cement type, there is a lower tricalcium aluminate content. So in the presentation, I will first focus on the combined attack mechanisms in seawater environment, first of all considering the effect of chlorides on sulfate attack. Sulfate attack may be either sodium or magnesium sulfate attack. Sulfates do degrade the concrete in a direct way by the formation of expansive reaction products. This can be etrangite, gypsum, or thaumasite. Furthermore, if magnesium is involved, other reaction products like brucite or magnesium silicate hydrates may occur. If we want to test which reaction products are formed, we will use XRD combined with Rietveld refinement. And furthermore, to monitor the degradation, I will show results of mass change and length change measurements. As you know, sulfates with their expansive reaction products will result in an expansion of the mortar, and then there will also be, or there can also be, a crumbling of the cement matrix. To simulate different temperatures, we have performed tests at 20 degrees as well as at 5 degrees Celsius, 5 degrees being more representative for instance, the North Sea climate. And solutions of both sodium sulfate and magnesium sulfate will be tested at the concentrations mentioned here. So let's first look at some results of sodium sulfate attack. So this is the mass change of sample. It takes quite some time to see a real degradation. But then after a year, it really takes off. And for the Portland cement based samples, you reach a pretty high degradation with a mass change of nearly 30% after 600 days. Whereas for the samples containing either blast furnace slag or a high sulfate resistant Portland cement, the mass change is really limited. On the other hand, when you would add to this sodium sulfate solution also sodium chloride, you notice that barely any mass change happens over the same time period. Also not for the Portland cement based samples. So the samples also visually look quite intact after this degradation time. How can this be explained? Well, it is clear that there is a reciprocal influence between the sulfates and the chlorides, since they both compete to bind with the tricalcium aluminate to form either ettringite for the sulfates or Friedel salt for the chlorides. This can be clearly seen from the XRD prints, where you see in the reference solution containing only sulfate, only the presence of ettringite and gypsum, whereas if also chlorides are present, you see the peaks of Friedel salt appearing as well. If you analyze this more quantitatively using Rietveld refinement, it is clear that by adding the sodium chloride, there is a huge reduction in the amounts of gypsum and ettringite in comparison with a pure sodium sulfate solution. On the other hand, here you have the appearance of the Friedel salt. So the presence of chloride seems to have a positive influence on the resistance of PC mortar against sodium sulfate attack because of this binding competition between the ions. On the other hand, the chlorides have barely no influence on sodium sulfate attack in HSR or blast furnace slag mortar. When we now move to magnesium sulfate attack at 20 degrees, we can look again at the images of the mass change over time in a magnesium sulfate solution for our different mortar types. So it is clear that for the Portland cement-based binder, the degradation remains quite limited in this case as well. However, in this case, if you add sodium chloride, there is a clear increase this time for the samples with 50% blast furnace slag, as you can also see here visually. So addition of chloride aggravates the degradation of the samples with blast furnace slag. If we carry out the same experiments at a temperature of 5 degrees, not too much changes in a pure magnesium sulfate solution. However, with the addition of sodium chloride, all samples now show a more intensive degradation. Although for the ones with slag, it's now more limited than in the previous case at a higher temperature. How can we explain this? Well, the magnesium present has specific reaction products. There is formation of brucite, which can form an insoluble surface layer, which will reduce the penetration of sulfates into the matrix. However, this brucite layer is less present on the mortars with blast furnace slag, since they have initially less portlandite in the matrix to lead to brucite formation. Additionally, reaction products like magnesium silicate hydrates may form, which will lead to a decomposition of the calcium silicate hydrates, which provide strength to the mortar. At low temperatures, in addition, we can have the effect of thaumasite formation, which negatively influences the microstructure. So actually, the effect of chlorides on magnesium sulfate attack is both temperature and binder dependent. At 20 degrees, there seems to be no effect of chlorides on the degradation due to magnesium sulfate in PC and HSR mixtures, whereas there is a negative effect for the slag mixtures. This is due to an increased decomposition of the CSH to magnesium silicate hydrates by absence of this protecting brucite layer. On the other hand, at 5 degrees, the degradation is intensified regardless of the binder type. And one of the reasons is the increased thaumasite formation, especially in combined solutions with both sulfates and chlorides. Okay, we have considered the effect of chlorides on sulfate attack, but we can also consider, on the other hand, the effect of sulfates on chloride ingress. Chlorides have an indirect effect on concrete degradation due to their contribution to the corrosion of the reinforcement steel. We will consider chloride penetration tests by diffusion, which mainly follow the Fick's law, which will allow us then in the end to do also some service life predictions. Chloride binding will also be important, since this can lead to Friedel salt formation and less flea-free chlorides, which would then lead to rebar corrosion. We have been using different types of test solutions, either with a high concentration of sodium chloride, like you can find in standardized tests, or a lower concentration, which is more representative for the real conditions in the North Sea. The chloride to sulfate ratio was taken between 3 and 5.4. The chloride profiles can be determined by collecting powder layer by layer by grinding, water or acid extraction, and then a titration to determine. The chloride ingress was also visualized with silver nitrate spray and with electron probe microanalysis. These images show the chloride content versus depth into the sample. So from these chloride profiles, it is clear that the effect of the sulfates is time dependent. The green lines represent the solution with only the sodium chloride, whereas in combination 2, sodium sulfate is added, and in combination 5, magnesium sulfate. So, depending on the presence of the sulfates, we will have different profiles. There is, like I said, also a time dependence, and at very early exposure periods, there is a limited effect of the presence of sulfates. At longer exposure periods, there seems to be a decrease in the chloride diffusion if you add sulfates. And at longer exposure periods, there may be an increase, especially when cracks start appearing due to the expansive reactions of the sulfates. These profiles can also be explained a little bit more if we look visually at what happens. For instance, at lower exposure times, there is this formation of brucite in the case of magnesium sulfate being present, which blocks the surface and reduces the chloride ingress. Whereas at longer exposure times, the brucite layer is breaking down and leaves behind a mushy and porous layer. And then when cracks appear, the corrosion can really go much faster. This is also clear if we look at the concentrations of Friedel salt versus depth into our sample. This is at an exposure time of around 260 days. And then it is clear that for the solution which does not contain sulfate, the Friedel salt can be found at much deeper depths into the sample than when if also the sulfates are added. If we study our samples using electron probe microanalysis, it is clear that also the penetration depth of sulfates and chlorides into the samples is different. Actually, the chlorides penetrate much deeper into the samples than the sulfates. You may think from this image that it is not the case when you look at the color codes, but here you should notice that initially there are already sulfates present in the sample as gypsum or anhydride. So this is just kind of the initial concentration, and the increased chloride concentrations can only be found in the outer layer, whereas the chlorides are penetrating much deeper into the sample. When looking at those chloride profiles, we can also use the model codes to come to a service life prediction. In the current models, the effect of sulfates is not taken into account, but there are effects that can be introduced due to aging of the samples, temperature, and so on. This is one of the outputs of the modeling, which shows the probability of failure versus time. And these lines show that when the probability of failure increases above 10%, there is a dangerous situation, and this can be considered as the end of service life. In gray, you can see the effect of a varying concrete cover on the probability of failure. So the reference value is 50 millimeter. This is the dashed line here. And if the concrete cover would be varied with minus or plus 10 millimeter, this can lead to a quite large difference in predicted service life between less than 100 years and about 300 years. On the other hand, for a cover of 50 millimeter, here the changes due to our studied ranges of sulfate content are presented. So these changes in sulfate content can have a large effect on the service life, but it is more limited than the effect of the concrete cover, as you can see here. So we have seen that sulfates have a time-dependent effect on chloride diffusion. The influence on the service life is large, but maybe less important than the effect of other parameters such as the concrete cover. As a second part of the presentation, I want to give more details about our research on the presence of cracks and the effect of crack healing. If cracks are present in concrete, this will of course lead to a much faster penetration of chlorides and sulfates into the matrix. However, small cracks can heal by themselves due to the autogenous crack healing properties of concrete. If water penetrates into the crack, unhydrated binder particles at the crack wall can hydrate and lead to precipitation of calcium silicate hydrates. Furthermore, if carbon dioxide penetrates into the crack, it can react also into calcium carbonate, further blocking the crack. We have studied these effects by creating cracks in cylindrical specimens by a splitting test with two different crack widths of 100 and 300 micrometers. Then those cracks were allowed to heal by continuous or cyclic immersion to simulate real-life situations like submerged zones or tidal and splash zones. These graphs show autogenous healing in solutions where sodium chloride is present. As you can see here, the crack closure is shown versus the immersion time for samples with only Portland cement or samples with 50% blast furnace slag. The last ones seem to show a slower crack healing, but for both, the cracks seem to slowly close. Still, after 200 days, they have not been closed completely. If magnesium sulfate is added to the previous solution, you can see that the crack healing goes more rapidly and reaches more complete crack healing values of nearly 100%. This is again due to the precipitation of brucite in the crack. In the next slide, we can see a comparison between healing in distilled water and in sodium chloride solution. And this for two different sizes of cracks, small cracks in green and cracks larger than 100 micrometer in gray. If we compare both graphs, it can be seen that there is not much difference between healing in water or in sodium chloride. What is also clear is that small cracks can heal completely after some time, whereas cracks larger than 100 micrometer would not heal completely or need a much longer time for healing. Very important also is that as long as the crack is not completely healed, there is still a preferential penetration of chlorides through the crack and into the matrix. And we have found that the critical crack width is as small as 10 micrometer. So as long as you have a crack of more than 10 micrometer present, you will have faster ingress of chlorides along the crack. So we have seen that autogenous healing is not significantly influenced by the composition of the solution. Chlorides do not really delay or accelerate crack healing. Presence of magnesium can lead to more complete crack healing, and you will need a quite small crack width and a very good healing to have no chloride penetration at all. To have a faster and more reliable crack healing, we can also engineer the concrete to have some autonomous crack healing properties. We have studied a lot of different ways to obtain this autonomous crack healing, by incorporating superabsorbent polymers or bacteria or encapsulated polymers into the matrix. Here I will give some results about the effect of polyurethane in macrocapsules, which has been introduced into the mortar. So when a crack is formed, these glass capsules break. This is a proof of concept experiment. The polyurethane prepolymer is released, makes contact with humidity, starts to foam. It can expand quite a bit in volume and may fill the cracks completely. In this image of electron probe microanalysis, you can clearly see that if the crack is not healed, the chlorides will not only penetrate from the surface, but also into the crack and from the crack into the matrix. In order to obtain chloride profiles, in this case, we decided to grind in different zones around the crack and further away from the crack. So if you take the profiles nearby the crack, it is clear that if you look at the uncracked reference, you have a much faster chloride ingress if cracks are present. On the other hand, if the cracks are properly healed with polyurethane, like in the green curve, then you have a slowing down of the chloride ingress in comparison with the cracked sample. This is an average of different profiles. However, when you look at different samples, it is clear that when the healing is complete, as for those green lines, you have actually the same condition as for an uncracked sample, whereas if the healing was not very efficient, the chloride ingress may be as worse, almost as bad almost as for a cracked sample. We have also studied the effect of crack healing on actual corrosion of the rebar, and more results can be found in the paper mentioned here. So we all know that when a crack is present, chlorides will penetrate much faster and a local anode will be formed where the iron goes into the solution. Electrons will go to the cathodic zone where they will react with water and oxygen, and the final reaction product will be rust, which will be deposited somewhere in between the anode and the cathode. In order to be able to measure this corrosion current, which is an indicator of ongoing corrosion, we have separated the anode from the cathode and have connected them again outside of the sample so we could measure the corrosion current. This is the actual setup that we have used with a small anodic rebar with only the middle zone exposed and a huge cathodic reinforcement cage. You can also notice here the capsules with polyurethane prepolymer that are present at a location where the crack will be formed in a 3-point bending test. So this is the actual image of our design of the reinforcement. So these prisms were cast and cracked at 28 days of age. Then they were stored for 48 hours at 20 degrees and 60% relative humidity to allow the polyurethane to cure completely. And the specimens were mounted in a steel frame to keep the cracks open at exactly the same width. We have then put some aluminium foil around the sample and created 3 separate basins on top of the sample. The crack was facing upwards, so we could put in the middle a sodium chloride solution and at the sides a calcium hydroxide solution. So the samples were subjected to wet-dry cycles of 1 day wet and 6 days dry for a total period of 44 weeks. We measured then every hour automatically the corrosion current and also weekly manually other electrochemical parameters like potentials and anodic and cathodic polarization resistance and concrete resistance. If we then monitored the corrosion current over time, it was clear that for the uncracked samples over the complete duration of the experiment, almost nothing was measured. However, if this is compared with cracked samples, these graphs show that corrosion appears after already a few weeks' time. This was also clear at the end of the experiment when we removed the rebars, that there was a clear visual corrosion, formation of rust, and after cleaning of the rebars, we would clearly see the corrosion pits. In this graph now also the corrosion potential is shown, which remains around 0 for the uncracked samples, but for the cracked samples drops to large negative values pointing at active corrosion. If we tested self-healing samples, we used 2 different types of polyurethane, and the blue curves are for polyurethane with a quite high viscosity, which was not able to fill the cracks very well, resulting in corrosion at about the same rate as for the normal cracked concrete. Whereas for the green curves, a polyurethane with low viscosity was used. And here it is clear that the corrosion currents remain very low and the potential also remains near 0, which is very similar to the non-cracked situation. We can then do a service life prediction based on the volume loss calculated by Faraday's law, differentiating between the initial period and then the more steady later secondary period. So the electric charge passed through the steel that we measured can be used to calculate the final mass loss of the material. And for cracked samples, we found a mass loss of around 0.2 gram of the reinforcement steel. This mass loss was then further used in a simplified hemispherical pit model to calculate the loss in cross-section of the steel. So this is shown here for the cracked and for the polyurethane self-healing samples with low viscosity polyurethane, where, as you see, we calculated the mass loss in the initial period, and then also in the secondary stable period, we had a mass loss per week, which was much lower in the case of the self-healing sample. From these results and the pit model, we could then obtain values for instance, the time after which the cross-section would be reduced by 26%. In the case of a crack, this could happen already after as few as 2 to 3 years' time, whereas in the case of the samples self-healed with polyurethane, the service life would increase, if you take this as an indicative value of service life, would increase to a value of 40 or even more than 100 years in case the healing was really perfect. We finally did also some life cycle assessment for these self-healing samples, where we also looked at economic allocation of the impacts. We did not include the transport impacts of the constituent to the concrete plant, but we did include the environmental impacts associated with the production of the ready-mix concrete. And for the polyurethane foam, we adapted the existing eco-invent data. This was another situation than the one I showed before. We modeled steel reinforced concrete slabs with a certain variable load and a design service life of 100 years. And then we studied the effect of the presence of cracks on the service life. So whereas for uncracked concrete, the service life was nearly 100 years, for the cracked concrete, this was reduced to 7 years. And with the self-healing material included, it could be around 80 years. This was used to estimate the number of repairs that would be needed in a 100-year service life. So for the last 3, only 1 repair would be needed. And for the cracked concrete, many more repairs would be needed. This, of course, has a huge effect on the global warming potential. And here you can see the effects of the different scenarios and the different elements in the slab on the global warming potential. So some effect is due to the concrete of the slab and the production of it. Some is due to the rebars. Very small environmental impacts are linked to the presence of the capsules and the polyurethane, but very important is that by self-healing, you can reduce enormously the number of repairs needed, because here, if you need a lot of repairs, this will create a huge global warming potential. So to conclude, if we want to study concrete in marine environments, we have to consider the realistic attack mechanisms, which means combined attack, which is dependent on the cation, the temperature, and the binder. It's quite complex, and it has a large influence on the service life, this combined attack, but can be larger than, for instance, the cover depth. It can be smaller as an effect, sorry, as for instance, the cover depth. Material properties are also important. If cracks are present, the service life will decrease a lot. So we can overcome this by using self-healing concrete, which will improve the durability. However, at the moment, the systems are maybe not yet 100% reliable and will need further research. But if healing can be well done, the service life will increase, the number of repairs will reduce, and the environmental impact will reduce as well. So for some further reading, feel free to consult those papers, and for any questions, I can always be contacted by mail. Thank you very much for your attention.
Okay, let's thank Professor Nelly Bailey for the interesting work on the concrete durability under sea marine environment, which is very interesting. As you have, as I have noticed, that there were some questions in the QA, but since she's not here, you can send Professor Bailey an email as in the, we will send it in the chat box of her email, and also you can send your question to us, which we will also provide a email, and we will let her know of these questions and get back to you of her answers. So let's welcome Dr. Lin Guan for introducing the next speaker. Lin Guan.
Yeah, hello. Can you hear me?
Yes, yes.
Okay, so thank you very much. It's a great honor that I could be one of the chair of this final section of the workshop. My name is Dr. Guan Lin. So our next speaker is Dr. Debo Zhao. Dr. Zhao, are you here? So you can share your screen. Yeah. Dr.
Yeah, I'm here. Can you hear me?
Yes. Dr. Zhao is currently an assistant professor at Shenzhen University. Before that, he received his bachelor degree and a PhD degree both from Hunan University. And his research interests include performance of RC structures under extreme loading and the corresponding retrofitting and strengthening techniques. And the title of his presentation today is Experimental Study on Dynamic Behavior of Large Rupture Strain FRP Strengthened RC Beams under Impact Loading. So let's welcome Dr. Zhao. It's your time.
Hello. Thank you, Dr. Lin. Can you see the slides?
Yes.
Okay. It is my great honor to have the opportunity to speak at this meeting. So hello, ladies and gentlemen. I'm Zhao Debo from Shenzhen University. Today, I would like to introduce my recent study about the experimental studies on dynamic behaviors of large rupture strain FRP strengthened RC beams and impact loading. So my presentation has 4 parts. I will introduce the research background first, and then I will introduce the response characteristics of RC beams and impact loads. This is the basis of the strengthening beams. Just like to cure a disease, we have to know how the disease comes out. The third part, we talk about how to use LRS FRP to strengthen RC beams and impact and its dynamic behaviors. And the last part is conclusions. So I will introduce the research background briefly. So the concrete structures may be subjected to dynamic loads arising from impact. There are several kinds of impact events in civil engineering, such as natural disasters, traffic accidents, and terrorist attacks. And the catastrophic destruction of structures and impact indicates serious problems of these structures, and clarify the dynamic failure mechanism of RC structures and impact loads as the basis for reasonable design and strengthening. So we first investigate the response characteristics of RC beams and impact. We use drop weight tests. The test program include drop weight test of 10 beams and 3 static loading beams. The specimens were divided into 3 series. In each series, all specimens had the same size and reinforcement. The primary variable between the B and C series was beam length, and that between the C and D series was stirrup based. Here shows the static results. On static loading, the BS specimen had an overall fracture response, where specimens CS and DS both exhibited shear failure mode. And this is the impact test results. It can be seen that the failure patterns of specimens on impact is different from that on static loading. Basically, the cracks of RC beams failing in shear and impact loading can be grouped into 2 categories. This is the first one is inclined cracks in the shear span that are similar to shear cracks on static loadings. This we call it the type 2 crack. And the second one is the diagonal cracks forming a shear plug near the loading point. This we call it type 1 crack. This failure mode is a characteristic dynamic phenomenon that has not been identified in static tests. And we also found that with impact velocity increasing, type 1 crack tends to dominate the failure. So we also use a high-speed camera to record the failure process of specimens. And it can be seen that for the specimens failing in fracture, fracture cracks emerge first. And with the beam deflected downward, you can see the concrete at the impact loading crushed. However, for the specimen failing in shear, you can see diagonal shear crack developed rapidly, and no other cracks were observed. And the whole failure process for shear failure lasted for only several milliseconds. It's really short duration. And this video shows the crack propagation of type 1 and type 2 shear cracks. It can be seen clearly that type 1 crack emerged earlier than type 2 crack. So we also conducted a FE simulation to the test, and here shows some details about the FE model. And the simulated results were basically in good agreement with experimental results, especially for specimens that failed in fracture. It can also show the change of failure modes with impact velocity increasing from fracture failure to shear failure. So with the FE model, we can get more data that is hard to get in the experiment. So the left video shows the deformation during the impact process. It can be seen that the deformation concentrated at the impact point at the initial stage and propagated to the supports gradually. And the red graph shows the shear and moment distribution along the beam length. It can also be seen that these internal forces concentrated near the loading point at the initial stage. So, so typical time history of moment and shear force at the critical section. What we call the critical section is at the middle of the type 1 crack. It can be seen that the moment and shear force histories can be divided into 2 stages. The first stage is the local response stage. At that stage, both the shear force and the moment increased rapidly. And the shear force is extremely large, and the moment is relatively small. The ratio of the moment to shear force was smaller than the static loading conditions. And for the following overall response stage, the shear force was proportional to the moment, which is similar with that of static loading. And with these findings, we can explain the failure mechanism of type 1 failure. So the type 1 shear failure occurred very early during the impact process, and the stress waves generated by the impacting load were unable to reach the supports. Therefore, the effective span is much smaller than the beam span. That's why the type 1 cracks so close to the impact point. So based on the above findings, we built a simplified model which can predict the shear and fracture damage competitively. Then we are trying to use strengthening techniques to improve the impact resistance of RC beams. Here we use RSFP. So let's take a brief review of the traditional strengthening technology. It includes a steel jacket or externally bonded FRP. There are some limitations of conventional strengthening technologies, such as the durability concerns and the brittle fracture of FRP and the FRP debonding problems. Because impact loading requires high deformation capacity of RC structures, so the fracture and debonding problems of FRP becomes more severe. So to address these problems, this research project applied RSFRP to strengthen RC beams and impact. So RSFRP is a new material. It has larger rupture strength than conventional FRPs. It is also a recyclable material because it can be made from waste products such as plastic bottles. So we first conducted a SHPP test to investigate the mechanical properties of RSFRP confined concrete and impact. And the test results show that the dynamic mechanical properties of RSFRP confined concrete are much better to the unconfined concrete. And then we used RSFRP to strengthen RC beams. So let's review the response characteristics of RC beams and impact. First, the cracking and impact tends to concentrate at the loading point. And the common failure modes can be concrete crushing and the type 1 shear crack. And the second point is the input impact energy is proportional to the bending capacity and the maximum displacement. So the bearing capacity and the deformation capacity are both important. Based on these findings, we developed a corresponding strengthening method. Here we use PN FRP. So the brittle fracture of traditional FRP can be solved by material properties of PN FRP because it has large rupture strength. And the FRP debonding problems, we use an anchorage to prevent it. We use PN FRP bonded at the beam surface to increase the bearing capacity, and we use the RSFRP wrapping around the impact point to increase the deformation capacity of the plastic hinge. This is to increase the deformation capacity, the delta max. So 4 strengthening methods were used. The first one is externally bounded PN FRP, and the second one is anchorage FRP systems, and the third one is PN FRP wrapping around the mid-span, and the last one is the unified method, which combines the anchorage FRP and the PN FRP wrapping method. So the test method is repeated impact with a drop hammer until the specimen failure. here we define the specimen failure is either failure of the strengthening system or the RC beam. So the first group is the control specimen. It is unstrengthened. And the second one is the externally bounded PN-FRP group. It is mainly used compared with the unaccurate PN-FRP system. And this is the unaccurate FRP system. And the test variable in group is the FRP tab. As you can see, PN-FRP and CFRP were used. And the fourth group is the mid-span wrapping FRP system. And the test variable is wrapping length. And the last one is a unified strengthening method. So this is the test setup. You can see 3 high-speed cameras were used to record failure process from different perspectives. So this is the static test results. As you can see, for the unstrengthened beam, the failure of the beam is controlled by concrete crushing, and the load deflection curve is like this. And for the externally bounded PN-FRP system, there are small increase of the bearing capacity, but the ductility, as you can see, is reduced. And for the unaccurate PN-FRP system, as you can see, its bearing capacity increased. Will it maintains the ductility with the unstrengthened specimens. And for the CFRP specimens, as you can see, though its bearing capacity was increased, its ductility was decreased significantly. So for the mid-span wrapping system, as you can see, the ductility was increased dramatically. And for the unified strengthening method, you can see it presented the best form. Both the strength and ductility were increased significantly. So this is the impact test results of unaccurate FRP strengthening system. As you can see, EA-FRP at the beam soffit reduced the deflection and damage significantly compared with the unstrengthened beams. And the failure of CFRP specimens was controlled by FRP rupture, while the debounded PN-FRP was held by the unaccurate. So the EA-FRP system still worked even when the specimens underwent large deformation. But the failure of APD was also controlled by concrete crushing at the top of the beam. So this shows the high-speed video, and you can see though unaccurate cannot prevent debonding of the FRP, it can hold debonded FRP and make the strengthening system effective. And the greater rupture failure of CFRP limited the deformation capacity of the beam, while the PN-FRP showed better cooperative working performance. So this is the mid-span wrapping system results. And as you can see, the wrapping length has an obvious influence on the response. If the wrapping length was too small, it cannot prevent the concrete from crushing. But with sufficient wrapping length, you can see the fracture failure mode was controlled not by the concrete crush, but by the tension rebar rupture. And the ductility and energy absorption capability increased significantly. So this is mid-span displacement histories. As you can see, the unified strengthening method, it shows the smallest mid-span deflection, indicates it has the best strengthening effort. and it also presented the best recovery capability. So this is energy absorbing capability. As you can see, also the unified strengthening method has the best energy absorbing capability. It is almost, it is 3 times of the unstrengthened beam. So this is some conclusions. So for the cases requiring high deformation capability of structures, LRS FRP presents better cooperative working performance with RC beams than CFRP. And the PN FRP laminate with an average is a good strengthening technique. And the FRP wrapping at the mid-span should have sufficient length to prevent the concrete crushing failure. So more details about the research can be found in the following papers. So we are still working to build the finite element model and to develop corresponding design methods. So that's all. Thank you for listening. If you have any questions, I'd like to give further explanation.
Okay, thank you, Dr. Zhao, for your presentation. As we know that the large rupture strength FRP has a very large deformation capacity, so it's especially attractive for the impact loading. So we still got 1 minute. Any comments or questions from the panel or the audience? We could allow maybe 1 question. Any question from the panel or the audience?
I have 1 question.
Hello, Professor Weder.
Yeah, Weder. Yeah, very interesting presentation. Thank you very much. If you try to utilize large fracturing strain, a PET could be the better, but why do you choose a pen this time? You couldn't find the PET fiber sheet?
You mean PET?
Yeah, PET.
PET fiber?
Yes, PET, yes.
I think PET fiber has similar similar material properties with PN FRP. So we for now we only test one kind of large rupture FRP. But as you said, the PET FRP may have a much smaller elastic modulus and larger rupture strength than PN FRP. So it is maybe much, so maybe in the further research, we can use the PET FRP, but for now, we only use PN FRP to investigate the response.
Okay, thank you.
Okay, thank you. Due to the time limit, maybe we can move on to the next presenter.
Yeah, okay, thank you, Dr. Zhao Debo. Our next speaker is Dr. He Wei. Dr. He received his PhD in geotechnical engineering from the University of Science and Technology in Beijing, and then he worked as a postdoc at Tsinghua for a period. And now Dr. He is in a lecture and the associate head of the Department of Civil Engineering at Beijing University of Civil Engineering and Architecture. And his research interests include concrete durability and the recycling of solid waste, with an emphasis on the effect of chlorine salt on the properties of slag-based geopolymer. And so let's welcome Dr. He. If you're ready, Dr. He, it's your time.
Yeah, yes, I'm ready. Can you see the screen?
Yes, clear.
Okay. Thank you very much for the introduction. Many thanks for giving me the chance. I'm He Wei from Beijing University of Civil Engineering and Architecture. We would like to give this presentation, strength and mechanism of stabilize the coastal saline soil by weak alkali activity slag cement. This work is an outcome of the close cooperation with Dr. Liu Chenbing, and I'm very grateful for this. Then I want to acknowledge the financial support provided by Beijing Municipal Nature Science Foundation and the National Nature Science Foundation of China. As you can see, the topic of my presentation was the effects of sodium chloride on the mechanical properties of slag-based geopolymer. However, while I was preparing PowerPoint, I realized that this topic may be not deep enough, so I added something more, and the topic is changed to strength and the mechanism of stabilized coastal saline by weaker accretor activity slag cement. In order to ensure the stability of the network, I will turn off the video on my face. Okay, this is an outline of my presentation. First is background. Second is the effects of sodium chloride on the mechanical properties of slag-based geopolymer. Then this is a long-term performance of coastal saline cooled by the slag compound cooling agent. The last is the conclusion. That's the first. The coastal saline in China is distributed mainly among the east coast of the North China, such as the Liaoning, Bohai, and the Laizhou Gulf. The coastal saline soil is usually a soil with fine particles, the formation of which is affected mainly by erosion of seawater. Usually, soluble salts contained in the North China coastal saline soil is mainly about 0.3 to 3%. Since the North China coastal area dominated by warm temperature, subhumid continental monsoon climate, the evaporation is greater than rainfall due to the erosion of seawater. As for the soluble salts in coastal saline soil, sodium chloride occupies the most. Compared with the ordinary soil, there is a lot of soluble salts in the liquid phase of the saline soil. The soluble soil in saline soil varies with temperature, cooling temperature, and the evaporation of water will cause the solids to begin concentrating into the solids, increasing the solid content. If not, it will go down. First, the coastal saline soil has elegant characters such as severe collapsibility, cellular heaving, corrosiveness, and water-induced softening due to the presence of sodium chloride. In December 2017, Beijing government published an official document issued options on the enhancement of construction of key platforms for industry transform and undertaking in Beijing, Tianjin, Hebei region. The new strategic document suggests that 2 carrying sails and 4 structural foundation areas pattern will be built. However, half of the structural foundation areas are seriously affected by saline soil. For example, the roadbed of a coastal highway in South Tianjin was made of certified coastal saline soil by land. However, just after 7 years, the pavement is seriously damaged. Many holes was found in the shoulder, and the roadbed is deformed. Since the solid and the water content changed rapidly, and the traditional cooling agent is hard to lower the solid content. The risk of expansion and dissolution remain unchanged even after cooling. And there's a coincidence. The region with the largest of coastal saline soil is also the region with the largest steel production in China, even in the world. Due to the high cost of road transportation, the slag price in other regions, such as Beijing, contains a larger population of freight costs. But in coast area of Bohai Gulf, the slag is very cheap. Before discussing the cooling effort of slag-based polymer on saline soil, we should know that what's the influence of sodium chloride in saline soil on geopolymer. Here's the second part, effects of the sodium chloride on the mechanical purpose of select-based geopolymer. As introduced, I got my doctorate degree from geotechnic engineering. In my doctoral program, I mainly focus on the surface life prediction of shaft exposed to softened environments. The very first vertical shaft I ever seen is in Linghuan coal mine. This coal mine was completed in 1985. The sidewall of the Alexei shaft is in surface soil is made of 1.35 meter thick doubly reinforced concrete, and in bedrock section, is made of 0.5 thick C30 plain concrete. For the plain concrete, sodium chloride was used as an early age strength agent, and about 4 kilograms of sodium chloride was used in 1 cubic meter concrete. At that time, I wondered if sodium chloride can be used to activate slag. With that idea, 36 slag-based geopolymer polymer motor samples containing sodium chloride were prepared to clarify demonstrate the effects of this on the geopolymer. Then 36 SG samples that does not contain sodium chloride was prepared. The only difference between the two kinds of samples was the content of sodium chloride in the latter, as the number is too big. Not all the SG samples are shown. According to Portland cement stands, the sample number 4 meets the strength stands of 32.5 grand slag Portland cement. Compared with the sample does not have sodium chloride, the strength is increased about 50 and 22% at the age of 3 and 28 days. You can see. This indicates that adding an appropriate amount of sodium chloride affects the mechanical purpose of geopolymer and increase its strength. There are some SEM graphics of the past. You can see needle and rhodal crystals and some tablet crystals was generated after hydration. Then we're doing some EDS and XRD tests trying to identify the components of these crystals. We found that sodium and the chloride are engaged separately in hydration reactions with the geopolymer, which generates new hydration products. There's Guzel and the net. Since Guzel and the net are insoluble, we wonder if sodium chloride is removed. This kind of slag-based geopolymer can react with the sodium chloride in coastal saline soil. Then it can be a very good, I think it can be a very good cooling agent for coastal saline soil. Then we come to the third part. The long-term performance of coastal saline soil cooled by the slag compound cooling agent. As described before, when we use the sodium chloride, gypsum, quicklime, and magnesium as the compound activity, it can meet the stand of 32.5 grand slag Portland cement. So after the sodium chloride component was removed, it can be a cooling agent for saline soils. The test saline soil was taken from our coastal area in Tangshan. Once in the laboratory, the soil was first dried and then smashed. Shells and other debris in the saline soil were removed after the soil passed through the 5 millimeter seal. Then water was added to the saline soil according to the natural water content. The soil, after mixing, was placed for 24 hours to ensure that the saline seal with the natural water content was prepared. Then the agent and the soil was mixed At last, the mood was filled and are compacted by vibration. Then we analyzed the soluble salts in the cooled soil samples, and we can see that the soluble iron content, especially for sodium chloride and the sulfate radical in saline soil, significantly decreased with the increase in time. According to the classification of saline soil in Code for Investigation of Geotechnical Engineering, after 28 days of curing, the salinity degree decreased to weak, and after 90 days of curing, since the soluble salts were too low, and the sample cannot even be called saline soil. And you can see what's more, at 1,900 days, water-soluble salt components continues to decrease. We can see that the strength basically increase with the increase of age. The strength increased fastly in the first 180 days, reaching 2.24, 5.96, and 6.98 memper in 7, 90, and 180 days. After that, it was basically in slow growing. The strength in 1,900 days increased by 8.74% compared with in 180 days. And you can see that the soft coefficient shows that the water solubility is also very good. Then we do some XRD and EDX test. Due to the time constraint, the analysis process is omitted. We found that Cosel salt in the sample, since the cooling agent does not contain the chloride, it appears that the chloride is from the saline soil, as we predict. Moreover, the hydration products also include MSH and FT, and all which together improve the strength. Complex hydration reacts occurs between slag, quicklime, gypsum, and magnesium. First, you can see that calcium hydroxide is formed because of the presence of calcium oxide in the agent. Then is the following reaction occurs, and the activated magnesium oxide reacts as follows. Since the soluble of magnesium hydroxide is lower than that than calcium hydrochloride, magnesium first binds to hydroxide radical to form magnesium hydroxide, which replaces the calcium hydroxide to react with the dissolved activated silicon dioxide. Then calcium hydroxide continues to undergo a series of chemical reactions with active silicon and alumina. When it reacts with water, part of hydroxide calcium aluminate react with the gypsum to form FT. Another part of hydroxide calcium aluminate react with the sodium chloride in the saline soil to form the Friedel solid. The Friedel solid continue to react with solid radical in gypsum and solid soil in the environment with a large concentration of sulfate radical. As a result, a part of the chloride was replaced to form Cosel solid. Sodium chloride, sodium hydroxide, a byproduct of forming aforementioned reactions, byproduct of affirming reactions continue to act as an activity of the snake. Analysis result of the XRD reveals that the hydrogen product include the LH. Therefore, the chemical equation of the slag in the sodium hydrated environment can be expressed simply as follows. You can see. At last, here's the conclusion. After incorporation the agents into the saline soil, the slag stimulated to the activity of the calcium oxide. Alumina and the silicon dioxide under the action of gypsum and the quicklime result in the hydration of slag to form hydrate calcium silicate and hydrate calcium aluminate. Part of the hydrating calcium element react with the gypsum to form FT, while another part of hydrating calcium element react with the chloride in the saline soil to form Friedel solid. However, the Friedel solid was not stable, and the Kuzel solid was finally formed under the effect of sulfate radical. A calcium hydride, a product of the forming process, provide a more acting environment for the slag, which further increase the activities of the calcium oxide, alumina, and silicon dioxide to gain more CHH and ZH. So I think it has a very good potential for cooling saline soil. Thank you for your attention. Here's my email, Richard, if you have further questions.
Okay, thank you, Dr. He. Very interesting work on the geopolymer. So is there any question from the audience and the panelists, please? We have time for 1 to 2 questions. All right, it seems that you have made a great presentation. It's very clear to everyone, so there's no...
Thank you.
Oh, actually, wait. There's a question in the QA. Just want to know a detail of your curing procedure, direct immersion in your curing solutions or sealed with plastic fumes. Have you considered the leaching of chlorides?
Yes, it was not put in the water. It was imported in a room and with high humidity. In your question, I think there's no leaching of crinols.
Okay. Yeah, that's the question from Dr. Xiang. So, yeah. And is there any other questions? Okay, so if there's no other question, I guess we can move to the next presenter. Thank you. Dr. He, yes. Yes.
Okay, our next speaker is Mr. Wei Zhao. Ms. Zhang is now a PhD student at the Department of Civil and Environmental Engineering of National University of Singapore. She obtained her master's degree from Dalian University of Technology in China in 2020. Her research focuses on seawater and sea sand concrete. And the title of her presentation is the impact of seawater on cement hydration and motor strength. So let's welcome Ms. Zhang Wei.
Hello, good afternoon, everyone. It's my great pleasure to give this presentation. The topic, can you see my PPT?
Yes, very clear.
Okay. So the topic of my report is the impact of seawater on cement hydration and mortar strength. I will introduce the following 4 components, mainly include the hydration and strength performance of seawater cementitious material. Sorry. Water scarcity is a great constraint to concrete production, as shown in this map. The areas highlighted in yellow are facing physical water scarcity. Physical water scarcity means that the water resource development in these regions is approaching or has exceeded sustainable limits. More than 75% of river flows are withdrawn for agriculture, industry, and domestic purpose. According to United Nations World Water Development Report, nearly 6 billion people will suffer from clean water shortage by 2050. Water concrete production consumes several billion tons of fresh water annually. In 2050, 75% water demand for concrete production will occur in regions expected to express water scarcity. Given the fresh water shortage, seawater, which accounts for about 96.5% of water resource on Earth, appears to be an alternative resource to produce concrete. The main ions in seawater include chloride, sodium, magnesium, sulfate, calcium, potassium, and carbonate ions. The ion concentration of a substitute ocean water specified ASTM standard is between the actual ion concentration of seawater in different regions. The chloride in seawater has the highest concentration, which may cause the corrosion stim reinforcement, which has been reported by many professors yesterday and today. This issue may be alleviated by replacing stim reinforcement with non-corrosive reinforcement. In addition to steel corrosion, what are the other effects of high ion concentrations? Most researchers tend to just use seawater directly to prepare samples. However, the discussion on the difference between the effects of different water is limited. To answer the last two questions, we conduct a preliminary study on the hydration properties of cement paste mixed with distilled water, tap water, filtered seawater, and seawater. In addition, the strengths of mortar mixed with tap water and seawater are analyzed. Let's move to the second part. The ion compositions of seawater near Singapore are also chloride, sulfate, sodium, magnesium, potassium, calcium, bromine, strontium, and aluminum ions. The pH value of seawater is 8.13. Generally, the pH value of surface seawater is between 8.1 and 8.2. The weak alkaline of seawater is due to the hydrolysis of weak acid ions such as hydrogen, carbon ions, and carbon ions. The following picture shows the location of seawater collection, which is located at the east coast of Singapore. The normalized heat flow of cement paste mixed with different water is shown in this figure. For filtered seawater group, seawater was filtered through 0.45 micrometer process before sample preparation. The experiment results indicate that there is no obvious difference between the hydration heat of cement paste mixed with distilled water and tap water, or cement paste mixed with filtered seawater and seawater. Seawater can accelerate the early age hydration. This accelerate, in fact, can be seen as both at higher silicon peak and as higher sulfate depletion peak, as well as the early time of peak occurrence. For cement paste mixed with seawater, the heat of silicon peak was 42% higher than that of cement paste mixed with tap water. The time to reach the peak reduced by 1.8 hours indicate that the hydration of tricancer silicon is promoted. The heat of sulfate depletion peak increased by 30%, and the time decreased by 2.3 hours. It means that the hydration of tricancer aluminate and aluminate ferrite is improved. Similarly, mixture with seawater released higher cumulative height at early ages. However, this effect decreased with time. At 7 days, the the heat release from cement paste mixed with seawater is almost in addition to that cement paste mixed with distilled water. And it is about 10% higher than that cement paste mixed with tap water. When seawater is filtered, the heat release of cement is close to that of cement paste mixed with tap water at 7 days. It is proposed that chloride in seawater is one of the main reasons for simulating cement hydration. Firstly, calcium hydroxide could react with calcium chloride to form insoluble solid form calcium oxide chloride. This process will reduce the concentration of alkalinity and calcium in solution. As a result, the cement hydration will move faster. Secondly, the chloride could react with aluminate and ferrite to form Friedel salt, which may densify the cement matrix. The reaction equation is shown here. If iron present, then this product will also form. Thirdly, the sodium ion and magnesium ion in seawater would affect the dissolution of tricalcium silicon and the precipitation of hydration products. The composition of cement paste mixed with tap water and seawater was determined by thermogravimetric analysis. It can observe that the CSH and potentiate are made hydration products for both samples. Marmol carbon aluminate rather than marmol sulfate aluminate is formed in cement paste mixed with tap water due to the acid carbonate from limestone. Calcite is a mineral in limestone in cement. Friedel salt and magnesium can be absorbed from cement paste in cement paste mixed with seawater. Friedel salt could be dehydrated at 120 degrees. Therefore, Friedel salt cannot be distinguished with monocarbon aluminate from TG analysis. The total mass loss and the content for calcium hydroxide could be calculated according to the above TG curves. For both samples, the total mass loss increased with curing age. Seawater can increase the calcium hydroxide content by 12.3% at 1 day and by 6.6% at 3 days. The increased calcium hydroxide content indicate that seawater can increase the hydration degree up to 3 days. On the figures below are diffraction patterns for cement paste mixed with different water. 4 miners in cement, namely tricalcium silicon, dicalcium silicon, tricalcium aluminate, and aluminum ferrite, decreased with curing age at different rates. The intensity of Portland was much stronger than other products. Friedel salt is the main difference between cement paste mixed with tap water and seawater. The morphology of Friedel was observed by other researchers through SEM observation. The element spectrum shows that the chloride in seawater is found in Friedel salt, as we can see from here. Seawater can increase the pressure strength and compressive strength of mortar up to 3 days. This result is consistent with the above analysis. The mixture for mortar is shown here. Seawater can increase the pressure strength by 11.6% at 1 day and increase pressure strength by 32% at 1 day. In conclusion, seawater simulates the early age hydration and improves the hydration degree of cement up to 3 days. Chloride reacts with calcium hydroxide and aluminate. Sodium ion and magnesium ion in seawater promote the dissolution of tricalcium silicon, therefore accelerating cement hydration. Friedel salt formed in cement paste mixed with seawater. Last but least, seawater improves the flexure and the compressive strength of mortar at early ages due to the accelerated hydration degree. Thank you for your listening. This ends my presentation.
Thank you, Ms. Zhang, for your presentation. Ms. Zhang focused on the effects of seawater on cement paste, right, instead of concrete. Any comments? We could entertain one or two questions. Any questions from the panel or the audience?
Can you hear me, please?
Yes, yes, please.
I'm C.S. Poon, Polytechnic University. Yeah, very excellent presentation, Ms. Jiang. Yeah, and
thank you.
Actually, many people have done the hydration of cement paste with seawater, right?
Yes.
And you also quote some references. And so, what is your aim? The aim of your research, and how different is your research from others?
The main difference is I compare the effect of different water on the hydration of cement paste. We use the distilled water, tap water, filtered seawater, and seawater because other researchers can just use direct